Good morning, everyone, and welcome to day 2 of Ethereum Zurich. It's nice to see all you early birds here today, and I think we got off to a really good start yesterday with an amazing program, and I believe we have a pretty good program on today to keep the momentum going. My name is Tom Lyons, and I am the Director of Communications and Content at the Enterprise Ethereum Alliance. And I'm going to be your host this morning until lunchtime. And after lunch, my good Crypto Valley buddy, Ian Simpson, will take over and take you through the rest of the day. Before we get to the program, I just wanted to say a couple of things. On behalf of the EEA, I'd like to thank Professor Tessone, the Uni Zurich, blockchain team, Pawn, and all the sponsors, and everybody who worked together to put this show on, especially my new buddies at GM Events. I've been watching from the sidelines for the last couple of months as everyone's been working really hard to put this together, and you've done an awesome job, so well done. I also wanted to mention at the EEA, the Enterprise Ethereum Alliance, we work to foster adoption by businesses of Ethereum and Ethereum-related technologies. And we do this through education, we do this through communications, we also do this through technical standards, as, for example, my colleague Charles Neville in a workshop yesterday talked about our ETH Trust security standard. And it's really, the thanks go out to all the developers, all the researchers, all the educators and communicators in this Ethereum community who really push this technology forward. It's amazing how far the Ethereum community has come in a very short time from a technology standpoint, and I think it's just getting started. I think it's going to be a lot of more great things to come. And without further ado, I think we'll get the program started. We're starting off this morning with Joseph J. from Pawn, and he's going to talk about Pawn's new crypto native economy report. Joseph?
Thank you, Tom. So first things first, you have my deepest appreciation for being here early. I know it's tough to wake up in the morning. Well, kudos to you. So today I want to talk about something that we did at Pawn recently, which is the Crypto Native Economy Report. It's basically a dive into understanding a bit the entire scope of on-chain transactions and user demand that happens on the various blockchains and in between the dApps. My name is Joseph J. I wear many hats, which I switch frequently. So first things first, I'm part of an establishment called Parallel Polis, which is a crypto native hub in Prague. It's basically a space that's dedicated to educating around mixture of technologies and art and scientific topics, and it's also the headquarters of headquarters is not really the right word, but in Parallel Polis there is the world's oldest crypto-only operated coffee in the world, essentially since 2014. The cafe establishment only accepts cryptocurrency, so there is no way to pay in cash, there is no way to pay using cards, but the whole purpose of the concept is essentially to bring people into crypto through some tangible experience. So if they want to get a decent coffee, they either already need to be onboarded, or the staff will explain to them how things work, and they will make their first crypto transaction for actually buying coffee there. I was also part of the Ethereum Foundation for quite a bit. I was part of the DEF CON team. Opened up the hackerspace called Bordel in the basement of Parallel Polis, which now is basically put on hold until we all get back to Prague for ETH Prague finally. So I've also organized some community conferences such as ETH Prague or Ethereum Zurich with the production crew. And last but not least, it's actually the majority of my time now. I work at PawnDAO. So today I'm going to tell you about what we did in the crypto economy report. First, I want to define the term. So who are crypto natives? What do we consider the crypto native economy to be? And then finally, we will look into some of the numbers. It won't be super detailed in terms of the numbers themselves. So you will see a bunch of graphs, but the whole purpose of this talk is basically to get you to see the paper is 37 pages of data from the various dApps. So, who are crypto natives? Well, you know, we're probably not so bold to like come and tell you like this is our definition of like whoever this like new demographic or personality could be. So we started doing instead was we started pulling in other people from the industry for interviews, and we started asking them the question, who is a crypto native? And all of these people were people that we kind of assume are crypto natives that, you know, are part of this ecosystem for quite a bit now and have a decent traction in like building or educating about a space. So the one thing you can do is basically go to our blog, pond.mirror.xyz, and read all of these interviews. There's also kind of like a too long didn't read version, basically compiled definition of who a crypto native is that we got from GPT, basically pouring the interviews into it, which you can find on our Twitter. But I will just tell you like my current definition, like in my opinion, who I think a crypto native is. So first things first, it needs to be a person who uses crypto assets, who owns crypto assets. But I think the word you use here is very important because in my opinion, a crypto native isn't just someone who invests in cryptocurrencies or in tokens and just like have them in their wallet or sitting on an exchange and basically just waiting for appreciation. In my opinion, crypto native is actually someone who like lives it, who uses crypto in not necessarily day to day, but you know, like you should be a savvy user of a variety of DeFi apps. Like you should have tried like using a DAO or something, or like voting in a DAO and basically like try out what's out there. So another important aspect is using DeFi or like having DeFi as not a secondary way to like handle your finances, but the primary way of like how do you reason about like your you know, your wealth or where do you save money? So instead of like looking at, I guess, like traditional means of just like putting you know, $100 into your pension fund, you'll be looking at like the DeFi protocols, figuring out like what actually makes sense for storing your assets or like putting them to good use. Another important and, you know, like quite, I guess, like more frequent in the last 2 years is also a person who actually gets paid in crypto. So there's a whole bunch of people now that can choose to be paid, to have their salaries paid in cryptocurrencies, especially here in Switzerland. It has been so for quite a bit. But there's also an increasing amount of people who work for DAOs and just like, they don't even have a regular contract. They just like are being paid through the different means of like collective treasuries and having their roles basically just captured in like a smart contract, which pays them if a certain like group of voters agree. Another thing that I actually want to use the opportunity here in Zurich to maybe have some of the attendees to explain to me another aspect of like who crypto natives are is it's people who don't understand the concept of bank holidays. So it's like beyond me how in 2023 like international bank transfers take like multiple days and don't work over the weekends or like don't happen at night and so on. So I guess it's just it's just a realization of the technological gap between the current system and what crypto actually enables now today in terms of the ease of use or like ease of transfers. So all in all, crypto natives, in my opinion, are people who like see and reap the benefits of crypto, that already kind of like realize the 10x benefits for them, not necessarily having to push it on other people, but are basically like here, like not even for, I guess, the low-level tech, but for simply like using the stuff that the entire community has created over the course of the last decade. So what's the crypto native economy report about then? So what we started looking at was, well, okay, well there is this new demographic that's kind of imminent. It's happening. There's a whole bunch of people that we can associate as crypto natives. And what unites them is that their transactions or their interactions are happening on chain. What's a transparent, like proof of usage. So let's just say, like, what if we forget about all of the other parts? What if we forget about centralized exchanges? What if we forget about all of the, like all of the SaaS services or like consulting services, whatever it's like around crypto? What if we forget like fiat exists and we just focus on what we can actually track on chain? And we basically just say, all right, let's take the fees that people are willing to pay into the protocols, to the validators or the miners. Let's even forget about like mining rewards and like newly minted coins. That's definitely an incentivization part, but it's not necessarily. And you could argue, really, open to hear that argument. You could argue that, well, it's like a collective revenue or like collectively decided fee to be paid to these maintainers of the network. But we were really just interested in like how much are people willing to pay for using the protocols themselves or some on-chain services. So fees that are directly being withdrawn as part of transactions, part of dApps. And yeah, and we just said like, that's it. Let's start with this as the base segment. Let's forget about all of the rest. In this particular report, which is the first one we made, we don't also look all that much into how much people are earning from these protocols then, like how the DAO salary structure works, but it's definitely something that we want to add in the near future. So basically now we are looking at what happens on chain, what is like verifiable, things that generate value in terms of the demand for those services and willingness to pay fees, yeah, like in the near future we'll be also looking at how that actually transitions into then like again the purchasing power through like salaries and services, but that's not the part yet. So we looked at, we have like two data sources. Obviously like a whole bunch of these things are on chain, but there is a convenience in using already existing databases. The primary source was Token Terminal. The secondary source was DeFi Llama. The data was basically captured on 1st of January 2023. And the data we consider in the report is essentially everything that happened in 2022. So there's definitely some like limitations that I should mention. I already mentioned that we are literally only looking at like protocols and dApps. We're not looking at like exchanges. We also don't look at like price movements. It's mentioned in the report just for allowing to, I guess, like visualize. So 2022 was, the bear market or the bear market slope. And all of these fees, in the case of a report, are denominated in US dollars. What you will see in most of the charts, obviously, like the trajectory of the bear market. But what you have to take into account is that those fees are basically counted at the time of the transaction, and at the time of the rate of the particle token the fee was paid in. So. In the report itself, what you can basically compare is how these different protocols or dApps have performed compared to the overall market price movement or like the general market cap of the entire industry. So even though you'll see a whole bunch of like falling graphs, it doesn't mean that these dApps necessarily actually had lower interest than the previous months. So in terms of infrastructure or L1 blockchains, these five, Ethereum, BNB Chain, Bitcoin, surprisingly Avalanche, and surprisingly Filecoin, are the five blockchains that basically together make up 97% of all of the L1 fees. in the space. Or at least like these are trackable and these are available like through the data sources that we used. All in all, on these 5 chains, the user fees that were paid ranged to $5 billion. For comparison, when we did our first like quick dive mid through 2022 for the past like 12 months, so it was like August 2021 until July 2022, this number was roughly $10 billion. So definitely different. And yeah, the interesting part here is that not all of these chains, not all of these protocols have the same trajectory throughout the year. So what we see here in the graph is basically Ethereum as the lead here compared to all of the other blockchains or protocols out there. So obviously, like you can see that in January. Oh, by the way, apologies, I heard it's illegal to use it. I won't point it towards you, but yeah. So in January, things started off like still in the bull market season. The fees like ranging to $1.5 billion. 91% of that is Ethereum, and then obviously you can see the decline throughout the year. But roughly, Ethereum still made up around like 70–80% of all of the protocol fees paid in 2022. So the second was BNB chain. BNB chain has definitely the largest traction in terms of user count. It actually has about 30–40% like more users or daily active users than Ethereum, and it basically followed a very similar trajectory. And again, what you have to take into account is that despite the number obviously falling throughout the year, the prices were falling like even faster. So this doesn't necessarily mean that there was actually less usage in the bear market. Another quite interesting thing is that, well, even though Bitcoin isn't the lead in terms of the fees paid, it definitely has a very stable community and actually increasing demand. So you know, compared to Ethereum, definitely wasn't that overhyped, but there is definitely a significant traction in terms of like just keeping users engaged on the network. Another interesting graph, which we probably won't see next year, is Avalanche. It actually made its mark throughout the first 2 quarters, but then kind of correlated to the Luna drop. The interest basically disappeared. I'm sure there's like more reasons for that, but also very likely this won't make it to the next year's report. Another quite interesting point here, Filecoin is number 5. So if you didn't pay attention to Filecoin, it's probably about time to start. So Filecoin actually didn't follow the same trajectory at all. There was even you know like a spike in usage in April and May. So looking at dApps, there's multiple categories of dApps that we took into account. There's definitely you know importance saying like the 5 billion paid in fees in 2022 in dApps is definitely heavily impacted by the NFT hype. So there's a whole bunch of like NFT marketplaces, NFT infrastructure involved, but then we get into what we would expect. It's like mostly DeFi, mostly DEXs, and some lending and borrowing. So again, I know this is not like easy to read, but the purpose is like for you to go into the report. So again, like similar trajectory to as the protocol fees. We started off. Yeah, I mean this is the wrong graph. Sorry, this is just the different dApps. But the actual fee graph is like very similar to this one. So the largest mark is on OpenSea side. It's like more than $1.5 billion paid in fees. This is not like you know the volume of OpenSea. This is the user paid fees on OpenSea, which already is huge. But that's the kind of the mark of the NFT hype, which definitely is fading or like was fading. And again, next year we'll be very likely looking at a different graph. The second one is Uniswap, then again, looks rare, back to the NFT hype. And then there's a very interesting project, Convex Finance, which, again, is one of those that didn't actually like lose anything during the bear market. In terms of where these fees originated, again, majority of these fees originated on Ethereum. It's the blue column, and then a whole bunch of other networks. In this case, there are also L2s considered here. So it's not only focused on L1s, but the whole bunch of the traction is happening on L2s already. So again, this is the graph, like basically showing you the trajectory of the entire bear market. But again, what you have to take into account is falling prices and the fees being denominated in the token exchange rate to US dollars at the time of origination. So when you look at, there's another mistake that I have to warn you about. It's not part of the report, but just in my slides. The table says average monthly users. This is actually average daily active users. So these are the addresses that are somehow like involved with the particle dApp on average, like every day of the month. So in terms of OpenSea, what you can see is like, again, beginning of the year still being in an NFT hype. The fees being close to $400 million. There's definitely like a good number of royalties that were paid as well. And what's also important to mention is that despite the NFT hype like disappearing in terms of the fees being paid, it's not like the users actually disappeared. So the user drop wasn't as significant. It's like 1/6 of the users that basically faded. Looks rare. Again, a similar graph in terms of the traction. In terms of the users, it's like fraction of it, but they definitely made it, again, a huge mark in the beginning of the year. Convex, here you can see like a very steady, again, I know the graph is falling, but it's like actually a very steady revenue and like interest in the protocol throughout the year. Lido, it's like one of the projects that actually has like increased demand, increased usage. Obviously, like thanks to more people getting into staking, like realizing this is a feasible way for them to participate. Aave, again, like similar graph to what you've seen before, but not as much in terms of the users. So Aave daily usage is actually quite significant, and it's I think it's actually with Uniswap, it's the most used app out there. So yeah, I know this was pretty boring, but it's kind of like meant to be. The purpose of the report is just like to provide you some baseline of like what you can look at and make the conclusions yourself. For me, the conclusions were there's definitely a huge, I guess, like gap between what we see in terms of the fees being paid on protocols and essentially to look at like the top 100 like coins on CoinGecko somewhere, because, well, it only made sense to consider the 5 that actually made up like the 97% at the point. So it just shows there is still a lot of like speculative value in the space. In my opinion, like this bear market is kind of one of the last tests, and in my opinion, the entire like crypto industry has passed it because the users didn't leave. Like what we've seen, I think, in like 2017, 18, and the drop right after. A whole bunch of the people left the ecosystem. It's not happening now, at least in terms of the users that use the stuff that was created. The NFT hype is paused, but it definitely had a huge mark. It's obviously a question what's going to be the next driving factor. It may resume, but I'm again guessing that next year we'll be looking at a very different graph. As it was mentioned, some dApps were growing, so things like Lido, Aave, or even Convex are like still functional, not impacted at all. You know, as someone coming into the space from more of like the Ethereum background, have to admit that things like Bitcoin and Binance Chain actually have decent traction and are actually bringing in users and have their own communities of users. And yeah, that's pretty much it. So the crypto natives didn't leave; they're still here. In my opinion, the demographic will just increase in numbers. So I think like now it's actually the right time to start considering crypto natives or like people in crypto to be like even like a buying force and start building dApps that are not necessarily like focused on like bringing more people into crypto, but already can target especially like the the crypto natives as someone we're building products for. So this was it. This is now our smart contract dev, and this is actually our internal slide that we use on all hands. And yeah, if you're interested in reading the report, you can follow us on Twitter at PondDAO, and you can also just go to cryptonative.pond.xyz to get the full report. So again, thank you for your attention.
That was great. All right, thanks a lot. So yeah, this kind of transparency is really important, I think, for our space. We can see what's going on, and it's really great to have people who do the work. So we're going to get started in about 3 minutes with Roman from Paladin. Going to talk about algorithmic governance. Be back in a couple. Okay, everybody, we're going to get started with the next speaker on our program is Roman, who's the CEO of Paladin. He's going to talk to you about algorithmic governance. Over to you.
Hello, everyone. Thank you for showing up so early on a Saturday morning. I hope you have a coffee, because it's going to be a bit intense. So you're going to need a bit of energy to follow all of this. So we're going to focus a lot on governance today. And the idea is how is algorithms, smart contracts in general, are helping supercharge what we're doing with governance. So I'm going to walk you through a bit of history, how governance used to be, how it still is, and kind of where it's going. Because honestly, it's scary, and it's good to have like at least a bit of light at the end of the tunnel to know where we're going. So just before that, it's always good to have a bit of context, because everything that someone says is biased, right? I work in governance. I used to be a banking lawyer before, so it's important for you to understand that I'm also a business grad, so and I work in DeFi, so it's going to be highly focused around corporate governance, because this is what I know. If I start talking a lot about democracies or even about community governance, I'm probably not going to say things that some of you are going to like if you are passionate about governance. To give you a bit of idea of Pardin, the project I co-founded, we built 3 dApps on Ethereum that are basically around vote markets and governance infrastructure. We have roughly 800 community members. We raised a few funds. We're actually a profitable project right now, which is always good in the current market, right? And we're managing over $10 million of voting rights. That figure is actually untrue. It's over 25 right now, but we're going fast, so yeah. Okay, moving on to governance. What is governance? I like to have a very simple definition of what governance is, which is the process of decision making. So why so simple? Because you can basically govern around everything, right? It's just about people getting together and deciding what the direction is going to be for a specific project. That's it. So there's many types of governance, but if you want to simplify it, you can think of it in 3 ways: hierarchical, collegial, and democratic. What does it mean? One person is deciding, or a very, very small group. One group of people is deciding, and everyone is deciding together. So we can see that depending on the different structures, for example, companies tend to be hierarchical, states tend to be democratic at the bottom and collegial at the top. And this is super important to understand because it changes the dynamic of how the decision-making process happens. We're going to see why it's actually very interesting, because if you look at corporate governance is actually quite new, because companies are only at 300 or 400 years in terms of entity. They're quite young. So just to give you an idea, we saw them actually almost 500 years. Yay. But they appeared in the 17th century when states realized they needed a lot of money to actually do the explorations. So they started building entities that would basically be able to attract speculation and enable them to finance all of these expeditions. It changed a lot with the United States, especially during the conquest of the West, because the state wasn't really present at the time, so corporations were ruling a lot some places during the conquest of the West. And it changed again during globalization, because companies went from very local to global. And that's actually very important in terms of to understand how big the current companies are and the way they're structured. So most companies are structured the same way they were 200, 300 years ago, but they actually change scale and they're as big as states now. So that's why you see like some CEOs that are extremely powerful, because they don't have the right organization compared to the actual size. So I just wanted to give you an idea of how it works in corporate governance, and now onto democracies. On the side of political governance, I think it's important to see how it works, specifically what's working and what's not working, because we are in times where there's a lot of unsatisfaction towards what's happening in political democracies. So what's the problem? And this is actually a picture that was taken last week in Paris. It's not that low. The problem that we see right now is that there's a lowering problem of participation. It's also true in corporate governance, and it's extremely true in crypto. There's also something that's simple, is that you're prone to sabotage, in the sense that people can very easily come in and try to break the system from internally, because it's a human system. It's just social engineering, right? And the second thing is that it's inconsistent. If you look at politics, elections happen every 4, 5, 6 years, 7 years, depending on the countries, and usually they change sides. Democrats, Republicans. Democrats, Republicans. So what happens? You don't have a correct line of direction over the course of decades, simply because politics keeps changing of sides. So what we're actually seeing is that there's a huge loss of trust in the model, slowly but surely. So we went from, for example, monarchies to republics, and now we're saying, hey, what's next? Because nothing is eternal. So what's coming next? And the truth is that it's a bit scary what's coming next, because what's coming next is actually algorithmic governance. So it's built on something that's called blockchains. I'm not going to teach everyone here what a blockchain is, but what's very, very interesting about a blockchain is simply the characteristic that you're switching part of the decision-making process by an algorithm. So you're saying, hey, out of all the decisions we need to take, part of it is going to be taken by a smart contract, and we won't have a choice because the program is going to enforce it. So what does this mean? It means that we can scale trustlessly. That's it. That's the huge value of blockchains. And that's why at the point, even when we had proof of work and it was consuming a lot of energy, people were ready to pay a lot. And people are still paying like $5, $10, $20, $30 just for a transaction in Ethereum. Why do they do this? Because it's a trustless system, and removing trust on certain decisions has a lot of value. If you think about finance, the number of banks that have fallen over the past month, and we're in Switzerland, right? I think no one here is educated, knows better than you guys about the topic. It's better if you know that the project is actually not going to default and go away with your money, right? So blockchain is about trust, paradoxically. It's the fact that you know exactly what's going to happen, because instead of trusting a human, which is unpredictable, you're trusting a contract, you're trusting an algorithm. So what's algorithmic governance? By now it should be, there's a slide that was skipped, it's okay. Algorithmic governance is doing the decision-making process, but replacing it with smart contracts or with algorithms in general. What does this mean? It means that in general, for example, you're going to rely on algorithms on your decision-making process. So for example, you're going to use oracles, and instead of having people saying, hey, I think we should do this because this is happening, we're just going to list, if X happens, we go in this direction. If Y happens, we're going to exit the funds from the project. If Z happens, we're going to give it back to users. And you don't have context, you don't have humans, it's just looking at values and executing. So it can be good, it can be bad. For example, if you look at the way we can do with lending, it means that the house will never fall, because theoretically it's always liquidating lenders before they're actually underwater. This is an example. Okay. For example, with Liquity. So again, Swiss project. I've tried to be thematic with the project, but it's interesting because we're on a governance talk, and we're actually talking about the most ungoverned project. Is it because it doesn't have governance? Well, Liquity actually has governance in the sense that there are decisions that are taken by the project, but they're just taken by the smart contract, not by the people. And this is what's interesting. It means that it's a project that is entirely run by its lines of codes. So all of the decision making, what happens, when do our users liquidated, or how do you pay them back, all of this is done by the smart contracts and by incentives. And this is what is really interesting, is that even when there's no governance, at some point, if there's no arbitrageurs, the system doesn't work. So in a sense, it's extremely hard to have a system that's going to interact with humans if there's no actual humans that are powering the system at some point. So instead of thinking about automating everything, we're ChatGPT era, right? Humans are going to be useless, ChatGPT is going to do everything. That's not how it works. Each time we have a new invention, what happens is that it's just a tool that people are going to use. So you're going to have a human that's going to be above, and that's going to operate it one way or another. And that's what you have with Liquity. You have users that are opening troves, and then arbitrators that are helping the peg be restored. Nothing can be entirely programmatic. And this is why, for example, I'm a big fan of Curve. Disclosure, we build a lot on top of Curve. Again, also a Swiss project, apparently. And the idea of what's happening with Curve, and that's very interesting, is that they have a programmatic system of emissions and of tokenomics. But what they do is they entirely rely on incentives for people to participate. And this is what is really interesting with algorithmic governance. It's just not about replacing some part of the of the decision-making process with smart contracts. It's also about building the right incentives for people to come in and interact with the contracts at a specific time. So what this graph is, it's the design of the size of the gauge in Curve. So what Curve does is that they control the emissions, their emissions, the way they distribute their token, through a distribution that's done on a vote every week. And this graph, the resolution isn't that great, I'm sorry guys, but it's just the different actors and how much of the share of the gauge they're having. And what's really interesting is that you can actually see the different wars, in a sense, happening, where people are trying to take control and then disappearing. For example, which one? The purple one that you think that's really big and that stops at one time, it's Terra. And there's a few others. When you read at this chart, you can actually see the theory and the history of governance. And what's interesting is that at some point, the project stops paying incentives or disappears, people stop voting for it. And that's what's really interesting, is that we are going to have to learn to read coordinations of machines and how humans interact with them. And that's the whole point of tokenomics. So that's something that's extremely important to understand, is that the way we're seeing algorithmic governance go, it's going to have positive and negative impacts on the way we interact together. And we're talking about DeFi today, but you have to understand that the future of states, the future of companies, the future of associations, they're all going to have algorithms at some point that are embedded into it. So what's the advantage of using such type of governance? First one is that there's no corruption possible. You can't go to a machine and offer him coffee or like offer him a restaurant. It does not work. They do just a mission and they execute it. The second thing is that theoretically, and if there are devs here, they're going to laugh, it's consistent. So when it works, it is consistent. And that's the important part, is that you can rely on it much more than a human being that sometimes is not going to wake up, sometimes is going to be tired, sometimes he's not going to be in the right state of mind to actually do what he's supposed to do. So he's not going to execute as consistently. And the last thing, which is true for every technology, is that it's more granular in the sense that you can be much more specific about what you want it to do. So for example, you can have a smart contract that's going to do one very specific task, and that's it. And it's more scalable. So, in a sense, a bigger problem that we've had in governance systems up until now is that we've had trouble in basically scaling them. It's very hard for us to have very large-scale system for governance, simply because it's hard to coordinate a lot of people at the same time. Algorithmic governance is the solution to this. However, and that's the big problem with this system, is that it can't adapt to context. So I used to be a lawyer. The beautiful thing about law is that it adapts to concept. You have rules, but the rule bends depending on the context. You're like, hey, yeah, but maybe this person wasn't wrong in this specific context. It's just we weren't aware that this could happen this way. And law can bend depending on this. Smart contracts, they don't. Like if there's an oracle that doesn't take the right value and suddenly everyone gets liquidated, you're done. You lost all your money. This does not happen in the traditional world right now. So this is the problem with algorithmic governance, is that it can actually be played in a way. This is also because of the fact that there's no human interaction. So we're basically building a machine system, and the best way a machine system can work is with another machine. So we have to understand that it's very good to build systems that are going to scale just between machines talking to each other. But if you have a human at the end, they're always going to have some pain points, and it's always going to be a problem. So you need to find the right balance between doing the algorithm and having human decision making. It's probably going to be half and half. And the last thing, I wrote predictable. So you might think, hey, consistent, predictable, that's kind of the same thing. Why is it in both sides? Well, if you know how a system is going to behave each time you interact with it, you can actually game it. So there's no corruption, but there's gamification that's possible. And that's actually another point, is that it's dangerous. So that's why you have all these debates, for example, when people are hacking projects, they're like, hey, I didn't steal the money. I used the code and did what was intended. That's a debatable explanation. And some people went to jail for this. So what can we expect from algorithmic governance and the way it's going to reinvent? I'm not going to tell you it's going to change everything. It is. But it's not going to change everything over our lifetimes. So we shouldn't worry about that. We should just worry about the ways it's going to change over the course of what we're doing right now. Why? Because all of this is basically going to change the way humans interact with each other over the next centuries. So your kids, I mean, for some of you that have tried ChatGPT, you're like, wow, what I've done over the past 20 years is useless. No, it's not true. But a lot of it is going to get basically change the way people interact with each other, the way people work. It's just going to change. So what happens here? First, we're going to automate a lot of intermediaries. That was the promise of crypto, right? But it's becoming clearer and clearer this is happening. So we're going to remove some banks, we're going to remove some hedge funds, and instead, it's just going to be smart contracts doing this. Two, we're going to reduce a lot of the quantity of number of people and the time dedicated to governance. Everything that's burdensome is going to be managed by algorithms, and everything that's important, everything that needs context is going to be managed by humans. So for example, you're probably always going to have a human judge. But instead, you're probably going to have someone that's going to be able to find all of the relative items and analyze everything that's actually happened, find the data automatically. So you're going to have automated oracles in the sense, but it's going to be limited on the real decision-making side that has impacts on humans. So we're basically lowering the quantity of decisions that need to be taken, but raising the quantity, the quality of the ones that need to be taken. And the last one, which is very important, we're lowering the human complexity. So you won't have 15 persons you have to talk to, huge rule books. It's going to be much easier, but it's going to be much more technical. It's probably going to be IT. So if you don't know how to code, please learn how to code, because this is going to be a very important one. Yeah, that was the slide that was supposed to be at the beginning. By the way, some of these slides were done with Midjourney. Some of these slides were done by my designer. Some of these slides were done by myself. If you want the version at the end, you can have a look and try to find which one were which. So this is the important part. We've talked a lot about choosing between humans, between machines, algorithms. One important part is that we've been talking a lot about AGI lately. I think it's possible to have simply protocols that will be governed by this kind of AGIs. They will exist. You're going to have people who are going to try to bring them forward. And it's important to understand that these are going to be like subsets and parts of our society that are going to start appearing very quickly. So self-governed entities. And my take is that they're going to be pretty dangerous, especially at the beginning, simply because they will not have the capacity to enter enough context to be able to do the right decisions. So what's very interesting is that you will see no governance system that actually lasts over 500 years. Every civilization collapses, right? Because they evolve, and at some point they reach something that doesn't work. And it's going to be exactly the same thing with AGI. Simply because nothing is omniscient, nothing goes always in the right direction, so at some point they collapse. And why we should be careful, it's simply about putting them in the right place. It's a machine in the end. It only has the power that you give them. So, conclusion, I think that's really important. We're all going to have to live with the fact that part of governance is slowly going to be replaced by algorithms. And I think it's really important that all of you appreciate what's happening and how you should prepare to it. So first of all, we're going to need to redefine a lot of the governance systems we have been doing up until now. And we're simply going to have to think about the scope of what we have been building, in what direction are we going, and how do we basically work less on this and focus on what actually matters, which are the important decisions. The second, I've mentioned it, learn to code. Learn to read the code, and if you don't, read the docs. It's when you go into a crypto project, a normal project always has documentation. Please go and read it so you know what's actually supposed to happen. Because if you don't, you will be surprised by the interactions. And the third thing is important, take the red pill. Simply accept that we're moving away from entire human-to-human interaction. It doesn't mean that we have to entirely stop. It just means that we already started. In a sense, most of human interactions are actually happening through machines today. Most of the compliments you're giving are actually from Instagram, when you're liking a photo. Much of the information you're gathering is not through conversation, but through reading articles, through watching videos. So we've already taken a step into this. The question is, how much of a step do we want to take into this? And personally, that's one of the reasons why I like crypto so much. It's that it's not about submitting to what's happening. It's about choosing the system you want to get into. And so if you don't want to get into the system that most of the people are getting into today, you can just create your own, fork it. That's it. Thank you very much. And if you have questions... Yeah, we have fun.
So we actually have time for some questions if anybody has something they want to talk to Roman about.
Hi. I was interested in knowing... So, not really, ça n'a pas vraiment à voir avec le talk, but in the governance process, how important do you think it is for protocols to separate what gets to be chosen, what gets to be voted on by governance versus what the core team and what they get to choose on, well, what they get to actually vote on themselves, and not present to bring up to a vote for the governance process?
So that's a very up-to-date topic, especially for us. But I think it depends on the maturity of the project. Early on, it's extremely hard to be simply very decentralized because you haven't distributed enough to be able to do this. The idea is to let go as you go. So I think a big problem in the projects we have seen, especially right now, is that they've scaled to a size where they're expected to have the resilience, the distribution, and the organization of a large-scale company, or even sometimes a small state. But in the end, it's just 3 people in a basement. So it kind of creates a dichotomy between both. I would say today, you need a technical team that's going to drive the project, and then everything else around resource management, etc., can actually be governed by the company. But again, it's like a slider. In a sense, the more you're pushing towards decentralization, the less the core team actually has to be there. And this is actually why you have to expect the large stakeholders to actually get away simply from these projects. Right now, we're talking about token voting because it's the biggest system in crypto. But we're probably going to have new systems. But as long as you have token voting, when you have a project that fundraised, a core team that took a large allocation at the beginning, if you want the project to really become decentralized, you're going to have to expect them to slowly sell and get away from the project. In a sense, a project builds for 5 years, and at some point, the core team has like faded away. They're still building or still doing something around the project. They're just not central anymore.
For example, I mean, we see this with Maker, for example. What do you think? How do you think that? Oh yeah, sorry. With Maker, for example, the fact that they've decentralized the project so much has brought up some problems in the governance process. How important do you think, even on the long term, I mean, even if a protocol looks to decentralize the entire governance, how important do you think it is still for the team to have some, like the initial core team with the initial vision of the project, to still have some input, some like kind of executive input on the direction of the project for certain aspects?
It again depends on the way the project has scaled and how functional it is. Because if you look at Maker, today it's just one of the co-founders that's basically coming back and re-centralizing the project to redefine the vision and basically allow it to go to another scale, taking it up a notch, right? But if you're a brick project that is basically just accomplishing its mission of public goods, you don't really need to come back and re-centralize, right? You can just have the project organically grow. And that's the complexity, but the beauty of these projects is that we expect them to go in one direction, but if you want it to go in the one direction, you need a core team, or at least a decision-making body that's going to push it in this direction and be consistent with it. On the opposite side, if you want to be fully decentralized, you have to expect chaos. You have to expect something where it's going to go in all of the directions, and 99% of the time it's going to fail, and in one direction it might succeed. So it basically depends which type of projects you want to build and how ambitious you want. Not everyone wants to build $1 billion project. Some people just have one key mission and they just want to execute it well.
Okay, so I think we have time for one more question if anybody has one. Otherwise, I would have one, if you don't mind. Yeah. So I was just curious, you talked about how governance systems change over time and no governance system is eternal. So if we're in a period of transition right now, do you foresee in the future a scenario where we have, for large societal infrastructures and systems, purely algorithmic governance, or are we always going to be hybrid?
No, I think it's going to happen, and I hope it's going to happen. If you look at, for example, this is very up-to-date in France, everything that's about retirement, right? This could actually be automated in the sense that you would actually be able to be an opt-in or opt-out system. You come in, you pay every month, you get points, and at some point where you stop, you just get an allocation that's just paying you back for the points you got. I'm just giving us an example. But in a sense, we already have some things that are pretty algorithmic because we're just following some specific type of rules. It's just that we haven't really expressed them through code entirely. And that's what we're going to see. It's probably going to be opt-in, opt-out system where people just come in. It's basically network states.
One more, real quick. All right, the last one, keep it quick.
How many people are actually going to be able to read the code?
That's a good question. So I would say a growing number of people, because a lot of crypto natives are doing it today. Also remember that a lot of the younger ones actually learn coding at school. And the third thing is that today you can just use, like for example, something like ChatGPT and say, explain to me the code. So basically anyone can read the documentation, right? But if you can have software that actually creates the documentation,
So to be a lawyer, you went to school for years to become a lawyer, to understand how law works. And a very large proportion of the population didn't, and a substantial proportion of the population probably couldn't. And I think that's going to be the same problem with, you know, what do we do? The point about using systems that can explain the code, that's actually a really good one. That's a valuable thing to be able to have that we haven't had so much in the past. But it is an interesting question of, do people have time to understand what you're asking them to do?
So that's the dramatic, and maybe I'm going to end with this and we can finish outside just for you guys not to be too late, but that's the dramatic fact about crypto and tech in general, is that we're erring towards complexity and inequality. Before it used to be where you were born geographically, in which family you were born, and the more we're going into the future, the more it's going to be around, hey, are you able to read code, understand what's actually happening? And you're seeing it today. I mean, there's a lot of 20-something people that have more money than 50-something people just because they play their cards correctly in DeFi. Or just they got lucky, right? So we're seeing something where inequality is moving to tech literacy. And this is extremely scary because if you were born in a place where you don't have internet or not, you don't have good access, you didn't learn to code, you're done. It's crazy.
Thanks a lot. That was excellent.
Thank you.
Okay, we're going to move right on to the next speaker. We're going to turn our attention now to programming. And Miao's here from the CTO of Superfluid, and he's going to talk about using functional programming techniques with Solidity. Miao? Okay.
All right. Oh, sorry. Should I be here or?
She wants in the middle.
Yeah. Yeah, it's, I can take a look at this. Yeah. Yeah. Put it here instead. Okay, yeah, thanks for people coming here for the rather technical talk about pure functional solidity for fun and profit. I just wonder, like, how many people are actually familiar with the idea of functional programming, just so that I know. All right, great. So let's just get going. So the goal of this talk is to demonstrate the possibility of limited functional programming in Solidity. And the second is use a new paradigm to build a simple super token step by step. So it's going to be involved, and I'll try to go right speed, but it's a bit short time. The third one is examples of using Certora to formally verify the code. Right? I don't say it's complete down, but just exploring the possibilities. And last, if you're not familiar with the functional programming yet, is to make you interested in functional programming in general. Right, so, okay, so let's start with today's task or idea is, let's reimagine what is a token, right? So let's have a new mental model of what is a token. Let's call it super token for now, right? So token is like a bank containing a collection of accounts, right? That's how we know about even ERC20 tokens, right? Each account has an owner, representing the owner's wallet with a collection of, let's give an abstract name, monetary units, not to be confused with currency units. We're talking about just abstract units, right? So, and these monetary units provides a balance, right? And a set of payment primitives, right? So let's have this mental model and move on and see what's it about, right? So what are payment primitives, right? Let's give 4 of them, and they have 2 dimensions. One is one-to-one transfer, one is instant versus constant flow, right? So we're all familiar with one-to-one instant. That's ERC20 transfer, right? That's just one thing in that 2 by 2 boxes. The other is one-to-n instant to all the accounts. There are a lot of ad hoc projects that are doing that, but let's say, can we generalize as sort of a payment primitive? So we want to do one-to-n instant transfer. The other is one-to-one constant flow of money, right? Often known as money streaming by people, right? And the last is the one-to-n constant flow. How about I distribute to any number of people as flow of money, right? So that's so-called a generalized payment flow, generalized payment primitives, right? Okay. Furthermore, what come with this generalized payment primitives and the new mental model, right? So it's also frictionless. What does it mean? So it's real time. So it's a model that continues in time, right? So it's, in effect, because blockchain move per block, so actually it is move per block, but it's modeled continuous in time. So it's real time, true real time, right? The other is composable, right? So it can be chained with other payment primitives. So the moment you receive the money is the moment you can use the money, right? So it's frictionless in that sense. You don't need to wait for the money accumulate and you transfer as a batch later, right? So it's using at the same time you receive, right? So programmability also, right? So there's two programmability. One is on-chain mechanism, right? So let's say include a callback. So when you receive the money, you act on it. One of the examples is ERC 777. But you can generalize it. If you receive a flow of money, then you trigger a callback, it does something. That's kind of on-chain mechanism. There are certain things you cannot do on-chain, such as reacting on time, right? You can't do that on EVM yet, right? So when the certain time hits, you do something, for example, right? So it's not doable. So you have to provide off-chain incentive when in that kind of cases, right? So a little bit more thoughts about Super Token before we move on actually about the main topic, which is functional programming, is monetary units you can think of as coins, cards, or notes in your wallets, right? So optionally, you can think of like UTXO-based system or on-chain representation of account could be kind of complete bypass. It's no longer wallet, but just a bunch of notes. You can do that in your UI instead. All right. Okay, let's now have this mental model in mind and let's build it using Solidity, right? So, but we'll not do all the features we talked about so far. We'll talk about only creating those payment primitives. Also for fun, disclaimer, this is not for production, right? So just for fun, right? So first of all, let's define some types, right? So there's something called custom types already in Solidity. I don't know if you start to use it or not, right? So this is what you can use for wrapping numerical types. And from 8.19, there is something called operator overloading also. So you can actually make it more convenient to use by using that. So let's see an example, right? So first of all, let's define something called time. In this case, the time is int32 unsigned, and you define two functions, pure functions for add and subtraction. And the last line is the 8.19 new feature, right? You can do operator overloading where you say, okay, you say the plus operator is using this function and the minus, the subtraction operator is using this function. So this is the new syntax available from 8.19. So with this, you can then actually use the custom types in a more ergonomic way, right? It's just syntax sugar, but it's rather convenient, right? Let's define more types, right? So you need to have value. Unlike the ERC20 value, this is assigned also, right? So there's a positive and negative, so it's int256. Similarly, you define the add and sub, and you apply the operator overloading also, right? So now there's flow rate. In this case, let's say it's 128 bits instead, because otherwise, it's gonna overflow. There's only 256 otherwise, right? So very similar code than previous one. Let's move on quickly. Unit. We'll talk about what is unit later. It's really about distribution. Think of the dividends payments. You need to have a share number. In traditional, like how many shares you have, Microsoft share, Twilio share, whichever, and those are measured by something called unit. So this is the type gonna be handy later. All right, so however, Solidity doesn't have a operator overloading when you have two types that are different. So you kind of have to go back to the old way using a library. Say if you want to multiply the flow rate by time, you put that as a library function, and then you use kind of keyword using this library for the flow rate globally, right? This way you can then have a operator by name of a .mul, right? So multiplication. So this is you can't do mixed type, so unfortunately you have to do this. All right. So next step, let's define what is actually the thing we're talking about here, right? So we need some sort of a data type for doing this very specific magical token, right? So there are three things. There's a time for that data structure. It's a very abstract name. It's called a basic particle. We will see later why. And there's value, and there's a flow rate. With three fields, you can count. Okay, before I go further, right? So there's something in the Solidity about pure, functional programming is that it is not really pure function. Why? Because it's similar to JavaScript or some of the language that when you have an input of the memory data type, storage indicator, you can actually modify the input. Right, so this is not really a pure function in that sense, if you know what is actually the pure function. You can modify the input, which is kind of bad, right? So for the functional programming perspective. So what you really need to do is do a clone. So whatever input you receive, you clone it, so you make sure that you don't modify the input. So we keep that pattern throughout the code, right? So make it purer. All right, I need to check the time, so I'm gonna move on fairly quickly. So now we have a small data type. Now we need to calculate the the balance from the data type, right? So it's very straightforward. It's one-liner. Say, okay, flow rate multiplied by the delta of the time, right? Then you plus something called a settled value. Then effectively you have a calculation of what's the balance of that data structure, right? So it's called a RTB, right? A real-time balance. Another very abstract function called settle is because it's a very important kind of construct throughout the code in order to make sure that when you do operation between two data structure, they are synchronized with the same data structure, same time, right? You settle at the same time. Otherwise, they're not compatible, let's say, or another way to put it. If they're not settled at the same time, you cannot do operation on top of it. So let's call it settle, right? As you can see, the first operator is always .clone, so you don't modify the input data, or talking about functional programming, you always clone it. In Solidity, unfortunately, you have to do that, so that makes a little bit boilerplate, but not too much, right? You clone the data, you calculate the real-time balance, is the second line of the function, calculate the balance, settle it, and put the time in the third field, right? So, okay, now go to the third step, right? One of the things about a functional programming is that you define a bunch of functions, but how do you know if those functions are correct, right? So you do now need to define some laws for it, right? So laws, what are the laws, right? So laws like mathematical laws, right? So let's define something called a monoid. If you're in a functional program, you probably know what I'm talking about here, but it's actually a very simple concept. So it's the data structure we talked about there has additional operator, let's call it X, or has some name called append, and satisfies certain laws. What are laws? It's very simple, right? So there's empty elements multiplied by any number, any data is equal to that data. It's like 0 plus X equal to X, or 1 multiplied by X equal to X. You can do different order, left or right, so you can have left and right. So now we have a foundry-based property-based testing, right? So you have any random input, and you test if the law satisfies with any order you have, right? So multiply by append from the left or append from the right, you get the same equality, right? So that's kind of foundry-based testing, right? So the fuzzing to test this law. There's other way to test, but this is one convenient way. All right, another is associativity, right? So you A multiplied by B multiplied by C equal to A multiplied by B multiplied by C with the different brackets locations. And in the foundry is also very clear one-liner, right? So you check if it gives the same data, you do kind of with different brackets applied to the data structure, right? So it's very easy to test, right? So that's a common mathematical property for the data, for a lot of data, especially for data wants to append to each other. But the data we just defined also has its own laws, right? Because we were talking about some domain-specific stuff. Something is it's called, there's a settle function, right? So if you settle twice, they should give the same result, right? So it's kind of idempotence, let's call it, right? So actually, the fun fact, I asked ChatGPT, can ChatGPT generate the function if I just give the function name? Actually, generate pretty okay. I mean, it doesn't work fully, but it does understand the word and it understand what it means, right? So because in principle, it's a second formula is just settle twice with the same time is equal to settle only one time, right? So that's basically what about. This is not very interesting yet. The next interesting one is what actually about the constant flow of money, right? So you actually then test the real-time balance is always the same no matter how you settle it, right? You have 3 timestamps here now in the Foundry-based testing. You have T1, T2, T3, and you settle with a different order. Then you calculate the balance at the same time. They always equal, right? This way you can make sure that the function you define actually makes sense according to this law. Right, so Foundry, again, provides a very nice facility for testing this. It's a very concise test. You just test the property, and you put random inputs, and it will give you 1,000 data points, and it all works. Then you're happy. Right, so, all right, I'm going to speed run now. The number 4 step. We talked about 1 to n also, right? How do we model the 1 to n? Now we need a new data type, right? Let's call it the pool of money. Right? Let's look at the pie chart. Imagine, okay, I need a data structure can represent the ownership of the pool of money by different owners. So let's say that each pool has members, and each member owes some amount of units, and anyone can distribute money through this pool of money to its members, and these distributions can be kind of instant or as flows, and members' share of the distribution are proportional to kind of a number of units relative to others, right? So this is a mental model of a data structure. Let's just define it, okay. We have this kind of basic data structure we defined a few slides ago. Now we just wrap it into on the left side, 2 different new data structure, right? So you say the pool has total units, and you contain a wrapped information. That wrapped particle is actually measured per unit. And then you have each member. Each member say how many units I own, and where is the settled number I have there, and what's my synchronized position of that. Now you have 2 data structure, and essentially done. You have now a 1 to n. How? Right. So again, you need to define this function that we defined for the basic data structure. Now we define what's a real-time balance for this function. Right. It's also very, very concise. This is a kind of hallmark of functional programming. Right. So you just define pure functions, define data structure, define really, really small functions, and you gradually build things up, and you will get what you want, right? So as you can see here, the real-time balance function for that pool is essentially a few lines, right? You say, oh, I need to see the difference between the wrapped one and the synced one. You multiply by the number of units this member has, and you plus this so-called settled value. Done. How do you come up with this formula? It takes a little bit of time, but once you get it, it's short and it works. But how do you know it works? Right. There's something called a settle also, but let's move on. How do you know it works? Remember, we talked about laws, right? So in order to know if it works, you basically test with the same law we talked about there to see if this new function you created satisfy those laws. And the good news is they satisfy, right? So now you know you created something new, and they satisfy the same law, and they work, right? That's the good news about that's kind of why you should do functional programming, because then you just create data, create function, test with laws. And it's step by step and build things up. And yeah, I'm hand waving here, right? Just trust me, it worked. Right, so now, not finished yet. Now we have data structure. Now we need to go to something finally, right? So we're building the token, right? We're not there yet. Step 5. 5 minutes. All right. So we need a shift and flow, right? So we need to shift the value from 2 parties, from left to right, and we need flow money from left to right, right? So that's called 2 primitives. And in Solidity, I have to do twice this for different data structure. On the left side is 2 basic particle. On the right side is, on the right side you have a basic particle is A, and you have a pool which is B. And as you can see, they are very, very similar functions looking, right? So the body of the function is very, very similar, almost identical, right? It's not a coincidence. Let's see another example. All right, then you have a shift flow. right? They are almost the same. They are just different input types, A and B. They are just slightly different type signature. But the structure of the function is almost identical, right? So this is something that in Solidity they are going to be introducing, as far as I heard from last year. They're going to introduce something called generic programming. So that means when Solidity have generic programming, I don't have to create the same function twice because they are essentially the same. What we need is generic programming so that I can write one function and they can work for both different types because you can just duct tape it, right? Duct type it. Like in JavaScript, you don't care about the type of it. You just say, oh, if you're a function, it just works, right? So we need a similar thing kind of in Solidity, right? Then we don't need to create the function twice, right? Okay, so now we have laws for the new function, right? So in Solidity, I want to show you one trick in Foundry, rather. Solidity and Foundry. So I have a generator function. So it takes two functions as a pointer as an input, and I can generate tests based on the operation 1 and operation 2. They are abstract function. Sorry, they are function pointers, and this is kind of my template to generate more tests. What do I do? Right, I use that generator function to create 4 different set of test cases. I say it's a shifting, flow, shift, flow. I have now all the combinations with the generator function, right? So this is something that you could also do in Solidity with function pointers, and then you generate a bunch of the tests using that, right? So, all right, now where are we now? We can do shift, we can do flow, and if you shift from 2 basic data structure, you get a transfer, ERC20 transfer, and you get a one-to-one flow. And if you do the shift for the basic data structure and the pool, then you get 1-to-n, both instant one and both stream one, right? So as you can see, it's using functional programming to build stuff from bottom to up. You have basic data structure, you have a complex data structure, but same function, and you get you get all the function you need. All right, so you get a functionality you need, right? So, okay, now what, right? So we have a library, pure function library, does a lot of things, but also at the same time nothing, because it can't really change storage, can't do anything. So like, what do we do now, right? So let's call it the infamous M word. If you know function programming, that's kind of the most dreaded word because no one can explain it, right? So but let's focus what do we need. We need a reusable code that use the library we just created to build these tokens, right? So I'm gonna fast track. Sorry if I kind of have to jump a little bit, right? So let's go straight here, right? So what we can do is we create abstract function, has a function that say I want to flow. I call these pure functions, and then I want to actually modify the storage, right? That means I have to define a virtual function and then do all the tricks, right? So this how you create a kind of reusable code for using those functional pure functions. And the implementation in the token. So this is now the final code. In the token.flow, you will see, okay, I use the only important part is almost in the end, like underscore do flow, and then you have it. All right, so there's another trick. Unfortunately, I can't show you here, but just see, this is actually Solidity code instead of the last one, right? You have the dot set, sorry, this one. The last part is, this almost exotic code is like you can do shift and dot flow. It's like a chain of function calls, right? So it's a re-implement the same token flow with a slightly different ergonomics, how you do it, right? So what do we have achieved? So we now have a Solidity pure function library for implementing the token. Now we have 2 variants of the interface that for reusing that code, and right, why it matters. I'm going to jump real quick because people are waiting. And so what is function programming? It's really about implement as much code as possible using data definitions, equations, and logical formulas. And to make code actually useful, we need to have the kind of computation strategies stuff, right? So why it matters, I suggest you look at this paper called Why Functional Program Matters. It's really, really old paper. It's 10-pager and it tells you why it really matters, right? So the keywords is that it's for better debugging, reusability, and less maintenance costs, right? The main point I want to actually bring out is that with this with this kind of way of building stuff, you can actually make the form verification really easy, right? Then you can have the, in the Certora, you can have this define the rule. You say, this property we were using Foundry to prove, it always works, not only with 1,000 data samples, but also mathematically always works. There's another magic from Certora is that it can inductively prove that something always works throughout the state of the program, right? Okay, so I'm rushing a lot here, but thank you for listening. Yeah.
Sorry to have to rush you. So we don't have time for questions. We're just going to set up for the next panel. But I've been told you're here today and all tomorrow, right? So if anybody has any questions, just catch me out in the hall. All right, so we're going to set up now for a panel on Ethereum object format, and we'll take about a minute for that and keep going.
All right.
Very good?
Yeah, after you finish, you just pass the mic to the moderator.
Oh, okay. All right, everybody. Moving on to the next panel. This will be my easiest introduction of the day because I'm going to hand over the mic to Stefan and he'll do the rest. There you go.
Thank you very much, man. I think we all feel great to be here, and thank you all for listening, and we'll go straight to the point. Today with us are Miao from Superfluid, Mario from Ethereum Foundation, George from Consensus, Anton from Chain Security, and Nebojša and myself are from Tenderly. Guys, if you want to say like 1 or 2 short sentences about yourselves, introduce yourselves, and we'll get straight to the point.
Oh, okay. Yeah, I was building SuperToken, yes. Yeah, so I'm from Superfluid. We've been building the magical token called SuperToken for quite a while, and I don't know enough about EOF, but I hope I can provide some also my new thoughts about it also for this talk. Thank you.
Hey everyone, I'm Mario. I work with EF, specifically protocol support team, which is a team which helps to coordinate the work around core devs and also to test ship hard forks. So I'm more of a technical part of this team where I dive into some research around the current research, and I've been running the protocol fellowship, so I'm helping to onboard new core developers. Yeah.
Hi everyone, my name is George. I'm from Consensus Diligence, and I mostly do smart contract security audits, some tooling, and some ZKP research here and there nowadays.
Nice. Hey everyone, I'm Nebojša, one of the co-founders in Tenderly. We are building a developer platform that helps builders be more productive and efficient when they're building and testing smart contracts. Mainly, I'm working on our custom virtual machine that is capable of extracting more data during the runtime.
Hello, my name is Anton. I'm from Chain Security. We are also doing audits for Ethereum smart contracts. And also internally, we're doing different tools and keeping a close eye on all the changes in the bytecode and EOF including. That affects our security tooling a lot, I would say. And yeah.
Thanks, guys. So, for the intro, Nebojša will really shortly go through like the what Ethereum object format is, but we wouldn't want to focus too much on the technical aspects of it today. We would like to focus on what kind of impact EOF will have in the space and on developers. So, Nebusha, take it away.
Right, I'm going to do just the short intro, and anybody from the panel can also chime in if they have something to add. So basically, Ethereum object format introduces this new way of how smart contracts bytecode should look like. By that, I mean it restricts how exactly the sections of the bytecode need to behave and look like. And this has a lot of implications. The first one is that on the runtime, we no longer need to do and perform some checks, which can, in essence, help us with the scalability of the whole Ethereum. But as a consequence, we need to do some checks on the deployment time. Right. Yeah, that's basically it. I mean, if anybody has something to add?
I would mention just one important thing, that like the whole name is wrong here. Like I was telling the organizers, and I think it was changed in the schedule, but it's still here. It's not Ethereum object format, it's EVM object format. Okay, so we are talking about the Ethereum virtual machine, the heart of Ethereum, I want to say the brain, the execution environment, which right now it has to work with just like a blob, basically, just like bunch of bytecode. When you are deploying a contract, it doesn't have any structure. It's just bunch of code, and the EVM goes code by code, bytecode by bytecode. First, it verifies whether it's correct, whether it can even execute it, whether it exists, whether it has enough of gas, whether it doesn't break any computation, and this can be externalized to do it at the moment of deployment, which is great, not just because we save the time at execution, but also we will prevent having just a mess on the chain, which is unexecutable. Yeah, just to mention, right? Like, so now instead of just like random pieces of code, it will be structured like we have a header. This is the code. This is the data. And when the EVM comes, it can tell like, okay, the header explains the version. That's one important thing. That will be the versioning. And this is the code that I'm looking for, and I need to verify this, right?
Right. It's good that you mentioned versioning, because that's basically where we wanted to start. So, like, what will be the implications of versioning? I mean, how do you see that going down and propagating through the levels all the way to the depths or whatever you're building?
Should I talk like it?
I can choose who talks, but George looks like he wants to say something.
Go ahead.
So
yeah, no, I think since we're talking a little bit less technically, more like narrative almost at this point. First of all, I think one thing I want to say is that this is the first big change to the EVM itself, especially after all of these upgrades to the protocol. Now it's finally we're putting the spotlight on like one of the main things probably about this whole Ethereum ecosystem. So that's first big change. And then the second, that within the change itself, we have the notion of versioning. So it's kind of an interesting thing how now we're going to be looking at even more explicitly looking into upgrading very core parts that are not even necessarily backwards compatible parts of the protocol as we're going to be upgrading them. And then on top of that, we're going to even have an explicit versioning part to it, meaning that we are explicitly looking to have several different potentially not compatible versions of code kind of living on Ethereum, and we might have, correct me if I'm wrong, some contracts that are going to be able to speak to each other, in future potentially not being able to speak with each other. Let's say if we have EOF version 13, right, it might not be able to be speaking to version 6. And then we were speaking in the green room right before this, how it might be interesting that this might spill out to different layer 2s and how they might have their own dialects of the EOFs running there in different containers or code containers that might be a little bit slightly different from the mainnet and might be compatible, but maybe one way, not the other way. And just overall, kind of, I think it's interesting how this isn't just a major upgrade of the EVM itself, but in itself, within the upgrade, we have a notion of that it's going to be changing more and more.
I also wanted to maybe like add something that Mario mentioned before. Like that's basically this could be chunk of an executable code, right? It's actually one of the cool things is that there are going to be introduced also data sections, right?
Yep.
For like bytecode is not only executable code. For many things, the parts of a bytecode contain actual data because there is like code copy of codes and so on that can be used for immutables, right? The factory contracts needs to store the bytecode of the contracts they need to be deploying also somehow, right? And like alternative is doing it as storage, but it's super expensive and there is no like a way to load large chunks of storage in one go. You only can access it word by word. So it's like for many places, the bytecode is used as a kind of data storage, right? Yeah. And for me, it's like, this is honestly a really nice feature because now you can clearly distinguish between what's executable and what is used as like data, right?
But thank you for mentioning like that's one of the important things to mention that like it's the biggest upgrade to EVM in a while. Like I mean, like the most significant upgrade we had was push 0 this week. But, yeah, like the EVM today looks almost the same like 3 years ago. And the folks from the Ypsilon team, Axik, Pavel, Andrei, has been working on EVM upgrades since like the EVASM era, and this is something which they put a lot of work into. So I'm hoping that it's going to like these changes in the EVM are very slow. It's also one thing. So we mentioned the versioning. Yeah, I wanted to react to that because I mean, it's like we'll basically now have different, I want to say versions of EVM, but it's not like fully what people might imagine because there is you cannot the changes that can be done in each version are still limited. It's more like it's the new version can add new features. It cannot change things, right? So we can see that the contract or the developer can actually see that he's using this version and he's compatible with the new features, let's say. So it might be even easier to add more features, but also it's like maybe more standardized approach to have the various EVMs around the ecosystem, especially for example layer 2s, right? Because I think Arbitrum already announced it, but the idea was already like a year back at least. Like we could have kind of beta version. Don't quote me on this, but like another like version of EVM where we improved something, and this is running on layer 2s. They tested, and maybe it get boosted up to mainnet at one point. But again, like this breaks the equivalency, right? Which some people are trying to reach, and generally, like there is a lot of issues with EOF as well. Like it's not all fairy tales. Like it's pretty a big problem to solve. That's why it got pushed from Shanghai to maybe Cancun, maybe Prague, one thing is that now we are going to basically break the EVM for all of the forks, which is like half of the crypto coins out there.
So I'd like to add that, right? So it's not just a rainbow and sunshine, and there might be also the fragmentation. And now it's not only technically a new arena for us to innovate, but also probably politically a new arena for fragmentation, right? So there are political actors like Q-Switch for smart contract. What if someone decide, on this EVM, there's a specific feature enabled by better versioning, which is a technical excellence perspective. What if the political kind of hijacking, right? So I think that part we often less talk about in the technical circle, but often in crypto there's a lot of this kind of good and evil sometimes can emerge as a conversation.
Especially now as we have a lot of layer 2s that are coming out like white labeled, like exchange-based layer 2s, like let's say the Coinbase one. That could definitely see something like that there.
Yeah.
And as well as you mentioned, like the fragmentation of the chains, but you also have the fragmentation in the tooling space. So the layer above, like the L2s is like, and the EVM is programming language, and the layer above that is the tooling, the security components, the decompilers, etc. And they would also need to keep up with all the improvements on the object format as well. So, yeah.
I also sorry, wanted to add something about the features, because it was mentioned here, like basically we are adding features, but honestly, with the EOF1, at least like how it's now, it's technically we are constraining how the code can look and what it can do. It's technically a removal of features, you can say. It's by forcing this blob of data that's now to be of a certain shape, we are technically disallowing certain behaviors that were kind of allowed before. And I think, I don't know if it will make into the final EOF1 or it will be some further EOFs. For example, self-destruct opcode is going to be kind of replaced by something self-indol opcodes. And this is, you can say, also like a feature removal, right? And it's technically like even like there was one proposal that our engineer Hubert Riesdorf, maybe people know, proposed to EOF itself on the discussions, and it's maybe going to be accepted, is that there's now going to be longer a way to delegate call from the EOF into the vanilla EVM version, just because otherwise this will be like a backdoor to access all those features that's technically right now are removed in EOF, right? But of course, like going further, maybe EOF 3, 4, 5 is going to be more feature rich than EOF 1, right?
Yeah. So this is what you actually just said is a nice segue into like the following topic, which is basically, I mean, sure, there are like good sides and bad sides, and people are going to use EOF in various ways. But like, how do you see it starting to propagate in the developer community? Like, what do you see are the first use cases or usages for EOF? In which types of projects? I mean, any kind of thoughts on that front you want to share?
I guess one thing is we're also trying to battle this question earlier and trying to think like how is the adoption actually going to happen. One thing that kind of springs to mind, and that often how these, especially in our space, these things happen is there's probably going to be a big player, like a big project, big protocol, you know, the Uniswaps of the world that's going to release their new smart contract version, and they're going to have it probably, you know, all up to date, and then all the T's crossed and the I's dotted with the EOF container version, you know, with the newest EOF, whatever that's going to be, EOF 1 or whatever that form is going to take. And they're going to say we're now, you know, fully doing it up to the EOF contract with all the things removed that need to be removed, all the things there that need to be there, and then other players later on, as is usually the case in our space, will start to fork this, and that's going to start to propagate this. And then, since these are going to be popular contracts, our security tooling is going to need to start to catch up with this, and it's going to start to adopt these features more. And then other security tools are going to start to follow, and slowly everything is going to kind of avalanche from there. It's definitely just one of the ways I think that adoption is going to happen, but probably in my head, a big player is going to do this, and then that's where it's going to go.
It's funny that you mentioned the Uniswap, because I mean they've been pushing for the 1153, is it? The transient storage, right? I mean, they had their own solution, basically, and now they kind of have to wait for the EOF. Yeah, I mean, because, I mean, first of all, it needs to be implemented in compilers, right? I mean, Solidity that doesn't have it, because it's not even specified yet. We don't have final EOF specs. So, like, what I'm hoping for is that it will be on the Solidity level or the compiler level, it will be natively, or like, won't be like some optional experimental feature, but it will be easy to use, so it will be basically utilized automatically by any contract. And yeah, hopefully we'll save a bunch of gas, yeah.
I'm not so sure if the incremental change is the best way to actually get this out. I'm just wondering if there's chance for bit more leap forward type of improvement that maybe something from scratch, like a new chain or something that they say, hey, how about we start from scratch in this particular chain to demonstrate something like a really, really new, as opposed to incrementally fix something in the ecosystem already. So, but you guys probably should know more.
It's actually interesting that you talk about like starting new chains with these updates. Because with things like ZK AVMs, they need to completely rewrite all their circuits with every single upgrade. I even wonder that, say, because there's a couple of ZK AVMs, you know, supposedly already alive today, for them to upgrade to with this new EOF version, I wonder if it's easier to just start a new layer 2, and then, you know, start a new instance of their ZK AVMs with these upgrades, as opposed to maintain the existing one and then try to upgrade it to the newer version with the EOF. To actually support these leaps, is what you're saying. Because for them, especially for these circuit-based ones, it's going to be very difficult to always keep up to date with incremental upgrades for all of this.
Yeah, I mean, it's great you mentioned it. Like, it was one of the points to be raised. Like, there's like 5 ZK EVM projects right now, and they will have a it's not trivial to change something so big as EVM there or the EOF there. But also for all of the client teams, for all of the Ethereum clients, what it means now is that they basically need to maintain different versions of EVM because you want to do this full sync, and now you need with each hard fork, or like in this case, let's say with each EVM version, an EOF version later, you need to execute this piece of introduction. Then okay, we switch to the new one, and that's a lot of code paths to be maintaining. Yeah.
And on the adoption, I think George and Mario, you mentioned a good thing. I think that this space is incentive-driven, and like dApps need to find a way to to reach the broader audience, and for that they need better virtual machine. And so they are pushing for the innovation on the virtual machine. Then the virtual machine is pushing the innovation on the compiler level. Then they are pushing the innovation on the tooling, and then we are also giving it back to the dApp developers. Yeah. So it's like this whole circle of like incentives that, and everybody is pushing in the right direction. Yeah.
But yeah, of course, it's like this innovation. I think that essentially, at least for Uniswap as well, it was motivated by doing the same things but cheaper, right? Yeah. It's like in the end, it's transaction gas you need to pay for, and the less you pay, the better. And exactly like the EOF, how I see like we are disabling jump opcodes, right? And introducing new static jumps and like call Fs, and because exactly they're not gonna need to do the checks on like validity of the destination addresses and so on. I think it's most likely they're going to be cheaper, and this adoption can come just from the fact that using EOF1 is cheaper, right?
I also recall, I think that now, once EOF comes out, on-chain validators, specifically for like layer 2s, like I think for Optimism, say, the Arbitrums of the world, I think even for them it's not going to be actually cheaper to run their on-chain verifiers to actually verify the state changes submitted by sequencers, and that's cheaper proofs, cheaper rollups, and that's downstream cheaper for the users of those rollups. That's also more adoption, right? If I'm one layer 2 that doesn't adopt this, and my competitor adopts it, and now suddenly they have much cheaper gas costs for their transactions because of the EOF, because their on-chain validators are that much cheaper, I'll be that much more encouraged to adopt this new version as well.
Do you guys think, I mean, one of the biggest things with EOF is definitely a much better utilization of resources and paying less gas and cheaper gas. But do you think that EOF will have an impact on security, a positive impact on security, as we hope it will? Or, we're going to find some other problems down the road?
I would say it's really a good question, and it's really undetermined.
That's why I'm here.
Yes. Last thing I remember was one update in Constantinople, I think, where the storage operations were repriced, and something like Ethereum, Solidity was using the gas limit for enforcing operations during the calls that just need to send the value, and you had enough gas, only like the 2,100 gas, I think, to basically emit an event. And after the reprice, you actually could do some storage operations, and it was problematic. In this case, like what I'm thinking, what's essentially happened in that update and why it's relevant to us, it's the system allowed more behavior than it was before, right? And now, like with the EOF, at least how it looks like, again, the behavior is not added, it's removed mostly, right? So at this point, I would say once there is no backdoor to delegate call back to the more feature-rich EOF, I'm not super concerned about the security, because you're technically just making more restricted systems that shouldn't break easily. But of course, because the tooling needs to catch up with all these changes, maybe there's going to be some compiler bugs again and so on, right? This is always a danger, right? It takes a while to test and to to validate such big changes. So yeah.
You mentioned before the call-off opcode. I think it's going to especially help us validate not just certain contract, but look at the whole chain more holistically and understand better what's going on. Like right now, when you have the EVM execution, you basically almost have no idea what's going on with non-verified contracts. But with the EOF and the code sections, we can better understand what's happening inside there.
Yeah, I think that to that point, especially because a big thing right now in security is doing like war room analysis, and a post-mortem analysis, and trying to determine what happened where with what contract and what happened with those transactions. With the EOF, supposedly it should be much easier to actually perform some of these analytics on the attacker contracts and whatnot. But it's interesting because assuming that once the EOF comes out, you will still be able to for some time deploy legacy contracts, which are a lot more of a random byte, not random, but unstructured bytecode that is much harder to actually decode and understand. I wonder if the attackers in those cases will exclusively deploy non-EOF contracts to throw off all the new tooling that will be better, better able to understand EOF contracts instead. But of course, that's I think going to be attackers are going to attack always. Haters going to hate. But on the other hand, for good contracts and for good bugs, non-maliciously occurred bugs, with EOF, it's going to be much easier to understand what happened and what's going on there and what those attacks did.
Besides EOF obviously improving the development process and hopefully the average quality of a smart contract, do you guys see like EOF for like smart contracts being used in any kind of, well, I don't want to say innovative ways because everything that we're doing in this space is more or less innovative, but something that we haven't seen up until now? Is it going to open some new doors for people to do things differently or to do new things or something like that?
Immediately, no.
No, of course.
I mean, in EOF itself, like the ones that's going to be recent, it's like, again, less features. So say something that's now present in Solidity, like function pointers, it's going to be pretty harder to do it without dynamic jumps, right? But what's big thing is versioning, right?
Yeah.
And with versioning, all the doors can be opened. So.
Axig had this talk, but it was like a year or maybe 2 years ago, about how EOF can work with account abstraction.
Yeah.
So actually we might see some improvements on that front, like actually utilizing it for more effective or more feature-full account abstraction. And yeah, I'm wondering how the data, like now when we have the space for the data, whether it will be maybe, I mean, what I was hoping for before was that this can be utilized better to store the L2 data, but we will have blobs for that, maybe sooner than EOF. So yeah, we'll see about that.
Sure. And like, since the effects of EOF will propagate, and you guys mentioned like we need to develop tooling and everything else, and this is not a Tenderly shill, although it's our panel. How do you think EOF will impact tooling as a whole?
Well, I can start. Yeah, we're doing like security tooling, right? And sometimes like we did like static analyzing on a bytecode. Yeah. Technically, it should become easier for such kind of tools that needs to dive into bytecode analysis, just because dynamic jumps were, let's say, not the most ideal thing to deal with, especially during like some symbolic execution. When you can jump to symbolic, I mean, Solidity things got, in most cases, had a good enough invariance where it never happened. But for generic bytecode, like it's like any bytecode that you can ever deploy, it was like a real problem. So for security tooling on a bytecode, it's going to be most likely easier.
No, an interesting thing there is, I think there were some comments also online around EOF about this, is that because we had to deal with these problems as is in security tooling, some of them, or maybe even the majority, have already been kind of solved. Like we've adapted our security tools for that. So ironically, while the impact is that it's going to be easier to create newer versions on this EOF stuff, we've already have existing code to deal with the previous problems. So we're going to have kind of like both. It's just going to be easier to adopt, I guess, newer tools and create newer versions of these tools. But also interestingly, we're going to need to maintain both for the time being to take care of the legacy contracts as well. So there is a little bit of that slightly negative thing now that we're going to have to take care of like both types of contracts or styles of contracts on chain.
I think the existing toolings definitely will push back on this, right? So because no one pays them to actually do the upgrade. It's like, right, like Ether's gonna have to upgrade their stuff. I mean, they're well paid, but there are people that are doing other toolings may not have the position to actually support both versions, and the economic incentive has to be also there for them. Yeah.
Right. And then, you mentioned an interesting thing that the tooling is going to have to keep up. I mean, I completely agree with that. The interesting part there is that we're still in, like, this is the version 1, and the community is still yet to see the real implementation of this and the possibility of the EOF. I think that once they get a sense of how they can utilize this, what would be the improvements for them that they, if were implemented, that they would benefit from. Like, we're going to see a huge number of use cases for it, and then the tools and security components will try to adapt based on that. And I think there's like huge room for improvement in that area.
Awesome. So the spotlight is back on me. You want more hard questions?
Please.
Honestly, no, I have one more because like the people, at least some of the people will want to know. Well, EOF is just getting started, and we don't really have still any kind of best practices or guidelines or use cases which you could refer to, either good or bad. Like, do you think the best practices will be led by, the Ethereum Foundation or the team behind the EOF, or it is more likely to come from one of the projects which will implement it well and use it well and act as a use case to be replicated throughout the industry?
I think it's a silly answer, but all of them. Specifically because the team behind the that's pushing the EOF, the team Epsilon that you're mentioning, I mean, they're just excellent. I mean, they maintain so many pages about this, and they constantly update all of them, and they provide all of this stuff.
So many HackMD docs, yeah.
Yeah, exactly. I don't know how many HackMD docs I had to go through for this panel. So without a doubt, I feel like once we get closer to implementation and once we have all of these things already set up with the specs and whatnot, they're going to also give out, here's what we think is best practices, because of course, I mean, it's their child, their baby. But likewise, I think, as I was mentioning earlier, I think one or two bigger projects are going to try to jump on this to also claim the spotlight, quite frankly, say, we're the first big one that adopted fully this EOF spec, and here's how we did it, here are our best practices, and then that's going to be the new holy grail of other developers' projects to follow this. So, but I do think there's definitely going to be different pushes, and some for altruistic reasons, like the Epsilon team, to help out with their own little project for the sake of the Ethereum ecosystem, and some a little bit more lucrative to say we are the first ones who got this EOF spec right, and here's our best practices, and do it like that.
Yeah, just to mention again, with the HackMD pages, I believe that AXIC made some Solidity examples or some examples of how EOF should be used. Not sure if it's best practices, but because we are still too early. Not that we don't have implementation, the specification is also not properly figured out. What I would recommend, the latest reading is the Mega EOF endgame, if I'm correct, right? So that would be the current state of the EOF. And then, what I'm interested in, or what will be fun, will be the race to be the first contract, not do it properly, but just to be the first EOF contract on the mainnet. Yeah, we saw that with PushZero as well.
First ZK-AVM.
So you can make NFT out of that or whatever. First EOF on mainnet.
Well, we probably will make an NFT out of it. We have a couple of more minutes. I would like to leave this time for you guys to share some final thoughts or whatever you find interesting about EOF, or whatever crosses your mind.
Actually, I have a question to the rest.
It's not a question, it's a statement.
Oh, I have a question. So, like we mentioned, it's like best practices, but best practices, you mean like for most developers, they are not working with the bytecode, right? They're working with Solidity. In this case, are you thinking that like Solidity will change a lot because of how the bytecode that Solidity needs to compile into will change? Because honestly, it's like there's a layer between developers and the bytecode, which is Solidity, and I expect like if it's done well, people won't even feel the change. Maybe it's like the only best practice so far. Don't use function pointers.
Well, I'm not really quite sure on this one, but I feel like, and again, correct me if I'm wrong, colleagues, but you could end up utilizing the data part of the code a little bit differently, right? And I feel like there could be some clever tricks and best practices around that could be utilized. So things like that, I think, could come up.
So, I mean, like, the best practices are inline bytecode, right, if you are a proper Solidity hacker. So, I mean, there is the layer. But, yeah, I mean, that's what I was mentioning. Like, I hope that Solidity implementation, the compiler will work so smooth that, like, we won't even notice. But still, for example, version is something that you need to work with, right? Like, there will be some subtle changes that we notice,
It's very interesting and speculation. Like, what if Viper does UF better than Solidity?
Actually, I wanted to mention like that's another thing with the tooling that I hope that Viper will catch up on UF and FE as well, which is also already production ready, and now they will have a lot of work to catch up as well. Yeah,
but in a way they have less work to do because they haven't been so spread out. But I get your point completely. Nebusha, some closing thoughts?
Just that I'm really excited about the implementation of DOF. It's been like, what, 9 years since we made any like significant changes on the EVM bytecode, and this opens the door to like new possibilities, and like once we change the base layer, the layer above that are going to change as well, and probably introduce some new way of developing, and introduce ways of having more security on each above layer as well.
Yeah, I completely agree. I think the most exciting part for me is like what this change means, and that it's not a protocol change now, it's the EVM, the computing change, and in itself it has suggestions for future changes and future upgrades. And I feel like it's just going to encourage a lot more maybe even wild experimentation on what could happen with the EVM later. And yeah, that's just exciting.
Awesome. I honestly completely agree with that. Guys, thank you so much for being a part of this panel. I think I speak in everyone's name that we all enjoy this. And for you guys, thanks for listening. And I hope you found this fun and useful. A big applause for the guys.
Thank you so much.
Thanks, you did a great job. You want to stick around and do the rest, or no? Okay.
I'm done with that.
Okay, so we don't have time for a. All right, we're just going to set up for the next talk. We don't have time for a Q&A, but these guys will be hanging around for the rest of the day as well. And we're going to get going in about a minute or two with a talk on homomorphic encryption.
That was awesome.
All right.
Yeah, I mean.
Thank you.
Okay, so we're going to move on with Rick Weber, who's a developer at Sunscreen, and he's going to talk about whatever happened to homomorphic encryption. I'm very curious to know.
Thank you. Hello, everyone. My name is Rick Weber, and I'm going to be talking today about fully homomorphic encryption and what all needs to happen in order for this to become a reality in Web3. So, just a quick survey. Has anyone here heard of fully homomorphic encryption? Okay, a few people. Then you may have heard some of these rumors. You may have heard that it's kind of slow. You've heard that it's unusable or that it's kind of useless. Two of these, in fact, today are actually kind of true in Web3. and one of them a little less so. And hopefully at the end of the talk, you'll know which is which. So to start off, what is fully homomorphic encryption, also known as FHE? So you take a traditional public key encryption scheme. So you generate a public and private key, then you can use the public key to encrypt data, and you can also take a ciphertext and use a secret key to decrypt the data. But there's these additional operations you can do. So you can add ciphertext together, which will produce a new ciphertext that contains the sum of the messages in the operands. And similarly, you can do the same with multiplication, producing the product. There's an additional operation called bootstrapping. And all FHE schemes today use a branch of cryptography known as lattice cryptography. This means that they are quantum safe, but they unfortunately have this side effect called noise. And what noise is as you perform these add and multiply operations, you get more and more noise in the resulting ciphertext. If that noise exceeds some threshold, then if you attempt to decrypt this ciphertext, you get garbage. And so what bootstrapping does is it resets the amount of noise in a ciphertext. And using this technique, you can compute for effectively forever. And because you can do addition and multiplication, and you can do effectively an unlimited number of them, you can compute polynomials, thus you can compute any function you want. So to give a kind of brief history of fully homomorphic encryption, it came into existence conceptually about a year after RSA was invented. It took about 30 years from there to come up with the first implementable scheme. This was done by Craig Gentry, where he introduced the idea of bootstrapping. This scheme was extremely slow, and in practice, it was more academically interesting than practically interesting. A few years later, BGV and BFV were born, and these feature very fast arithmetic, but bootstrapping under these schemes is fairly slow. And so in principle, in practice, people don't actually use bootstrapping under these schemes. A few years later, we got CKKS, which uses approximate arithmetic. And then we got TFHE, which uses binary arithmetic. And TFHE has the added benefit that bootstrapping is very fast, which means that you can effectively do it every operation. Currently, if you were to deploy FHE, you could expect to see performance slowdowns of between a couple 100,000 to a couple million. And you would further see memory usage increase by about that size too. And yeah. So why are we here talking about FHE? FHE is a new tool in the toolbox that you can use to create new kinds of applications. You can have private auctions, you can have dark pools, and you can compute on private shared state if you also use multi-party computation. FHE by itself is not extraordinarily interesting in Web3 because people can just send random messages that aren't ciphertexts. You wouldn't be able to tell the difference, and it would break everything. However, when combined with zero-knowledge proofs, you can create robust systems. So how do we combine FHE and zero-knowledge proofs in Web3? There's two kinds of different models that you theoretically could use. So you can use honest majority, whereby every validator is running the FHE computation and validating proofs coming from users to show that the ciphertexts they're getting are well-formed and that the messages contained within them obey the properties of the system. But you could also turn this into a roll-up, where a validator can do everything that we just talked about, and then additionally produce another zero-knowledge proof showing that the proofs were validated correctly and the FHE computation happened correctly. This roll-up today is kind of academically interesting, but in practice is too cost-prohibitive to actually perform. So everything we're going to be talking about today, we're going to be talking about implementing things with honest majority. So you want to use FHE in Web3. What do you have to do? Well, you have to pick an FHE scheme. We have three schemes to kind of choose from today. We have BFE, CKKS, and TFHE. And so we have three schemes, but we actually only have two schemes. CKKS uses approximate arithmetic, which if you've ever seen the movie Office Space, you realize may be a bad idea for financial transactions as you get rounding errors. BFE and TFHE then BFE, you can perform fast computation, so addition and multiplications are very fast. You get lots of precision, way more than is needed for performing operations in a blockchain setting. The keys in ciphertext are small, and yes, those are scare quotes because everything is relative. Unfortunately, performing some computations with BFE is fairly difficult. For example, if you want to compute the maximum of two values, this is very hard to do, if not practical, with BFE. Furthermore, bootstrapping is extremely expensive with BFE, and so in practice, you don't do it, which means that the number of computations you can perform is finite. TFHE, on the other hand, you can do a lot more operations because of the binary nature of it. So you can, if you want to compute the max of two values, this is possible to do in a reasonable amount of time. You can bootstrap on every operation, which means that noise in practice stays at a fixed level. Unfortunately, there's issues with precision. So if you want to use 32-bit integers or something of approximately that size, your arithmetic is going to be kind of slow and performance will be affected. So you also have fairly large keys, and you can have large ciphertexts if you use TFHE. So now that we've chosen a scheme, depending what we're trying to do, we need to set up the scheme. So with BFE, plaintexts are polynomials, where every coefficient is modulo p. P here means plaintext coefficient. It does not mean prime, as it usually does. And ciphertexts are polynomials modulo q. For the scheme to be correct and functional, we have to have that q is significantly larger than p. So working with polynomials is kind of annoying. So we want to encode data onto the polynomial, for example, an integer. One way you can do this is you can ignore and zero all of the terms in the polynomial except for the constant term. And then when you add and multiply these, you're multiplying integer values, and this will behave correctly. But this requires a fairly large polynomial modulus, or plaintext modulus, in order to not have overflow problems. Alternatively, you can decompose your integer into binary and transcribe this onto the coefficients of the polynomial. So once we've chosen how we want to encode our data, we need to choose the scheme parameters. So we've already kind of talked about the plaintext modulus and the coefficient ciphertext modulus, Q. But there are other scheme parameters as well, such as the polynomial degree. And if you choose these parameters poorly, you can either have way lower performance than needed, or if you make the parameters too small, then you don't have enough computation to successfully decrypt the result. So choosing a larger value of the polynomial degree means you can do more computation because you have a larger noise budget, but it also increases the size of ciphertext and reduces the computation throughput. Finally, BFE has this relinearization operation that after multiply, ciphertext grow in size, relinearization knocks them back down. So the question is, when do you put these into your computation? So is FHE fast or slow? Well, it depends what you're trying to do. If you're trying to do something reasonable and you choose the appropriate scheme, FHE can actually be very fast. Furthermore, if you need to choose the parameters correctly, suitable for your computation. And then you have to create a circuit that efficiently runs that computation. So if we're looking at 32-bit precision, and we want to compare BFE to TFHE, we see that key generation can take quite a while with TFHE, but this is often a one-time cost, so maybe it's not a problem. But the other areas where they differ is that you can see multiplication is significantly faster with BFE than with TFHE. And to kind of give some even more context, this BFE time was not multi-threaded. The TFHE one was. Unfortunately, doing comparisons with BFE, as we've mentioned before, is extremely difficult. But it is possible with TFHE. Now let's look at what happens if we change the scheme parameters with BFE. So we see if we change the lattice dimension from 2048 all the way up to 8192, then we see that the runtimes of various operations increases by maybe a factor of 16. So choosing the right parameters, this kind of highlights why it's important to do so. Everything gets slower if you make things bigger. Conversely with TFHE, if you change the amount of precision, you can see that if we 1.5x the amount of precision, going from 32 to 48-bit, most things are about 1.5x slower, except for multiplication, which is not. It grows by more than a factor of 2. So what's challenging for FHE? You have to pick the right encoding, how you want to map your data onto the underlying plaintext values. You have to choose the right scheme parameters. You have to insert ciphertext maintenance operations as appropriate, for example, relinearization with BFE. You have to choose the right amount of precision you want to use if you want to use TFHE. And then finally, you have to make an efficient circuit that performs the calculation you want to do. So taking high-level descriptions of programs and turning them into some kind of executable format is exactly what a compiler does. But unfortunately today, a lot of FHE compilers are not so great at this. So we're going to look at an application from this SOK paper, and this is a chi-squared test. And if you were to implement this manually in Microsoft Seal with BFE, and you timed the key generation, encryption, computation, and decryption, you can do this in about 50 milliseconds on a commodity laptop. However, a lot of FHE compilers, you just can describe this exact program, and you get overheads anywhere from a few hundredfold to tens of thousands of fold. Two notable exceptions here are Ava, which is a Microsoft compiler that uses CKKS, and again, CKKS is not so useful in Web3. And then the Sunscreen compiler, which can do this with a 1.3x overhead. So for a compiler to be useful in Web3, it has to deliver performance. And then kind of the final step you have to do if you want to use FHE in Web3, you have to prove that your ciphertexts obey the properties of the system and are well formed. So let's take an example. Alice wants to send some money to Bob. So the way you can do this is you have a ledger balance that's encrypted on chain, and Alice can produce a value that she encrypts under both her key and Bob's key, and she has to show that both of these ciphertexts are well formed, so they're not just random garbage. She has to show that the amounts contained in the message that will be subtracted from her balance is the same as the message that will be added to Bob's balance, even though they're encrypted under different keys. She also has to show that the amount she's transacting is greater than 0, so she's not stealing money from Bob. And she also has to show that it's less than her balance, so she's not printing money. So FHE on its own is actually not useful in Web3, because everyone can just print money and do all kinds of things that violate the system. So you have to have zero-knowledge proofs to go along with it. And unfortunately, zero-knowledge proofs are the expensive part of all this computation. So the first thing we have to show is that ciphertexts are well-formed. And there's a number of ways in which you can do this. We first attempted to use R1CS and then tried to find a proof system supporting R1CS that met kind of the prove or verify times and proof size needs. But we were unable to succeed in doing so. So we moved to something called the short discrete log proof. And this is not a general purpose proof system. It is specifically for showing lattice relations. And so Alice, who knows S, and the verifier knows A and T, S contains your message and the noise used during the encryption process. T contains the ciphertext. And A is just setting up the lattice structure and is public. So Alice can create a commitment to S and then prove that S in zero knowledge that AS equals T. And if she does so and also shows that the coefficients in S are sufficiently short or small, then she will have proven that this is a valid encryption under a specific key. So short discrete log proof has some problems when you implement it. The prover times are okay compared to other things out there. The verifier times are not, and the proof sizes are actually pretty good. They're under 2 kilobytes. So what we're working on currently is, can we accelerate the operations used during verification? So we have scalar inversion, scalar multiplication, and guess what? Multiscalar multiplication. Everyone's trying to speed this up. We're trying to do it on curve 25519, though. So now that we've shown that a ciphertext is well formed, we have to show that the messages contained in the ciphertext obey the properties of the system. So, like, you're not subtracting money from someone else. So we, to do this, we use bulletproofs with R1CS. And even though we're using bulletproofs, which has linear verification time as the number of constraints increases, the number of constraints and multiplies you need to create these kind of circuits is not very large. You don't need very many of them. So we have pretty reasonable prover times, reasonable verifier times, and our proof sizes are under 2 kilobytes. But we have a problem. So the prover has created a proof to a short discrete log proof and a proof to the bulletproofs kind of in a vacuum. How does the verifier know that the inputs you gave to both of these proofs were the same? Well, it turns out both schemes use Pedersen commitments at their core. And so what you can do is break these Pedersen commitments into shared and non-shared parts. And if you, the shared part contains the commitment to the inputs to the R1CS circuit and is also part of the short discrete log proof coefficients in S. So because you're sharing the same commitments, the verifier knows that these are the same inputs. And so using a number of other tricks, like using the same curve, permuting some generators, and reusing the blinding factor, the verifier can be convinced that the inputs going into both proofs are the same. So when we initially set out, we started trying to prove all of this with R1CS because it would provide a nice interface. So we built a compiler because expressing this directly with the bulletproofs library would be kind of tedious. So we built a compiler. This is currently ongoing work, and we're kind of refining it. But the kind of general idea is you write a Rust function, you put a little macro on it, and pass it to the compiler, and it will build a circuit for you. Because everything is in Rust, it's in a DSL, you can share your circuits with others using crates, as you would anything else in Rust. You also get all the syntax highlighting and all the other nice things about the Rust ecosystem. Today we support types, gadgets, and public and private inputs. And for R1CS alone, this API is very straightforward. You compile a circuit, you then can feed some inputs and generate a proof for it that satisfy that circuit. And then you can give that proof to somebody and they can verify that it's correct. However, what happens when we bring short discrete log proofs into the picture? How does one specify that A matrix to set up the proof of ciphertext well-formedness? And how do you specify what you're going to share between the two proofs? This is currently an open question, and we're still iterating on this. So, if you want to build a compiler for Web3, it has to do a number of things. It has to support BFE and TFHE, because these are the two schemes that are useful in Web3. It has to build fast circuits, and then you need a runtime that can efficiently run the circuits, so using multi-threading. You need data types, so users aren't playing directly with polynomials, and you need kind of efficient mechanisms for under TFHE so that people can play with integers. You need to automatically insert ciphertext maintenance operations such as relinearization, because you don't want to have to explain to a developer what relinearization is. And finally, a lot of compilers today view FHE compilation as, I'm going to compile this one circuit, I'm going to run some inputs through it, get a result, and then decrypt that, and that's the end of the story. But that's not really the scenario in Web3. In Web3, you have a balance that's on chain. I send some money to you, your balance increments. You send some money to someone else, now it decrements. And so the ciphertext is going through multiple circuits. We call this program chaining, and this is a mechanism that will help inform what parameters you should use during compilation. Then finally, FHE is useless without zero-knowledge proofs. So you kind of need a runtime that can marry the integration between zero-knowledge proofs and FHE. So today, FHE is not actually usable in Web3. We need better tooling, and in particular, we need to marry FHE and zero-knowledge proofs together. So now we've kind of talked about a number of problems with bringing FHE to Web3. We can hopefully start bringing some solutions to the table. So this concludes the talk. You can follow us at Sunscreen Tech on Twitter, or you can visit sunscreen.tech, and that's our website from where you can access our Discord, our GitHub repository, and our blog. So at this point, I can take any questions.
So if anybody has any questions, we had a couple of minutes here.
When you talk about real-world applications, what's the most exciting real-world application of this that you're looking forward to?
Right. Private AMMs is kind of what we initially got us excited down this route.
Anybody else? Okay, anybody else? If not, we're going to take a quick break, and we'll continue the program with Torgen from Chain Security. He's going to talk about, what is it? Talk about, MEV in Proof of Stake. Sorry about that. Okay, thanks, Rick, man.
Thanks.
Oh, yeah, you put the proto-dank track. Okay, cool. All right.
Yeah, let's do 2 minutes maybe. I have a companion which should come and help me with the talk, but I don't see them, so... Who is it? It's a cat.
A cat? Oh, the woman with the cat walked out?
The woman with the cat.
She walked out.
Does she need some money? No. I just need a cat.
We're looking to do Q&A at the end. Do you have time to do any talk?
I'm not sure. We'll see how it goes.
All right.
We'll see.
Is this for the are you going to do the ceremony?
Yes. I'm doing the ceremony. Yeah. That's
cool.
That's why I need
a cat.
A cat ceremony. Yeah.
Okay.
I mean, yeah. If you see her, but like, she should be here like by the end of the talk. Like, doesn't have to be here now, but there it is.
Catropy, now I understand. All right, everybody, we're ready to continue. We've got Mario here from the Ethereum Foundation, right?
Yes.
And he's going to talk about proto-dank sharding and take us through a catropy ceremony, which I'm curious to hear about.
Thank you so much. Let's see if this works. Oh, awesome, awesome. Yeah, thank you so much, all of you folks, for coming. I'm very excited to have you here because I will be talking about some things I consider rather important. I'm going to talk about the next Ethereum upgrades, about its scalability, and how cats fit into all of this. And maybe you heard about the summoning ceremony, maybe you heard about the danksharding, and that's what we are going to dive into today, because the whispers from the shadows tell us of powerful spirit of Dankshard. So what is the Dankshard? And to understand that, we need to look at the Ethereum roadmap first. So you might be familiar with this picture. It's the updated roadmap from Vitalik from like maybe a year ago almost, or something like that, a few months back. And as you can see, we managed to do a big move here, where we finished withdrawals this week in Chapella. Of course, the biggest upgrade in Chapella was push 0, but yeah, also withdrawals and stuff. I mean, huge kudos to all devs to finishing this, because so we see there are multiple tracks, multiple these boxes of things that needs to be done on Ethereum that people are working on, implementing and researching. And today I'm going to look deeper into one of these boxes, especially the Surge. And as you can notice, the Surge is talking about the scalability, about EIP 4844 and having, what does it say, 100K transactions per second. Oh my God, and rollups, yeah. I hated the estimations there, but yeah, let's work with this. So we will talk about scalability and what does it mean, or what is the problem here? Why do we even need to talk about this? Is the trilemma or dilemma that we have in blockchains. Because the whole point of Ethereum, the whole point of Bitcoin, the whole point of this ecosystem is to be decentralized and secure in a way that each of the people sitting in this room, I would say, and many people in the world are able to actually verify what is happening in Ethereum. That's what makes it trustless. That's what makes it decentralized, right? All of you, I see some folks with the computers here. I believe all of the computers I see here are able to run the Ethereum client and verify everything which is happening on Ethereum. But to verify everything means that the more things there is in the everything, the harder it gets. The more computation you need, the more storage you need, the bigger computer you need. And it gets incredibly more expensive. That means that just the richest from this room would be able to verify it, and the decentralization would be sacrificed. So our goal is to actually scale Ethereum to enable to put more things in there while not increasing the demands, the requirement for verifying everything. Well, the reason for it, it's supposed to be a GIF, but it's in PDF, I'm sorry. But yeah. So the reason for it, you might notice, especially in those days of DeFi summer, that the gas are pretty high, that's the thing, right? I mean, we've been talking about having some world computer accessible to everyone, but if it's going to cost 10 or around, right now it might be a few dollars or tens of dollars, sometimes it might be hundreds of dollars per transaction. That's not very inclusive. So we want to make Ethereum to be scalable, which means enable lower fees and at the same time stay decentralized as possible. So here comes the Surge. And the Surge is the Surge is all about the layer 2 scaling. You might heard about that, and we'll get there. But first, you might notice the word in the beginning, the sharding, because it all starts with that. Like the sharding is this thing in Ethereum community which was discussed since like years and years ago. I don't know, 7 years back, more. It's 2023, like 8, 9 years maybe. And the idea was the execution sharding in a way that, right now we have, after the merge, we have Ethereum. The Ethereum right now looks as the execution, the actual data, all the transactions, all the contracts, which are driven by the beacon chain, by the coordination layer, which is doing the consensus that decides what a validator consider valid or not. And the idea of sharding is that we use this beacon chain layer to actually coordinate not just the Ethereum execution as it is now, but many other layers or shards. And the sharding was something which seemed like far future a few years back, and it still might sound like, where are these shards we are still hearing about? But today we have the layer 2s, right? The ZK or optimistic layer 2s, and these are scaling Ethereum today. And how rollups work, just to give a quick summary on that, well, they roll up the data and put them on Ethereum. The idea here is that in case of optimistic rollup, or I mean in both, we have basically a separate chain, its own network, execution layer, and its own data, and we just either create a proof or just compressed version of this data, and we put that on Ethereum. So imagine that I can do many transactions on the layer 2 and or on the rollup, and I pay for the gas fees on Ethereum itself just for a fraction of it, because I'm able to roll it up like this. And I have two ways of doing it: either using some fraud-proof mechanism, which can decide if there was something executed not correctly on the layer 2, or using validity proof in ZK. But no matter what it means is that I take this rollup data and I put it on Ethereum. So yeah, this is what I was explaining. This is how the Ethereum looks like right now. We have the consensus layer, the execution layer, all the transaction, the EVM, the Ethereum state is here, and rollups are putting more data into this state. They are using what we call data to basically just store their transaction data or the validity proofs in the Ethereum itself. So we have this bunch of these rollups. They put the call data to Ethereum. So this is how it looks like today. And if you try to use rollups, you might notice that it's still not as cheap as some people would like to. It's still a few cents, maybe $1 or even a few dollars per transaction when the fees on the Ethereum goes high. Because, well, the fee that you pay for the rollups is mostly determined by the Ethereum mainnet gas fees. That's because we store all of this data on Ethereum. Arbitrum is missing here, which is like the biggest chunk. It will be like more than 10 gigabytes of data. So let's say we have like 20-something gigabytes of data stored in Ethereum. That's like incredibly expensive. And all of your computers, if you're running those nodes, are storing this data, which are kind of useless if you think about it, because we already use them. So so we have, because in these two mechanisms, in optimistic rollup, you can create a fraud proof only in some given period. So if after a week nobody create a fraud proof, nobody create a proof that the execution on the layer 2 was incorrect based on the layer 1 data, if nobody does that, then we consider it, I don't want to say finalized, but unchangeable. Nobody can challenge it anymore. And after this week or a few weeks, let's say, the data is still sitting in Ethereum, but it's completely useless because, well, it cannot be used for the fraud proofs anymore. In case of ZK, it's similar. We have the validity proof, and if it's verified and settled once, like why should we keep it forever there? Okay, so now enter the proto-dunk sharding. I'm sorry, I have alarm because I used to wake up at this hour. And it's another phone, I'm sorry. Yeah. Okay, I think I just snoozed it. Let's see you in 10 minutes. Anyway, so we are putting the data on Ethereum itself, but with the proto-dunk sharding. So the proto-dunk sharding is the EIP 4844, also called the blob carrying transaction. So we are introducing these blobs, basically a new kind of transactions, and this transaction is special because it has a backpack. It has a backpack called blob, and in this blob we have arbitrary data. We don't care what data it is. It's just some chunk of data that a transaction takes and puts it actually on the beacon chain. Puts it on the consensus layer in a way that sitting here, it will disappear in a few weeks. We will store it only for a month, let's say. And while we are storing it there, what the hell? Like, how can we reach it in the like? What I'm doing right now is when you talk as a user, your wallet, or if you're a smart contract dev, you're talking to the execution layer, you're talking to the RPC of the node, right? And that's accessing all of these data in EVM. But the data is not there now. We don't know anything about the data, but what we have is a commitment to this data. A commitment, it's a sort of a proof that the data exists or existed at the time in this form. So as a layer 2, I'm connecting here to the execution layer, and I verify that the data, my rollup data, is in the blob on the consensus layer based on this commitment, this KZG commitment. So yeah, that's basically what we are trying to achieve. Why? Because now, if I don't need to use the call data here, I don't need to execute anything in the EVM. I just create this KZG commitment from a precompile, and it will be basically no computation, and the data storage is ephemeral, right? The data, again, the blobs doesn't have to be there for more than a few weeks, because then it's useless for the fraud proofs, and the layer 2 needs to keep its history by itself anyway. So your node will just store this data for like some bigger amount of data just for a few weeks, then dumps it. So there is some upper limit that it reaches, and this way we can save a lot of resources and still save a bunch of data. And therefore make it much more cheaper, like magnitude level of cheaper. And yeah, there is this discussion that like it's not really execution sharding because we are working with the blob data. So the current meme is that we dunk scale the blob space. That's like the latest nomenclature I noticed. The Denkun is the upcoming upgrade. Now we had the Chapella, and the next one will be Denkun. That's the current focus right now. That's what is considered for the inclusion there, and the CoreDev community is now doing its best to finish the research, to finish the implementations on the 4844 or the dunk scaling the blob space. So now back to the commitments, back to the idea. I don't want to dive that deep into it, but the idea is that we have a polynomial. The KZG commitment is basically a polynomial commitment. What we are able to do here is like represent the pieces of data that we have as a polynomial, and if you have a polynomial, you can prove that you know the data without the data itself, just by referencing some point on the polynomial, right? And the KZG is a bit more complicated, but it's one of the ways how to do it, and it was decided to be used because of its features. Here is a nice summary of various ways how it could be done, and you see why KZG, the first column here, was chosen to do it. So we need this KZG cryptography to create commitment for the proto-dunk sharding, and then for the dunk sharding itself. So the idea right now with the 4844 is to create, basically to take the current layer 2s and thanks to this cryptography, make it more scalable, but already forward compatible with the full dunk sharding. So the dunk sharding right now is idea is based on data availability sampling. I don't have to go there, but like the full dunk sharding will be based on like reading pieces of data from the various shards, and thanks to the data availability sampling, basically it ensures that the data is available, again thanks to polynomials, thanks to that you can it's like the erasure coding, like in the DVDs, right? When you scratch part of your DVD, it still plays because it can calculate what is missing there. So this is like the full dunk sharding. And before we get there, we get this proto-dunk sharding. Dunk sharding is named after Dankrat Feist, who was researching it, and the proto-dunk sharding by Protolambda, who took the idea of already using the KZG to create the blobs. And as you can see here, the only problem with this KZG, or like the main problem, first of all, is that we are using ECDSA, we are using pairings. It's like a bit more complicated cryptography, so like there is some complexity to it. But the main problem that you can notice is that it requires the trusted setup. Now that's a scary thing, and many people were scared to hear that Ethereum should have some sort of trusted setup, because it's something which didn't gain a lot of trust in the community over the past few years, I think. Now, what is the trusted setup? So yeah, trusted setup is a way how we are going to invoke the spirit of Dankshard. This is the spirit of Dankshard. It's Dankrad as a spirit. Right. Yeah, first of all, the thing here is that for KZG, or maybe also some like Snarks, some ZK cryptography, you might know that we need what is called structured reference string, like some secret which is created for the cryptography setup, and it needs to stay secret because it's used to actually create those proofs. We use it as this reference point, and in case that somebody knows this number, the secret number, they can create false proofs. They could create commitments to data which doesn't exist, let's say, and he would break the whole security setup of Ethereum. So we need to craft this number in a way that it's that nobody knows it and nobody can reveal it. That's not an easy task, but that's what a trusted setup is. And it works. We are going to do it with so-called multi-party computation ceremony, which means that many people can connect to the ceremony using their computer, add to this computation, and we get output which is set up, but not one person, but by many people. You might heard about like many of these setups in history. Basically, any snark like starts with Zcash, where they did it like maybe 10 people in a hotel, then they destroy their computers, so they don't store the data which created the setup. But there's been many other of these ceremonies. For Tornado Cash, for example, for Aztec in Ethereum. And how does it work generally in these ceremonies? What we are using here is called Powers of Tau. And you can imagine it as a relay race, because it works in a way that we have some initial setupper, and now the first person adds his secret, adds his data, and does the computation, creates basically a public key, which is not revealing his secret, it's just the public part, passes it to the next person. Again, he adds his secret, does the computation, creates a new public key, or the public data, and moves it to the next person. And we create this chain of people with each person adding their secret to the system. And the assumption here, the whole security assumption here is that unless everybody gets together to redo the whole ceremony, everybody reveals their secrets, it's secure. Oh, here it is. Again, it's basically one honest party assumption. If there is at least one person who does not reveal the secret they put into the ceremony, the whole ceremony is secure, because you would need each party to reveal the final secret. So this is a way how we can make it secure. And the ceremony has been going on for months. Maybe you haven't noticed, but it's been it's been almost a year since the initiative started, because we need to finish this. We need to make this multi-party computation to create the secret. It needs to be ready before the actual danksharding or proto-danksharding gets implemented. So it's been developed during the last year, and this year in January, it was open for contributions. So basically, what it means that you could go, anybody could contribute, because the more people contribute, the smaller chances that somebody will reveal their secret. So the idea is that some Bitcoiner or somebody come to you like, oh, Ethereum uses trusted setup. It's trusted. Vitalik has the key or whatnot. Well, no, he does not. I have the key. I set it up. I contribute to the ceremony. I secure Ethereum. You can say that if you contribute. And now this is the main interface for the contribution. And of course, it needs to be more diverse, more decentralized. This is just one way how to contribute. There are multiple client implementations which connect to the ceremony. So in case there is a bug in one of these implementations, the others are still secure. The most popular one was a front-end website which is easy to use, so you could just go through it, enter your entropy by moving your mouse, writing something there. Also your browser generates entropy in this case. You need to log in, and then when the powers of tau are passed to you, your computer does their computation and publishes it. So this is how you could secure Ethereum. However, this open contribution period for now is over. It finished around a month ago. It was open for like 2 months, and right now there are only special contributions allowed, which means you need to have good friends who are doing the ceremony, and they will get you. No. There was actually a grant mechanism for people who wanted to create some special contributions. To mention some of them, there were guys doing it from a satellite. They contributed to the ceremony from the space. There were folks in New York, Calvin from Optimism, who organized this Moloch party where they created an ephemeral album. It was like multiple groups of people creating their own music. Then they played it, used the recording or used the music to generate the entropy, and then deleted everything, right? The album just was played once at a party in New York. So there are multiple ways how we can contribute creatively to this ceremony. And yeah, just to reiterate, we need a lot of contributions. In the public ceremony, there was around 80,000 contributions. So we can assume that up to 80,000 people were contributing. It was less because there was some spam, but we have tens of thousands of people contributing, and we hope that at least one of them didn't save the secret. We have the multiple client implement. The sequencer, you can see it in the slides. The sequencer is online. We are connecting to basically this one central entity, which is just ordering the people who are contributing. It doesn't have any other power than doing this. And we can trust it, or we can verify it. We don't need to trust it because you can just download a file which is like 150 megabytes at the moment, and it's a recording of all the contributions, and you can cryptographically verify that it's the chain which works together. So we know it's secure. Now, again, we need more and more contributions, and I would like to use today to do some of the contributions. But before I get there, I would like to take a moment to think about how we actually do it, how we actually create these secrets. Because I'm talking about generating some secrets, some secret number, and if you think about it, this is how all the computers are secured. This is how all the cryptography is secured, right? Your Ethereum wallet, you can see the address, and the private key, which is hidden somewhere in your hardware wallet or your computer or somewhere. The private key is just a huge random number, right? Like atoms in the universe, big number, and it needs to be random enough so nobody can guess it. But now the question is, where do I get the randomness? Like, what is the randomness? Because the randomness, the entropy, is something coming from the nature, from the space. Computers are calculators. They cannot think of a random number. Like, you are a person. If I tell you the random number, there is a high probability you tell me 7. But a part of that, like, you're a pretty good randomness generator. But computer is not. Computer is like does equations. So your computer, your phones, when they are generating these cryptographic keys, or like all of the internet, the HTTPS traffic, everything is secured by some keys generated by the CPU from some noise, from some electrical noise, temperature, maybe your mouse movements. If you are using Linux and you call the /udef random, it might even tell you that I'm still collecting randomness, not a good entropy, you have to wait. So the idea here is that as we need a lot of contributions, we need a lot of people, a lot of nature creating this randomness. My idea was to use cats, but not just a few cats, but a lot of cats, and that's why I have you here, because today you will become the cats. There is this paper called Proof of Cat, which explains how cryptography can be secured by cats. Because, well, cats are pretty random. They are their own beings. You cannot really predict their behavior. So what about using them as one of these inputs for our computers to generate randomness? So we can find the details at proof.cat, and this paper proposes a device for generating randomness using a cat toy with a microcontroller, and it's called Catropy. This is the device that I have right here in this little ball. So it's this fluffy ball. It's handmade. My friend in Slovakia, with hackers in Prague, we designed this board. It's called Catropy. It's open. You can also make it yourself, or you can get one. Yeah, this is a movement when you move with your hand like this with a gyro. So basically, it has a gyroscope, accelerometer, and it collects the movement data. And the more you move it, the more random it gets. So you can give it to your cat to play with. And right now, I would like to do the ceremony with you folks. And I believe that before we start, so right now it's on, and as it is blinking, when it turns green, it's collecting the data. So it collects the data in some random intervals. And actually, before we start with the people, do we have a cat here? I believe we have a cat. I would like to actually use a cat, and come here. I can't promise that it will work.
It's too big.
It's too big for him? Oi! Come on. Give me a paw. Come on, give it a sniff. Give it a sniff. It's too big. It moves. Come on. Ah, okay. Well, look, that's why we need so many cats, because not all of them are excited by the toy. Not all of them are. So we have bunch of lazy cats in the world, but some of them are playful. And if I put it on the floor, it's a good idea. Josef, can you get it? But I mean, we can. I mean, we had a kitty. You all saw it. It's cute and all. So let's maybe move to.
There we go.
But he's not gonna jump down there. Okay. So let's just. You get it? Thank you. But if you can pass it to the people, please, everybody. Please, like, just move with it, just play with it a little carefully, because there's the electronic inside. Like, don't apply too much force. But please pass it to everyone. Everybody, just play with it for a few seconds, and that was please, try to throw it closer, because it was pretty far. I hope it survived it. If it's still blinking, it's all right. Is it blinking? Cool. Yeah, I mean, it's a lot of entropy. Thank you. Okay, try to take shorter paths, please. Anyway, so now the entropy from your movement is being collected by the toy. And we have just 3 minutes, but after it, I will take it to my laptop and submit it to the ceremony. So this way you can tell that you secured Ethereum on eTzurich, and then that we have some. So like a part of this little boy, we have around 20 cats securing Ethereum thanks to this toy, and also like more than 100 core devs. Also, what I would like to mention is that these toys, I made a bunch of them, and I was giving them away I'm not selling them, but you can get them based on a donation to a cat shelter in Barcelona. There is a beautiful place in Barcelona called Jardin del Gats. It's a garden of cats. It's a kitty land, and it's a lovely place where they take care of stray cats. They have like 40 of them, and thanks to Catropy, thanks to this device and the donations from Ethereum community, I was able to donate like 500 euros already. And if you would like it, for like $30 donation to catropy.eat, and you can send an email and put email there to me or meow@proof.cat. you can reach out and you can get a toy as well. I can ship it to you. I don't have more units right now, but if you would like to have it for your cat or just play with it by yourself, you can get it by donating to Kitties in Barcelona. Yeah, so that's it. If you want to learn more about the KZG ceremony, check out the KZG ceremony repo, which is like the main coordination where there is all the information about the ceremony, which is still going on. And if you want to learn more into technicalities of how it works, I would recommend the talk by Carl, who is actually one of the main brains behind the whole ceremony from DEF CON, explained really nicely. And yeah, also this was nice about the implementation part of it, an interview with the talk by folks from the PSC team. Again, like the public ceremony, the public contributions are over, and the special contributions are finishing tomorrow or on Monday. So this is like your last chance to help to secure Ethereum. And where is my ball? I don't see it. Oh, you get it. Oh, thank you. Whoa. Thanks. Okay. Thank you all for your entropy here. I will keep it safe. And yeah, I believe that's it. So thanks again for your attention and for your entropy.
We got time for some questions.
Yeah.
All right, guys, if I'd have known, I'd have brought my cat as well. All right, we got a couple of minutes for questions. Anybody have one? They're in the back.
Hey, thanks of all. Thank you for helping us contribute this. I just had a question. When you were comparing the different systems, I noticed that this one is a trusted setup. We took that away with the ceremony, but it's also quantum vulnerable.
Yes.
I wanted to ask, first of all, obviously vulnerable doesn't mean that it's inevitable, so I don't know how complex it is even with a quantum computer, but is there anything in place to make it more quantum resistant in the future? Or if there isn't, how difficult would it be to break the entire encryption? Is it a simple how simple would it be to find the polynomial, basically?
Yeah, thank you for the question. I mean, the quantum resistance is a huge problem. It was already mentioned at this conference, especially in the KZG. So it's using the, I believe that like it's using this double pair of ECDCA, which is vulnerable to quantum computers. And I would say that like the KZG is like it's a big complex step. It's not like I wanted to say that, like, having figured out, for example, quantum-resistant ECDSA alternative, we could upgrade KZG, but I'm not sure if it will be possible with this complex setup. So, like, for right now, I believe that it's the best solution that we have, like the most effective one. And for the long-term future, like, it's not the only thing that we need to fix. And yeah, I hope there will be some alternatives to work on. I don't think about any solution right now. I don't think there is. But if you, so the picture that I had there is from the ETH research, ETH.ch actually. I mean, we are in Switzerland, it's .ch, ETH research, where this post is from. And there is a lot of discussion about the KZG, exactly about when it was initially decided to be used. And there was also some more discussion about the quantum resistance. You can look it up, whether there are some updates on it. Yeah.
Anybody else? Here we go.
What is the kitty cat's name?
Oh my God! I'm sorry, I was going to say it. Yeah, Jupiter. Thank you so much for being here. Yeah, I was going to say it first. Yeah. Yeah, Jupiter came all the way from Belarus, but through Moscow and Lisbon, and ended up here, almost giving us his entropy. But like, you know, cats, they know that their entropy is precious. So if they don't decide to give it to you, they won't. You can actually read more on that in the Proof of Cat paper.
Does Jupiter have a question? Do you think, or? I think he's clear. Yeah.
we got some meows in the beginning, but he's calm now. Yeah.
Okay, so that'll do it. Hey, that was fun.
Yeah, thank you so much. Thank you all of you. Thanks again for the cryptography. I will for the entropy. And yeah, I will submit it after the talk, and you can see it in in the ceremony.ethereum.org that there is the submission. The latest one will be this. Yeah, thanks a lot.
Great. All right. So now we know what Catropy is. Okay, we're going to move the program on with the next speaker. Torgen is here from Chain Security, and he's going to talk to us about new forms of miner abstracted value in Ethereum proof of stake.
Cool. Hello, everyone. I'm happy to be here. Yeah, so today I'm going to be talking to you guys about something that I call future block MEV in proof of stake, which is kind of a made-up name, but I hope that by the end of this presentation you'll know what it means. Is this the right clicker? I don't think so. Oh, maybe not. Okay. Yeah, so I'm from Chain Security. We do smart contract audits. We work with a lot of companies that you might have heard of. In my normal day job, my specialty is working with the smart contracts directly. But today I'm also going to be talking more about like the consensus engine of Ethereum. And so to understand what future block MEV is supposed to be, first we have to talk about block production. And block production is something that has changed a lot in Ethereum over the last year. So before the big merge, we had proof of work, right? And in proof of work, it was kind of a chaos. So in proof of work, every single miner was always trying to mine every single block. And what that meant was you could never know who was going to be producing the next block. Now, in proof of stake, it's a little bit more structured. So in proof of stake, we're actually determining whose turn it is going to be to produce a block ahead of time. And in Ethereum specifically, you can actually know up to 2 epochs ahead of time, which is about 12 minutes, who is going to be producing the next blocks. And in particular, that means that if you are one of the validators in Ethereum, you'll know 12 minutes ahead of time when your validator is going to be producing a block. And this is different than in proof of stake. You could never know before, and now you can, right? So this is what I mean when I talk about future block MEV. So what are some things that we can do with that knowledge? So one thing is that you could use it for oracle manipulation. So in oracle, in DeFi, usually we use price oracles, which tell you what the price of something is, right? Like the price of Ethereum today is different than it was yesterday. And there's a lot of DeFi protocols that need to know the prices of their assets. For example, if you had a lending protocol where you can put in some collateral and then you can borrow a different currency, it's important to know what the exchange rate between those currencies are. And so one of the approaches to oracles are so-called on-chain oracles, where you use an on-chain market, for example, Uniswap, and that's super convenient because that data is already on-chain and your contract can just go read the other contract and see what the price is at the moment. Now, if you just do that in a naive way and you just read the price at the current moment, that's probably not a great idea because someone can just come and push the price up and then you read it and then they push it down again and you're reading a totally wrong price. So the kind of mitigation that people usually use is that they use a time-weighted average price of some time frame. So for example, you say you use the average over the last 30 minutes of prices. And specifically in Uniswap, the way it works is it always records the last price in a block. So it doesn't matter what the prices are in the middle of a block, it only matters at the end of the block. And the reason why this is supposed to be good is that it means that if you want to manipulate the price, you have to bring it to, let's say, some very high level, and then you have to wait for the block to end. And when the block ends, that means that everyone else sees that this price is wrong, right? So there's going to be someone who's doing arbitrage. He's seeing, oh, the price on Uniswap is super high, and maybe on Coinbase, it's lower, right? So they can just buy coins in one place and then sell them in the other, and they'll make a huge profit. And if you're the attacker that manipulated the price, that's going to be a loss for you. So now, if we take into consideration this idea of future block MEV, where we know that in the future we're going to be proposing a block, we can do this exact same attack, right? But we're going to do it such that we manipulate the price in the block where the next one is going to be our own block, right? So the block n+1 here in the graphic is going to be the one that we know we're going to be proposing. And that means we're going to be able to order the transactions in that block in any way we want. So we'll buy a bunch of the token in block n, and then the price is going to get recorded. And then in block n+1, we just make sure that our own transaction is going to be the very first transaction. And we can just decide that. Like nobody else has any chance against us because we literally have the ordering rights. And so in that way, we can make sure that we are the ones that are taking the arbitrage and we're pushing the price back down to where it's supposed to be. And so what that means is that instead of the entire amount of money that we used for the manipulation being a cost, we're only going to be paying the Uniswap trading fees of about 0.3% when we're trading up and down. But aside from that, we have no costs. And so basically what this means is we are hiding MEV from other people, right? So I guess an important thing to note is I'm assuming that we can use a dark pool, such as the Flashbots MEV Boost, to put our transaction into block N, right? Currently, about like 2/3 of all Ethereum block producers are using MEV Boost. And if you use MEV Boost, what they give you is transaction privacy. So that means before the transaction gets into a block, nobody is supposed to see it. This works in most cases. We've also seen some cases where it doesn't. But assuming that we have that, then in block N, we're not going to use the mempool, so no one can see our transaction. Then our transaction happens. Everyone can see that the block was produced. But then it's too late because the next block is going to be our block. We can take the arbitrage down. And then the other cool thing about this is that if, let's say, there was a lending market that was using this oracle, then maybe because of our manipulation, some positions would be in the zone where they can be liquidated now, right? Let's say that we push the price of an asset down. And then, because that block is ours, we can also just use the rest of that block space for ourselves, right? So first, we'd take the arbitrage, and then we'd do a bunch of liquidations that are based on the new oracle price. And this is something that also nobody else can compete with us on, because we'll just won't let them into the block, and we'll just take the first slots for ourselves. And so this means we can trigger a liquidation with no competition. And the reason we can even do those liquidations is because of an oracle manipulation that we caused and had very low cost for. And so this is basically the reason why nobody uses these on-chain oracles today. So you can't actually do this in practice just because nobody is using the TWAP oracles. And unfortunately, there's also not really a lot of better ways to do it with on-chain oracles. So a lot of people use Chainlink instead, or similar services, where you don't have this specific problem, but you have a bunch of other problems, especially in terms of centralization. Yeah. Now, another fun thing that you can do if you know that you're going to have a future block is if you have a block, you get all the MEV payments, right? If someone really wants to get into that block, they'll pay you a lot of money for it. So as an example of that, we have here the Other Side NFT sale. This was the Bored Ape Yacht Club land. This is the biggest NFT sale that ever happened. And here you can see the gas costs. At the beginning, they were very low. And then at 1 o'clock, the NFT sale started, right? And you can see that the gas that was paid per block immediately jumped up to 200 ETH per block, which is about $500,000 at the time. So every single validator that got one of those blocks got paid $500,000. But there's a caveat to it, which is we have the two colors, right? We have the black and the red. So in the red, we have the base fee from the EIP 1559, and in the black is the validator tip. So the validators at the beginning, they all got paid $500,000, right? But then, because of the way that the Ethereum fee market works, when there's a lot of demand, the base fee spikes up as well. So after about 15 minutes or so, actually all of the ETH that was being paid was being burned in the base fee. And the validators that got all of the rest of the super high fees actually got nothing, right? They only get the black part. So that shows you that it's super important to be in that very beginning phase of a gas spike, right? So let's say that we are maybe some big entity that controls quite a lot of validators, and we can go check always, right, if in the next 12 minutes we're going to have a bunch of blocks. And if we do have, let's say, an overproportional number of blocks, then it would be worth it for us to maybe make some MEV happen, right? And so one way you could do that is you just launch an NFT mint at that point where you're going to be collecting the MEV, right? So you could maybe work together with an NFT project and you tell them like, hey, you probably don't care exactly when your mint starts, right? So you just pay them some money and you tell them like, okay, you can start your mint within this 30-minute window and we'll tell you exactly when, right? And then you make it so that it starts when all of your validators are going to be collecting the MEV fees. And so this is kind of cool because it's like the validators should actually pay someone who is launching a project to do it at the time where it benefits them most. And it's kind of like reverse MEV, right? The validators are paying the projects, and then the users of the projects are paying back the validators. And of course, it's very bad for like the average validators that aren't playing this game because they're probably going to get less lucky on average. Another thing that's interesting, which was actually brought to my attention by a guy called Iridian Alpha, is that because of the way EIP 1559 works, it might actually be profitable to censor some blocks, and combined with the way that MEV-Boost works as well. So as we saw before, the total fees paid on Ethereum can be very high, but it's possible that only a small amount of that goes to validators, right? So we have one example block here where the proposer was paid about 20 times less than what the total transaction fees paid were. So that means that block space, if you want to make a transaction, is expensive because you have to pay the base fee and the tip. But the blocks themselves are actually very cheap. You only have to pay the tip, right? And so that means that if, for example, you wanted to just create a block that's empty, you can forget about the base fee and you just pay the validator the tip, right? And the way that it works in the MEV-Boost system, which most validators are using, is they just get a block and they don't know what the transactions are inside. They only get the block header. And they also get how much the fees that, or the tip that's going to be paid to them is going to be, right? So if you're a builder in the Flashbot system, which is totally permissionless, anyone can be a builder, you can just start handing out empty blocks to validators, and you tell them, I'll pay you a slightly more than all the other blocks, right? And they'll just take it and blindly pick the one that gives them the most money. Now, the question is, why would you do this, right? And the reason is, or the reason that I can think of, is that you might want to censor the block before yours, right? So again, we know when our block is going to be. We know which one is going to be ahead of us. So we might want to just make that block be empty, right? We pay a small amount, like in that example, it was maybe like $40 to the validator ahead of us. And then all of those transactions are instead going to come into our block. And also, the block before was empty, so nothing happened on the blockchain, right? And this is super important for arbitrage, once again. So one example is what is called StatArb. So for example, the Binance markets, they trade all the time, right? All the tokens are always trading. But on Uniswap, the tokens only trade once every 12 seconds because there's only an Ethereum block every 12 seconds. So there's actually always arbitrage opportunities between Binance and Uniswap, just because one market lags it, right? And now you can imagine if there's one block being skipped on Ethereum, now all of a sudden Uniswap lags behind by 24 seconds, right? And so the arbitrage opportunities are going to be bigger because the market is going to move more on average. And it actually turns out that if you do this, if you stat arb every 2 blocks, that will end up being about 35% more profitable, which is an analysis done by this guy on Twitter. I also recommend you check him out. Because you can end up, first of all, with fewer transaction fees, but then also just because the market has more time to move, the arbitrage is generally going to be bigger, and it actually turns out it'll be more than the combined amount of just the 2 single arbitrages. And also, even if you're just doing atomic arbitrage, so like one very popular MEV strategy is sandwiching, where you see a big trade happening, and then you buy that same token before, and then the trade happens, and afterwards you sell it again. So you're basically making sure that that trade gets the maximum amount of slippage that they've set, and you take that slippage for yourself as profit. And now if you can censor, let's say, the block before, then there's a good chance that there's going to be more sandwich transactions that you can all sandwich at once, right? Like if it was 2 different trades in 2 blocks, you would have to sandwich twice. You would have to pay the gas fees twice. But if you just move them both into 1 block, you can do it both at once. Also, if you want to do the arbitrage yourself, again, you're the block producer, so nobody can compete with you. Or you can just have other people do it for you and pay you the fees. And then it'll actually be more efficient to sandwich multiple people at once than it would be if you did it one by one. And I think here there's actually also an effect where if you have more sandwiches, they move the price more, and it actually makes it more profitable to sandwich them as well. Yeah, so that already brings me to the takeaways for today. So I think my main thing is that block proposers in proof of stake are known in advance, and this is very different than how it was before in proof of stake, and you can take advantage of it in many different ways, right? This information can be very valuable if you want it to be. I've showed you a couple different ways to do that. I'm stumbling upon new ways all the time. I'm sure you can also think of some that I haven't shown here. And yeah, I think it'll be very interesting. I think it's an underexplored area so far. And we'll see how big of a pain this is going to become in the future. You know, I could imagine maybe there's some problems that will show up as a cause of this. We haven't seen too much of it yet. We've seen the MEV boost system not quite work the way it's supposed to just 2 weeks ago, where a validator actually basically proposed 2 blocks, two different ones. So they got the one from MEV boost, where they don't see the transactions, and then they signed that block, and then the transactions are released, and then they just created a new block as well with those same transactions, but they weren't respecting the MEV boost rules. So they were just reordering them however they wanted to. And in that way, they could actually take transactions that were supposed to all happen at once, and they took them apart, and they were able to steal $20 million from the MEV bots that were creating those transaction bundles. And in that specific case, there was actually also a small bug in MEV boost, but in general, you can actually just do this in every single MEV boost block. If you're a proposer, you might have to kind of race and make sure that your block is distributed through the network more, but it's definitely possible. And you will get slashed probably for 1 ETH, but if you can steal $20 million, maybe 1 ETH is fine to get slashed by. So yeah, I think it's a very interesting and still evolving topic. Yeah, if you're interested in the Oracle manipulation part that I talked about, I actually have a whole blog post about that, and also this future block MEV, multi-block MEV stuff that I've been talking about. I also wrote a paper about the Oracle manipulation about 2 years ago, back when it was in proof of work. It's actually, you could kind of do the same stuff in proof of work as well. In case you're interested, the paper is also linked in there. Yeah, so thank you very much for your attention. If you want, follow me on Twitter, read the blog post. Thank you very much.
So we got a lot of time. Can you wait, hang around for some questions?
Sure.
All right, everybody. So we've actually got a fair amount of time left before the next speaker. Any questions out there? Any block producers looking for some tips?
Hey, I'm over here on your right.
Hi.
Can you maybe just refresh us the premise that the block producers are known ahead of time? Can you maybe just like give us a refresher on exactly how that works with Ethereum, like how the block proposer is chosen and how far ahead of time?
Yeah. Basically in Ethereum, the two inputs to the random function that decides who the block producers are going to be is first of all the RANDAO value from the beacon chain, and then also the current Ethereum validator set. And the RANDAO value, you can always know it 2 epochs ahead of time. That's just how it's determined. And then the Ethereum validator set, it can at most change every epoch, but if nobody gets removed from the validator set, it actually also won't change within two epochs. Yeah, and that's just the input to the random function that generates the proposers. So if nobody gets removed from the validator set, you'll know it up to 2 epochs ahead of time, right? So if you're at the very beginning of 1 epoch, you'll know the entire next 32 blocks of this epoch, and then the 32 blocks after that as well. Now, if you're at the very end of the epoch, you'll just know like the next block, right, the end of the epoch, and then the next epoch as well. But in case someone gets slashed and gets removed from the validator set, then that second input changes, the validator set, and then it gets reshuffled. So if you get unlucky, then the next epoch is going to change. So the current epoch that you're in right now, you can know for sure that it won't change, and the next one is like pretty unlikely to change, I would say.
Anybody else?
Yeah, so I wanted to ask, it seems like the Flashbot's VEV problem is persistence in the sense that, if I'm an MVer, I can get front run by the validator at just the cost of 1 ETH, essentially. So what does this mean? Does it mean like MEVers can't have more than 1 ETH vulnerable at any point in time because then they can just get front run like this happened, or what does that mean?
So kind of, yes, the validator can just propose a second block. There are some parts that make it a little bit harder, which is they're going to sign their block and give it to the MEV-boost relay, and that's going to send it to the network. And then they actually, 2 weeks ago when this happened, they added a delay of 1 second of the relay sending the transactions back to the validator. So you probably won't get it quick enough there. So what you need to do is you have to have a bunch of Ethereum nodes. They can just be normal full nodes. They don't have to be staking nodes. And you have to basically build up a good peer-to-peer connection in the Ethereum network so that you have a high chance of being a peer of that node that the relay owns, right? And then you'll get the transactions from there, hopefully with less than 1 second delay, right? And then you need to do all your computations for your new block of how you want to reorder it. And then you need to spread that block in the network quicker than the other block, which was earlier, right? So again, here it's going to help you if you have a bunch of different nodes and you have good connectivity and you send it out from all of those nodes to their peers. Because basically, the other validators, they're just going to sign whatever they see first, right? And so you need your block to have more signatures than the other one so that yours becomes the canonical one, right? So it's not super simple. It's always going to be a race, but it's pretty easy to just spin up 1,000 Ethereum validators, right? There's not really a cost to it. So yeah, it's not super simple. The other thing is 1 ETH is going to be your slashing amount if nobody else gets slashed in the same period. If other people are also doing weird stuff, or if you do this every block, the slashing amounts are going to go up. But even if you get slashed for 32 ETH and you can steal 20 million, it doesn't matter, right? So I do think it's a real problem. The real world case where we saw this happening 2 weeks ago, there was actually the bug in the MEV boost relay where it didn't validate that the block header was correct, that was signed. So there was actually no race because the relay got an invalid block and it didn't release it to the network. And then the validator just sent their block and it was the only block, right? So they didn't have to race. So now that they fixed that, they will have to do this race, but I think it's something that's feasible to do.
Super short follow-up question. Yeah. Is this actually bad for the network? Because I think the only ones that are disadvantaged here are MEVers, essentially. If there's this threat for MEVers to not do MEV, it's good for the network in a sense, because then...
I mean, I think it's not as simple as saying all MEV is bad or all people that use the MEV relay are bad, right? For example, if I wanted to just do a big trade on Uniswap, I would also send my transaction through the MEV relay because of the privacy that it gives me, right? Because I don't want to be front run, even if I'm not creating a bundle, right? But then if this happened where the validator did this attack, then they could front run me, even though I think that I'm using this private mempool, which protects me from MEV.
All right, we still have some time. Anybody else? Maybe yeah, over here in the middle. And then I think we have one more over here afterwards.
Hi. Hi. So imagine at some point it's possible to hide completely who's proposing the next block or the future blocks. Is there maybe a threshold or some models on the percentage of stake that one validator might have to assume it's so high that you can optimistically assume that you will have 2 blocks in a row and create attacks that are profitable anyway, even if you don't know, because you know that you have some likelihood of having 2 or even 3 blocks in a row. Is there?
Yeah. So
does it make sense?
If you can't see the future validators anymore?
Sorry?
What was your beginning of the question?
Yeah, imagine that we find a way that there is no future MEV in the sense that you cannot know. Yeah. There is an Ethereum crate such that validators will not know in advance. But still the stake, maybe 30% is so high that it will still work. Is there some possible model like that?
So I don't think so. I think if you didn't know, there would always be some percentage that you don't have blocks in a row, and it's probably not worth it. But I think the Ethereum upgrade you're talking about is the secret shared validators idea. And as far as I understand, the idea is that other people won't know when you're going to be proposing a block, but you yourself are still going to know ahead of time. So if I've understood that correctly, then it's actually not a solution to this problem. So I'm not aware of any solutions right now being proposed.
Thanks.
I think over here, he had his hand up. Which one of you is front running?
I had a question on account abstraction. So things like, so one of the things you can do with account abstraction is going to be to schedule transactions. And I think, so I'm not an expert, but I would imagine that if you're using something like Biconomy, for instance, in the case of the other side Mint, you could basically say, okay, you pre-commit and you schedule transactions to happen over a certain amount of time to avoid having a gas war, right? Does that mean that then the operator is totally in control of because you can obviously, you know how much you have to print and you know what the market is, right? So you could basically arb this as freely as you want. Does that mean that it becomes quite mercenary?
So I'm not super familiar with how the scheduling works. Like if you...
Me neither.
Yeah, okay. I mean, at the end of the day, the proposers will always decide which transactions go in the block, right, no matter what you do. And there always has to be someone initiating the transaction. Like transactions never happen by themselves, even with account abstraction. Yeah, so you'll still have the same problem if you're trying to get into a specific block. Maybe if there's some mechanism where you can just like sign up for a mint ahead of time and they give you some different time windows or something like that, then yes. But I think that would just be like a design decision on how you create the mint.
And do you think that if, like, as things grow and the transactional layer becomes basically happening on rollups and not really on mainnet anymore,
yeah.
do you think that the fact that most protocols will, enfin, you'll be using zero-knowledge proofs most of the time, right? Do you think that this kind of arbs away the use cases of MEV?
So I don't think so. I think all of those execution layers are going to have their own MEV problems. You know, you have usually some sequencer that just decides the ordering, and then that sequencer is basically in control of the MEV. And then the zero-knowledge proof stuff happens afterwards, usually, when the ordering on the rollup has already been decided. So yeah, it's just a question of how you design the rights to order transactions. And I think you will definitely want to have some kind of bidding market where people can pay more to have their transactions included quicker.
Okay, I think we're going to have to stop it there. Thanks a lot, man.
Thank you very much.
All right, moving on. We have Akaki here from Off-Chain Labs. I'll take your water. And he's going to talk about roll-up batch processing strategies on the base layer. Welcome.
So, hello everyone. Welcome to my presentation. And I want to thank organizers for organizing this excellent event. So this is a joint project together with Edward Felten, who is a co-founder and chief scientist at Off-Chain Labs. And I joined them last year as a research scientist. So if you are not familiar with Off-Chain Labs, this is a company that built Arbitrum rollup chain and contributes to its development at the moment. So now, what are rollups? This is probably the shortest introduction in the rollups. So the purpose of rollups is to scale the base layer, and in our case it's Ethereum, but in principle it can be some other layer 1 blockchain. And it does by moving the execution phase of the chain. But they inherit security of the base layer by posting the transaction relevant data, which is called call data, to this base layer. And here, in case of optimistic rollups, as Arbitrum is, transaction relevant data is just transactions compressed, but you can imagine some other technologies that can post some other specification of the data. And then, second part where the rollup technology comes in is some rollup specific mechanism that checks that execution was done correctly. Okay? So now here we are solving a problem of posting call data at the right time. And as you saw in the previous presentation, I think there was a slide where Ethereum base fee rises very quickly and very high, but it doesn't last forever. It lasts for a few hours, maybe at most. And these periods, the rollups or sequencer of the rollup or whoever posts the transaction relevant data, call data, want to avoid posting because the price is high, but on the other hand, they also want to avoid delaying the posting too much. Okay? And one instance is that there was a time where a base fee raised 100 times, and it lasted several hours, and the automatic mechanism of the sequencer didn't post the data, and then Arbitrum developers had to manually post the data. Okay, so now how do we model this optimization problem? So we assume that in round I, so round corresponds to every time, let's say, new batch is created, we count how many batches do we have currently queued, and we also look at the current base fee price. Okay? And then we need to make a decision based on these two numbers. Do we want to, so how many batches do we want to post? Okay, so this is our strategy S, that is a function of the price that we see now and how many batches do we have at the moment. Okay, so intuitively you can guess that S should be weekly increasing in the QI, so more batches we have in the queue, more we want to post, and it should be also weekly decreasing in price. Higher the price, less we want to post. And this just helps the optimization in that it decreases the search space of optimal strategies. Okay, so next is how the cost is modeled. So first part of the cost is exactly how much we pay if we post ni many batches, and batches have the same size approximately. That was the case at least with Arbitrum. That creates almost equal size batches. Then the first part of the cost is direct cost of posting. And second part of the cost is delay cost. And here we take quadratic function of how many are remaining for the future, how many batches do we want to post in the future. But you can take some other function. We thought that quadratic is easier to analyze, and it has some nice analytical properties, and also because we wanted it to be faster than linear function. So there is this normalizing factor C, should also capture some preferences. So here I want to make a comment. For example, if the rollup has a technology that delays the finality, then you should not withhold a batch more than this time for sure. Otherwise, there is a security issue. And in case of Arbitrum, that delay time is quite large. It's 1 week, so it's fine to assume some quadratic function. And anyway, the coefficients that we are plugging in, it makes too expensive to delay. So we are never reaching 1 week period. Okay, so further justification of delay costs. First is psychological. When the users see that batches are not posted, they think that maybe sequencer is broken, and that creates maybe some kind of panic. Another is L2 users, so rollup users. They may have preferences about how fast they want their transactions to be posted on the base layer. And third part, which is not very relevant at the moment because the sequencer acts in the interest of the rollup, is that pricing of the transaction and compensating the Ethereum. Compensating the sequencer for posting on the Ethereum, on the base layer. And further, there is a delay, harder the mechanism to compensate becomes. So that's the further justification of the delay cost. Okay, so now what is the optimization problem? In the next round, we're subtracting how many batches we posted, but one new batch arrives, so that's how rounds are actually defined. And we assume that in the next round, the price of the gas fee is a random variable that depends on the current price. And at the moment, we assume that this is independent of what rollup does or what is our strategy. but I would say this is not completely true at the moment. If, for example, there is some huge roll-up, it can also move this price up if it posts too many, or down if it doesn't post anything. And in the future, if roll-ups become even bigger, then this may not hold. But at the moment, let's say it's a reasonable assumption. What is the objective value? We want to optimize discounted costs. So we sum up costs over the infinite horizon, and we discount the future. So 1 unit of cost we incur today is delta in the next round, and delta square in the next to next. So we care slightly less about the future and more about the present. And this also makes the expression converge. So initially we take that we don't have any batches, so we start from fresh, and there is some price of the base fee. But the results are independent of this initialization, actually. Okay, so now what do we think about the gas fee? So first we assumed that it's uniformly distributed on this interval of 7/8 times the price and 9/8 the price, and these constants are coming from base fee mechanism, this EIP 1559. So if there is a maximum demand achieved, then the base fee is increasing by 12.5%. This is 1/8. If the demand was 0, then it decreases with the same amount. And we were assuming, let's say, in the next round, demand will be uniform at random, and that's what happens with the price. And then if, for example, Arbitrum posts, or yes, any other roll-up posts every 5 blocks, then we need to take convolution of the 5 uniform random variables, and this is quite a good approximation for normal distribution. But then we looked at the data, and it doesn't look very uniform at random, and there is a big outlier. We see that in about 16–17% of the cases, full blocks were created. And that is happening because of the priority fees and how EIP 1559 works. And there is some small spike, also some small outlier at the 0 blocks. And this is also happening because of this EIP 1559. And there is another paper that we later found out that shows that sometimes if there is a big miner, it prefers and thinks that this miner will propose also not miner, but now proposer. Proposer proposes 2 blocks in a row. It prefers to keep 1 block empty so that base fee goes down, and then make next block full, because then it can collect more priority fees. So whatever, this is what data shows, and we have to work with this. But if we look at 1 minute relative change, now it looks kind of normal. There is small spike at 1.8, which means that 5 times in a row there was a full block, but otherwise it looks quite normal with some bias on the left, but that is also explainable. And actually I skipped this part here, that the product of these 2 numbers, T1 and T2, is less than 1. So this is again coming from the EIP 1559 transaction fee mechanism. But anyway, as we see here, uniform, so the normal distribution is a good approximation of what is happening to the price when roll-up comes next time to post a batch. Okay, this I already talked about. So related literature is actually inventory policy problem, where there is some manufacturer produces something. In our case, manufacturer is Rollup and produces blocks, and it wants to either sell, depending on the price and demand. In our case, these are cost of posting. So that's the first difference, but in principle, they are dual problems. And the second difference is that manufacturer has linear costs, or at least that's what we found is in the literature, and that is associated with maintenance costs. But in our case, we think that it's not linear because of the nature. It's not just maintenance costs. We don't keep it in the warehouse, but yeah, users have some requirements that their transactions are on the base layer, or we have some deadline that we need to post. So to solve this problem, we applied Q-learning, so it's dynamic programming. So we need to calculate two matrices. So first matrix is the Q from the Q-learning, I suppose. It has parameters state, ST, that tells what is the price and also how many in the queue we have the batches. And AT is a action. So in each state, we need to know what is the best action, or what will be the value of the queue table if action AT is taken. And then we need to calculate the optimal action, and that is denoted by O vector. And we have this value update iteration with 1 minus alpha, let's say probability. We keep the original value of the table, and with alpha we take cost that is incurred in this state plus delta times, because delta refers to the future, expected cost, but taking into account that when we go in the future, we will take optimal actions. Okay, so this is where, this is what this min A means. So we are taking the action that minimizes the cost. So we assume that in the future, we will optimally distribute or post the batches. Okay, so this is a very clean iterative formula. And yeah, so I already explained what is CT. That's the cost that is incurred by taking this action AT. And to find this action A that is minimizing the cost in the future, we take O vector element, because we know that O is optimal. And then we calculate O, or reassign values of O once we iterate and update values of Q new matrix. And initialization can be done in arbitrary way, but we just took one of the initializations, which means that at every moment we post all the batches. Okay, this initialization, but you can post 0 batches and it doesn't really matter. It converges very quickly and with the same speed. Okay, now the complexities and how much we could try, how large values of price and the size of the queue. So we discretized the price space, of course. We couldn't calculate on the continuum. And yeah, so we assume that we cannot hold more than some upper bound on queue batches. And then the space complexity is the size of this large matrix, is PQ square, and this is not a bottleneck. Then we need to also assume something about the support of the random variable that defines the next round price. And if we assume that this is also linear in the price, and in case of, let's say, in uniform case, it's not exactly linear, but in case of normal distribution, it's linear, then time complexity is P square, Q square. This is already quite slow for large values of P and Q, but there is also the convergence parameter I. So we want, we will not calculate the precise values of the matrix, but we need to converge to something. And this parameter depends on the learning factor. So higher the learning factor, so it's not actually exactly monotonic, but what it really depends on is delta. So higher the delta, slower it is. So if we take delta closer to 1, which means that we care about the future cost almost the same as today's cost, then it becomes very slow. Okay, so now what are the insights that we obtain? First is that there is a threshold price below which all batches are posted. So if the price is low enough, just post all the batches, and this is actually quite intuitive. But if the price is high enough, then it depends. Now we want to keep some size, so there is another threshold that depends on the price, above which we post everything, and below which we don't post anything. Okay, so there are these two thresholds here. And then we compare this algorithm that we calculated, the optimal algorithm, to the old algorithm of Arbitrum, and compare their performance. So in the new algorithm, the QLearn algorithm, we have two parameters. So first we need to define the large threshold, TP, and then depending on the price, we need to decide how fast, so how large is the other threshold. That depends on the price. In the original algorithm, there were 3 parameters. So there was an acceptable price under which it posts the batch, and each batch is associated with these 3 parameters. Then there is some exponent, and third, there is update time. So what happens if the price is not below acceptable price? Then it waits for this update time, which in that case was 2 hours, and then it multiplies the acceptable price by exponent, and that exponent was 2. So it was waiting for 2 hours, and if the price was still not good enough, then it was doubling the price. So there is also trivial algorithm that we looked at, and this is just post all batches immediately, and it has good property that there are no delay costs. But of course, sometimes then you post very, very high cost, and you don't wait for the price to drop. And also it has minimum load on the system when you do this L1 cost calculation. Okay, so there is another algorithm that also completely ignores the delay cost and just waits for the price to drop below some threshold. But there we looked at the data and saw that if, for example, you take threshold cost 100, then you need sometimes to wait 1,394 blocks, and this is unacceptable. And with 60, it was 14,000, crazy, so that is completely unacceptable. Okay, so now we compare these 2 algorithms that we have and see that the old algorithm actually does better job when it comes to publishing costs, so the observable cost. But the new algorithm doesn't make it too bad, so the publishing cost slightly increases, but delay cost is dropped very much, and if you look at the maximum delay, it's much lower. So for example, for parameters 60 and 2, maximum delay is only 42 minutes, while in case of, let's say, the original algorithm, it would be 193. That's like more than 3 hours. So there is a lot of future research to be done in this direction. First, we don't have a theoretical proof of optimality of our insight, so why do we need to have these thresholds? And I think it's possible to do, fairly easy, but I'm not an expert in the optimization field or that kind of optimization. Second is, so I mentioned that it can be that price changes depending on the strategy, and now we assume that it's independent. So that is also an interesting problem to look at, and then the same approach doesn't apply. So there was also mentioning of this EIP 4844 by Mario, I think. So this is new initiative for the batch posting or the roll-up data posting, called data posting, which creates a new market. And one may think that all this, what we did now becomes irrelevant because this data will become almost free. But this is not the case. And I think insights that we obtain in this research will be useful in the future when this proposal will be deployed. And the last question is, assume, so far, as far as I know, only Arbitrum uses this strategy and other chains are doing, so I don't know exactly what they're doing, but most of them are not doing this strategy, and it would be interesting to observe if this strategy is an equilibrium strategy. So if everyone else does this, is this equilibrium, or do the separate chains prefer to deviate from this? Thank you for your attention.
Thank you very much. I think, yes, the microphone is working. We have about 5 minutes for any questions. That has been super technical and super interesting. I don't have any questions because I don't follow everything, but maybe Wolfgang in the middle of the room has a question, or someone else. Yes, sir, right in the middle. Do we have a microphone for that gentleman right here in the middle, or? You can shout, absolutely.
So, if I understand correctly, there is a threshold above which you take nothing. Hello? And there is a threshold below which you take everything. Is that right?
So there is threshold below which you post all batches, and above which there is another threshold depending on the price you want to post more or less.
And what do you do in between the two thresholds?
So there is no in between. So let's say we post threshold 60. So under 60 we post everything. Above 60, let's say if it's very close to 60, we post almost everything, but let's say keep one. So from 60 to 64, so there is some functional form. We keep one batch, but if it's higher and higher, we keep more and more. So for, let's say, 200, we would keep 10 batches, but the rest we will post.
Oh, so it's not that you keep everything in the queue, is that
yeah, so
you keep
we
some of them?
Keep some amount, depending how large it is. And larger it is, more we keep.
Okay, and do you know or have you thought about what happens if you include some randomization in the keeping process? So instead of keeping it linearly or quadratically as it increases, maybe there is some randomization type of process.
So I found one result that shows that deterministic strategy of this type is optimal. So it doesn't specify what is the strategy, but it says that some strategy like this, which specifies for each price. So this is from inventory policy literature. So that specifies for the price or the demand in that case and quantity, posting or selling fixed amount deterministically is optimal. So you don't want to randomize or do some weird things.
And okay, that's great. And is this already productive? Is this how Arbitrum Sequencer works?
Yes,
now?
yes. So we deployed it last year in November, and it already went through the spikes a few times. But there is not enough data to make some conclusions yet. But at some point, we will track the data and observe what it is actually doing in the production.
Awesome. Thank you very much.
Thank you.
Thank you for the question. We have 1 minute and 10 seconds until the next session. Time for one more question. Anybody? Anybody? Wolfgang, you're taking notes? No? If not, then we thank you very much for the presentation. Super. And you can just join us on the side here. We're going to move on to the next section, but before that, thank you very much. I should let you know that I am the better looking version of Tom, who was moderating the sessions before. He had more white hair. I'm better looking. Anyway, my name is Ian from RuleMatch, formerly of Bitcoin Swiss, and great to see all of you here today. The next session is going to be about self-sovereign identity We have 3 panelists for the session. The first one is Alison Fromm, and she's going to be joined by 2 Daniels, D squared, so to say. The subject of self-sovereign identity, of course, very interesting and important for Web3, and especially perhaps here in Switzerland, with control and security being front and center. Alison, Daniel, jump right in. That's great. You all have a microphone, so you're all set? Equipped. All right. Over to you.
Hello, can you hear me? I think we are not, oh, we're not using that? Oh, sorry. I always love to ask how many highly technical people it takes to run a microphone at a blockchain conference. How about now? Oh, I think I'm live.
Much better.
Excellent. Are we good to go? Okay. Excellent. Well, thank you for joining us for our discussion about self-sovereign identity. Thanks, Ian, for the introduction. I'm Alison Fromm, Chief Commercial Officer at Proofspace. We provide an identity platform for issuing, holding, and verifying credentials. We'll get into more of what that means from our expert panelists. So first, I'd like to ask Daniel Geistiger, President and co-founder of Procivis, to introduce himself.
Yes, hello. Thank you very much for the introduction. My name is Daniel. I'm the co-founder of Procivis. I'm also co-founder of a couple of other blockchain companies here in Switzerland, among others TrustSquare, Verum Capital, and Nexus Squared. Very happy to be here. I was invited by the University of Zurich because of the project we did with them when it comes to student self-sovereign identities and master diplomas as verifiable credentials, which I'm talking about a little bit later. I'm also very happy to be here because of the partnership with this conference with my colleague from Czech Republic, with Paralelní Polis, where I did some meetups already 2016 on the topic of blockchain, and with my first company I did some scouting in Prague and actually many other countries around Europe to find what at the time was not so easy blockchain startups. And with Josef, who is one of the co-organizers here, we did actually quite a few of these meetups in Prague. So super cool to be seeing these connections coming to Zurich, and having that sort of setup here is perfect. I'm also been a regular visitor of the Paralelní Polis Hackers Congress in October, which usually took place before Corona in October, which again I think is sort of part of the co-organizational team here. And so it's great to see Zurich welcoming the team from Prague here in Zurich.
Thank you, Daniel. And our other Daniel Säuberli, President of DDoS. Please introduce yourself.
Hello, everyone. Thanks for being here. So I really appreciated the invitation by Claudio to actually speak here and give a little bit of an impression on what is going on here in Switzerland in terms of self-sovereign identity. So I'm basically a corporate guy or legacy corporate guy. I spent a lot of time at IBM, where I learned very early about blockchain and the benefits to organizations and to governments. So I'm more, let's say, from a knowledge perspective on that side. During my career, I had various positions in organizations that kind of led me to believe that we need to do something in terms of bringing more privacy to the digital world. And with that, with a couple of partners, including Procivis and Hochschule Luzern, and Vasily Suvorov and others, we founded DDoS in 2020, actually as an organization that would be a body for stakeholders to come together and solution and discuss about the emerging topics of self-sovereign identity and the challenges that it actually represents when it comes to adoption, when it comes to educating the public, when it comes to standardization or finding consensus around standards. Also the aspects of technology are well represented, and within DDoS we kind of try to create value in a very vertical way. So each of the sectoral ecosystems can kind of experiment with the technology and come together to kind of drive consensus around the aspects of what is important to drive broad adoption. So with that, besides DDoS, I'm actually also a board member at TrustSquare, so really happy to be part of that W3 or Web3 ecosystem here in Switzerland. And we also help organizations together with Vasily Suvorov on actually applying the right technologies with a company called Accelerate to today's world, especially where it's important to establish a more ecosystem-based business model, as well as ensuring that trust is established in each of the interactions and transactions of organizations and individuals.
Yeah, thank you. And I have to say, I'm a member of GDAS, and Switzerland is incredibly fortunate to have such a great organization of bringing together different stakeholders to promote the principles of self-sovereign identity in combination sometimes with the Swiss government. So we're talking about self-sovereign identity. Maybe we can go back to you, Daniel. What does that mean? Can you break it down for us at a high level? It's become a buzzword, but what are we talking about?
Absolutely. So, I mean, self-sovereign identity, from our perspective, is there to be able to create verifiable transactions and interactions and ensure that these data can be verifiable, any kind of proof can be verifiable at any point in time with the notion of being privacy preserving at any point in time as well. So when you think about self-sovereign identity and the various roles in self-sovereign identity, you can think about the issuer of a certain information or credential. You can think about the holder of that credential, and you can think about the verifier that actually verifies a certain piece of information at a certain point in time of a transaction or an interaction. And there is a fourth body that actually is involved, especially when we want to make it adaptable by organizations and governments and today's society at large. That's the governing authority, when you wish, so if you wish, which actually puts out the rules under which this ecosystem actually operates. So thinking about some of the principles that are important is that you completely disconnect the verification information from actually the issuer. So you want to ensure that there is privacy in verifying that I am Daniel Säuberli as part of, so maybe I'll show my ID card here because it's always a good example to kind of show that, because there are various credentials that you can see on my ID card. So if I am showing that ID card as a holder, I ask a verifier to verify that information, and there is trust established through a governing authority that actually issued this card or has actually put some security mechanisms and some mechanisms that allow the verifier to verify that the authenticity of the ID card at point of presentation. So now as we transfer this concept into the digital world, it's very hard to verify certain pieces of information. Obviously, most of you are cryptographers or know what cryptography is, and therefore you understand these concepts, but actually then disconnecting completely the ability of verifying from the knowledge of the issuer that your ID card has been verified at a certain point in time is an extremely challenging undertaking in the digital world, and that's what self-sovereign identity actually is solving.
Yeah, that's an excellent summary. So you've got the issuer, the holder, and the verifier, and the challenge is to allow the holder to present their credential in a decentralized way so that it can be securely verified. And if I can just add on to that, since we're at the Ethereum conference and you're all engaged in blockchain in one way or another, one of the interesting things is that blockchains give transparency and verifiability of transactions. Privacy is more of a challenge. One of the things that verifiable credentials do is take data about the holders of those credentials off-chain. So the data, the claims, the data, the attributes of a credential are never stored on the blockchain, not in any way, not even in an encrypted way. The only thing that gets recorded maybe into a blockchain ledger is the decentralized identifier of the issuer. And so then when the holder of the credential goes to present their verifiable credential, which is a data standard, to a verifier, the verifier checks the cryptographic signature of the issuer, which is public, to verify the data that's in the verifiable credential. But from a privacy-preserving standpoint, that data is direct peer-to-peer from the issuer to the holder, and then from the holder to the verifier, and can be verified without the need to ever put the claims, the individual's private information, into a blockchain, which will be there forever. But the blockchain is used as a register of the public identifier of the issuer for verification purposes. And it can get a little more complicated than that, but we won't go into the weeds just yet. What might be helpful is if we take it to a practical example. So Dani, perhaps you could talk about what our neighbor Zug did in the early days with Ethereum using the technology.
Yeah, I mean, ultimately, as with many things, there was a very early on development here in Switzerland when it comes to using what I would call the concepts of self-sovereign identity that became prominent in 2016, I guess, with Christopher Allen's post and paper on the topic. This was then taken by the Ethereum ecosystem and developed into something what was called Uport. And then Uport, as one of the implementation options of a self-sovereign identity framework, was actually picked up by the city of Zug as the first real implementation, and I would say really early on, a bit too early on probably for a real productive use, and issued a first citizen digital identity based on self-sovereign identity concepts based on Uport in the city of Zug. So 2017, I mean, this was a really ahead of the times premiere when it comes to using that technology. And it went spectacularly good. At the time, Crypto Valley was really, anyway, a topic in everybody's mouth. The Swiss ecosystem was growing quickly into really, I guess, the global hotspot when it comes to blockchain technologies. Ethereum obviously being in Zug as the foundation since 2014 obviously had also a major impact on that. And so it was a good showcase. It was, I would call it a proof of concept, but it was done with real citizens, and the citizens, I think at the time it was 200-300 citizens that actually used this self-sovereign identity wallet, and they got issued the identity by the city of Zug government. Really showcased how SSI could work, and that was really spectacularly good. At the same time, my inspiration to actually at the time start the company Procivis was a mix of that input. Also, my vision behind Procivis was that we should develop ecosystems around government-centric solutions and services based on a mobile technology that basically builds itself on self-sovereign identities. And so that concept then, we also tried to build like a pilot project like the Uport project for Zug. But when we talked to our government clients, we realized quickly this is far too abstract a concept for them to grasp. And specifically when it comes to decentralized technologies and something like the Ethereum network as the basis, something that they cannot control, this was obvious to us that this cannot work that way at that moment in time already. So we took some of these concepts of the self-sovereign identity, that we are a mobile wallet company, so we are only doing mobile wallet solutions. We've taken into account some of these paradigms of being in control of your data, being in control of sharing, being in control of what you share with whom, at what time, having a record of that, being able to reclaim your data, all of those concepts that were not so dependent on a blockchain or a decentralized technology, we put into our product. But then we stopped there and we really started building on top of traditional PKI-based infrastructure so the governments could still control what they are doing. And I think, unfortunately, at the time, as I said, the City of Zug's project was a good showcase for SSI, but then, unfortunately, if you think about the average Swiss person or an average Swiss citizen that potentially uses such a thing in the long run, they're not conceptually not ready to basically deal with gas and all the concepts that are needed actually to make such a system work. And so the project basically stopped there. And I think, but it was really, really good showcase for Switzerland, for the Crypto Valley and the city of Zug to showcase how innovative even a place like Switzerland can be.
Yeah, yeah. And I want to continue the Swiss story moving forward with SSI, but before I do that, could I ask you one follow-up question? So when you have a self-sovereign identity credential in your wallet, how is that different from having basically a picture of my traditional ID in digital format? What's the benefit to having a self-sovereign credential in an identity wallet?
Well, it's the whole concept that comes with it, and the wallet that actually holds then the credential that you're basically being issued to, obviously means that it's in the world of self-sovereign. So you control what you're doing with that thing, and it's not something that can be taken away from you because you're in possession of this. Obviously, we are now talking about when it comes to the real applications that we now see happening, the SSI implementations of governments, or I would say SSI-like implementations. If you want to follow all the principles, it can never be government-issued IDs. But let's say it's something that is very close to an SSI implementation solution, like what's happening in Switzerland with the Swiss EID initiative now that is currently being developed as a law, as a law that should be go into place into 2025. Bases itself a lot on the principles of SSI. That's basically what we can then basically see as the advantage. If you hold in your wallet your identity card in a digital way, as Daniel said before, in a digital copy, basically digital twin of the physical card. Once you have been issued that thing, you're in control, and that's I guess the main advantage.
Please, Daniel, follow.
And I think, if I may add to that, also new methods and mechanisms can actually help to preserve the privacy of the holder throughout the life cycle of these credentials. And while they are presented, zero knowledge proof and other capabilities can really help you to be saving on data, so minimalistic on data sharing. So you can, for example, when you enter a club, you can actually just demonstrate that you're 18 years old and you're actually able to consume alcohol or whatever kind of services. And you can do that in the physical world, but you can also do that in some way in the digital world. So being able to demonstrate that you have the credential that is needed for a certain transaction or interaction in a very privacy-preserving way, I think is the core one of the pieces of the core value of what self-sovereign identity promises.
Yeah. And also, I think the combination of credentials. I mean, it's not just about one identity credential in your wallet. It's about having all these credentials together in one wallet. So having an ID, your driver's license, your master's student diploma, your whatever else credentials that eventually you will hold in your wallet. And then the fact that you can combine the content of these credentials, the attributes of these credentials in the meaningful way for a given use case, which is what we did with the University of Zurich student wallet project, that you can apply for a job, you use some of your credentials from the student ID, i.e. potentially your birth date and the name, and then the grades from your master diploma, and you can, through a job application process, share exactly that sort of minimal set of data that is needed for that very particular use case that you're actually talking to. And that combination of using the different credential content details is what also is very powerful in the future.
Yeah, I would agree completely. And I would add too, perhaps, that verifiable credentials present a very different way of managing our online identities. So instead of giving all of our data to third-party platforms in order to have an identity online, an account with our username and our password, we're giving up all of our data to these big platforms so that they can know who they are, but then they have access to our data and they're monetizing it to provide advertising to us. But verifiable credentials turns that equation in reverse, and we control all of our data, and we decide who we share it with and when and how. The example, I forget which one of you was using, where you can prove who you are and what age you are without giving up your address and your birth date and other information that nobody needs. And you keep control of that data privately yourself. Go ahead, Daniel.
I mean, the example of Daniel's credential of University of Zurich also kind of highlights the importance of interoperability, because when you kind of move towards Singapore or somewhere else in the world, you need to make sure that in some way this credential can be used in context with what we are trying to do. So applying for a job or whatever, I think that kind of highlights the importance of interoperability across ecosystems, interoperability across borders, interoperability across various aspects of using technology and using these concepts as part of technology. So I think it is vitally important that bodies like DDoS help to actually drive that consensus, not only nationally as we do it or focus on today, but also internationally, and get that input from a global perspective on what are the key standards that we can reuse. Switzerland has a great history of doing Swiss type of standards, and I can fully understand that, because it creates value for the local kind of ecosystem and environment, and allows organizations to capture more value. But on the other side, it really challenges the way how these ecosystems work in the digital world, or should work in the digital world today.
Yeah, and let's stay on that topic of interoperability for a minute. So we've talked about the different building blocks of self-sovereign identity. One is the decentralized identifier, which represents either an issuer or a holder of a credential or a verifier. And we've talked about the verifiable credential. And both of those pieces of data need to have standards so that they can be used to communicate between the different parties. One of those standards bodies that Daniel just mentioned is the W3C. They register decentralized identifier methods. And I just checked this morning, I think there are 30 or 40 different decentralized identifier methods registered already, and this industry is brand new. And some of them, many of them point their decentralized identifiers to the Ethereum blockchain. There are some for Bitcoin, there's Cardano, there's Cosmos. There are a lot on Hyperledger, which is a private permissioned blockchain. And so one of the challenges that I think the industry needs to grapple with is exactly to Daniel's point. If you have an EID that's issued in Switzerland, but you want to travel to Singapore, how can you ensure that interoperability? How do you ensure that a credential I have here, like my physical passport, can be used to cross borders? And so I don't know, would either of you like to comment on some of the standards work that's taking place to ensure that interoperability and what the industry is doing to overcome that problem?
I mean, ultimately, I'm definitely not the right person to go into the standards discussions in detail about what standards are the right ones and the wrong ones. But what I observe when it comes to high level, the discussions and W3C's discussions around VCs and how long that took to get to a version 1 of a standard, this is exactly the problem. That's where I think is a big challenge for this concept of self-sovereign identity, or anything that is dependent on global standards for it to work, and the ecosystems to build around these things. And to Daniel's point from before, Switzerland is famous for its federalistic system, its power to the people. The people are the highest sovereign when it comes to the democracy we are having here. But that also means that the decisions are always at the bottom, and in the context of the Swiss government set up, a commune in Switzerland has much more power than the Swiss government in Bern. And that's seen in the context of the work we are doing when it comes to standardization of what is everyday use cases for governments, like a citizen certificate of residence, or a certificate of a credit record extract, or criminal record extracts. All these credentials that are government issued, it's a huge challenge just to get them right from a normative perspective when it comes to what is this document actually saying about a person, and in each village it says the same thing about that person. And that's a work that we just started with the Swiss government now to normalize across 2,500 Swiss cities and communes a standard for certificate of residence, for instance. And that has nothing to do with self-sovereign identity, but that is needed in order for self-sovereign identity eventually to work, because these records are a crucial piece to the use cases that eventually will be created around self-sovereign identity ecosystems, to make them actually interesting for the citizens to use. And that's the end goal. It has to be usable in everyday life. It has to be meaningful in everyday life. Otherwise, concepts like this will never fly. And so there's many different interoperability challenges, the technical ones, what we just discussed, and the ones about the use cases and the credentials that are needed for these use cases. Huge challenges, huge interesting opportunities to overcome, but I guess it will take quite some time until we get there.
Yeah, and I think, just as you were talking, I think self-sovereign identity really provides a unique opportunity for the communities to come together. So thinking about the blockchain community and thinking about the devs the brilliant devs that are part of your community today, and at the same point in time, sometimes not, going deep into how the real world works today, and therefore missing how a meaningful bridge can be built into an optimized future aligned with our principles and values as a community. I think it creates a tremendous opportunity to come together and solve, not only with the blockchain ecosystem itself kind of thriving on some of these technological innovations, but also kind of finding a way to come together with how the world works today and how we can truly create impact with use cases that are human-centered and that create value for organizations and that create value for societies and governments in privacy-preserving ways, and aligned with these principles that I think Christopher Allen very well put out, kind of walk the journey together. And for me, this is clear that we need to do this together. There cannot be just dev on the blockchain community side and then there's suddenly mass adoption in the real world. I think it really needs that strong balance. And I think self-sovereign identity, or the concepts around it, and that convergence of the world really creates an opportunity for the convergence of these worlds.
Yeah, I think that makes a lot of sense. And you hit on something that reminded me of a distinction I wanted to draw, where you talked about privacy preserving. That's a fundamental value of self-sovereign identity. And it comes back to that building block of verifiable credential, and how does it preserve the holder's privacy. And can sometimes be confusion between an NFT and a verifiable credential, because they can do similar things, but a verifiable credential is not a flavor of an NFT. It's different in a couple of ways, and privacy there is the key. So with an NFT, all of the data about that NFT is stored on-chain somewhere, and that's fantastic. That's allowed incredibly robust and exciting use cases and economies and tokenomics that we've seen just exploding across the blockchain industry. And all of that data is stored on-chain. With a verifiable credential, none of the data is stored on-chain. So that's where the privacy comes in. Trying to use NFTs for identity use cases can be very dangerous, because it would involve putting all of the individual's identity data into an NFT and recording it on-chain immutably forever. And there was just a really interesting presentation earlier about not just encrypting data for today. So you could have the best encryption in the world for my identity data that you put on-chain in an NFT today, but it's got to last forever, because that's the beauty of a blockchain. The data is there immutably forever. And so putting identity data into an NFT, even in an encrypted format, and storing it on-chain forever can be very dangerous. So while NFTs have fantastic use cases, what a verifiable credential does is take all of that private data off-chain, and it's issued directly from the issuer to the holder, but it can be verified using the blockchain. And that's where the interoperability and the global standards come from. And Danny, you mentioned the University of Zurich and ProSivi's use case briefly, but I think that's a fantastic example of the benefits that self-sovereign identity can bring. Could you elaborate a little bit more on what you're doing there and the benefits it's bringing?
Yeah, the work that we historically through different channels, and I don't know if Claudio is here, but we've been working with Claudio Tesone and the team of the Blockchain Center since the beginning of the development of blockchain here in Zurich with TrustSquare and so forth. And we always said we should be doing something along the lines of a student wallet, a student ID, and obviously the precursor was this the timestamping solutions that were going around in Switzerland for a while now, where you basically put a timestamp, a fingerprint of a student's record, a student diploma on a blockchain. But that then changed since the introduction of self-sovereign identity in the real world, especially with the Swiss government now looking down the concepts of self-sovereign identity for the future EID in Switzerland. That really gave it a boost, and we developed a self-sovereign identity platform at the company, and based on Hyperledger Indy, and we basically continued the discussion. And last summer we said, let's try out now this idea of a university student wallet that contains a digital version of a student card, which basically is exactly the copy of the Zurich University student card that we created as a verifiable credential, and then think through a couple of use cases that could come with such a wallet. And that's what we've done over the last 9 months. We have developed a system that across the university 100 students were using. So they got issued a digital version of their student card into a wallet of the University of Zurich. Then we basically developed a first use case around access management to a student event where the student could authenticate them, or rather authorize themselves to enter the event by scanning a QR code and basically just share basic information about him to be checked on a guest list. That was obviously a very simple use case, but that's a very powerful one because that can illustrate our use case as well, where you just show your with a zero knowledge proof you're above 18, and that's it. And so that's what we've done to showcase that thing, what you can do with an electronic way of identification in the real world. And then we said, okay, well, that's good, but let's think this a little bit further. We had a student event in September last year where we did some brainstorming. We did a demonstration of the wallet, came through with quite a lot of good ideas that we didn't think of, and we picked some of them, tried to develop them into real applications again. And obviously everything is proof of concept. This is not a live system. I have to obviously say that very clearly. But we then came up with the idea of a job application, and together with Swisscom and their HR process for applications, we developed a showcase of if you have your digital master diploma, which we also created as verifiable credentials, both for science and arts students, and always the real students with the real certificates were using this. We processed basically then that job application proof of concept idea into a real application, and we just last week demonstrated that at the university at an event with the students, plus also some of the senior people from the university. And so we did really try to get these things to life, these ideas of verifiable credentials, how they look like. Our credo is always that we want to make them as intuitive as possible, so everything we are doing is typically just richly a visual copy of the physical world, that card of the university, so it just looks like the card. It's the same design, it's the same logos, the same colors, and the same thing for the master diplomas. There is, to the topic of standards again, there's no standard for a master diploma, how that looks like. It's not even in Switzerland universally standardized how a university issues a master diploma, and that's just not heard of, and let alone internationally. And so that's another thing we then started realizing, okay, we do this, we showcase this, but obviously there's a challenge. If you want to use that, and the University of Singapore, to come back to that example, can then scan the schema from the University of Zurich and recognize the content of that verifiable credential, that's not going to work. So there's a lot of work involved in standardizing academic credentials in the future. But yes, I mean, it's a good example. We had As I said, we have about 100 students involved in all of this. We will publish a report about all of this. We'll do a public demonstration probably next month at the Swiss participation meeting of the Swiss government. And yeah, really cool use case. It's not something super unique. The university use case in the context of SSI is globally one of the leading ones. That's clear. That it's where the innovation comes from. The universities they see, and obviously a place like University of Zurich with the blockchain center is it's obvious that something like this should be also tried here. But it's actually the first time I think that it was really so broadly implemented and so broadly demonstrated.
Yeah, that's a fantastic example. And I wanted to highlight one thing you said. So the decentralized identifier of the University of Zurich, who's issuing the diplomas, is being stored in a private permissioned Hyperledger Indy ledger.
Yep.
And the idea is that as this ecosystem grows, that credential could be combined with credentials issued by others. So maybe there's another credential issued by an issuer who uses Ethereum as the register for the decentralized identifier of the issuers. Maybe someone else is using Bitcoin as the ledger to record the decentralized identifier. And I've heard some people in the US government who are working on self-sovereign identity applications, they're not even thinking to use blockchains as their ledger for decentralized identifiers. They're thinking to use a US government website. So as this ecosystem grows, yeah, I think I heard someone roll their eyes. It's typical, right, of the US government. As this ecosystem grows, we need a way to combine these credentials just as seamlessly as we use the internet today. I mean, you can use any web browser and access any website. So I think that's one of the interoperability and adoption challenges that the industry is working towards.
And maybe if I can mention, as you also spoke about experimentation, currently the Swiss Bund, and maybe just a step back, the Swiss Confederation is working very collaboratively and participatory on the creation of the EID law, as well as on the creation of the selection of the architecture that is being used for deploying that trust infrastructure for Switzerland. On one side, it's interesting because you as a community are invited to actually experiment with them and learn with them as they are looking for new ways of actually driving how should I say, maturity into the various aspects of the technology, the governance, the standards, as well as the skills and capabilities of the people involved, and the departments involved, and also the civil society, and also the organizations that ultimately will benefit from a trust infrastructure like this, because it will not only hold the aspects of EID, but it will also allow organizations and individuals to issue verifiable credentials into such a trust infrastructure, which runs on the basis of SSI principles. So what is going to be important is that experimentation is going to be driven by as many parties as possible. So if you go to the government website, you will find a way to interact with their sandbox. We as DDoS, we started like 1.5 years ago to deploy such a sandbox and have our members and associate experts to learn and experiment with it. But it also is an opportunity for ecosystems like yours that you can contribute to the further development of that architecture and the further development of how the technology is going to be applied in the future. So on this notion, I just want to mention quickly that we recently had a post on the ARF. The ARF is the architecture reference framework that has been issued by the European Commission. So as you can see, there are many initiatives across the globe, whether it's New Zealand, whether it's Canada, whether it's the EU, whether it's in Singapore, whether it's in Switzerland. And you can see that all of these initiatives, by the way, also in third world countries or global south countries, and all of these countries have different needs and aspects that they want to drive into these ecosystems in terms of how privacy preserving should they be, how strong of cryptographic methods should be used, etc. So we issued a blog post on the ARF that was published by the European Commission, and we invite you also to kind of look at that and be aware of what's going on in the real world in self-sovereign identity, because it's so important that the aspects of the broad stakeholder base is going to be finding its way into that consensus. I wanted to highlight that.
Excellent point. Excellent point. And I think we have time for a question from the audience. I'm getting a little bit of a mixed message here, but all right. Can we take
Thank you very much. I just want to say thank you very much for the conversation. Great job, Alison, moderating everything.
Hello.
We have time for questions. We have time for interaction and so on and so forth. I have a couple questions myself, but I throw it out to the audience immediately. Yes, sir, right here. We have a mic already over here. Good. Super. I'm told to stand in the middle of the stage. Yes. Good. Turn on the microphone for the gentleman, please.
I can repeat.
We can hear them.
I would like to
there
take
we go.
more like practical attitude and probably more like, I was recently in Israel. And they have pretty much automated their public transport system. So if you miss to get a ticket for the transport system at the airport, as an external, you have no chance to get permission. So I had to write black. How do you say that? So I could think about that why is not this identity thing connected to people being on travel, like helping them to get there what they need as a foundation at their destinations they're going to have stuff like communication, insurance, cash flow, and all this kind of stuff, and really take care for these people, because there's how many Americans don't have a passport and so forth. So maybe we can concentrate on the ones being in the flow and try to establish for them, maybe temporarily, at least for the time of the travel, some support for identity management.
So is it okay if I take it, or at least to start? So I think it's absolutely vital what you're saying, and that is maybe one of the misconceptions of or the problems that we are facing. So how do we drive the adoption for the traveler? How do we ensure that the services can actually be designed in a way so they use verifiable credentials as part of everyday life, whether it's traveling in abroad, or whether it's actually looking at your health record, or whether it's actually looking at whatever kind of interaction you need to do within your day-to-day life. And the beauty of verifiable credentials as they would be adopted is that, and Danny mentioned it earlier, that combination of multiple verifiable credentials into something that makes sense, or that something that would be available to a smart contract to actually execute on. So you could actually think about a frictionless future of buying a house, because all of the proofs could be obtained in a digital way, and could automatically be processed alongside the use case of buying the house and all of the regulatory aspects of what needs to get done to execute on that transaction. So you're absolutely spot on. And I think my colleagues will definitely have also a word on that, or certainly on adoption. Yeah.
I completely agree. And the only thing I would add is the importance of verifiable credentials, because as we create that frictionless experience that you were asking for and Daniel referenced, the thing to avoid is feeding all of our data about everything that we're doing, every movement we're taking, everything that we're buying to some centralized entity, whether it's a government or a company. We don't want to give all of our data away and allow ourselves to be monitored with every single thing that we're doing. So how do you create that frictionless, smooth, easy digital experience and preserve our independent privacy? And verifiable credentials really are a huge step towards exactly that.
That is the holy grail. One more question, sir, or two, and then we move to the next speaker. Okay, up here then.
Hey, thanks. Not sure if you were like following recent research and like what community is also building with decentralized societies. Yeah, so basically it's more like a concept of rather having identity system built based on verifiable credentials, right? You have like more sociocracy, right? Soulbound tokens and this kind of mechanisms. Yeah, it's open. It opens basically like really like the doors to more decentralization in that matter, right? Because like one of the problems with verifiable credentials is that an authority of like providing some credential itself. Yeah, so curious to hear your thoughts and if you thought you have anything experience about that.
Yeah, I remember from the discussions back in the time at when I was regularly in Prague, and the discussion around Liberland, I think it was at the time, that was going in the direction of a decentralized, totally decentralized country approach. And at the time also the discussion around real self-sovereign identities in the case of you create your identity yourself and you choose who actually attests for whatever identity element that you have. I mean, these are all the great concepts. These are all the things that also motivated me to really get engaged with all of this. Unfortunately, the reality is something that is not quite ready for something like this yet. I think we are struggling, and in Switzerland specifically, since more than 10 years now, to get a government-issued digital identity to use in everyday life as it is now. And to go to that next step, I think society, at least here in Switzerland, we're just not there yet, unfortunately. But it's obviously the end game and the end state. But I think it's just not the right time just yet. But if I can make a last comment, I don't know if it says finished here, but if you're interested in this topic, I would like to make a quick announcement about the Decentralized Identity Unconference that will take place here in Zurich on 7th to 9th of June. It's going to be a 3-day event on this topic of self-sovereign identity, centralized identities, in the format of what some of you might know as the Internet Identity Workshop in California that takes place since 18 years. That's really where this topic is being discussed at the real detail level, and at such a concept and any other technical concepts and any other philosophical concepts around identity can take place in an unconference fashion. That means it's not like a conference where you go and sit and listen to somebody in front of you, but where you actively create the agenda by giving input in the morning, and then teams are formed around the topic, and then you can actually discuss these things in great detail. Unfortunately, that's not possible here today, but if you're interested, if you go to the diceeurope.org website, you can see the details around that conference. I highly recommend it. It's here in Zurich at Trust Square. It's the first edition in Europe, and we're super excited together with DDoS to organize this.
Super. Very, very good. Thanks for the questions. Thanks for the great discussion. We'll wrap things up there.
Super.
And move on to the next speaker.
Thank you, guys.
Always the Americans.
Okay. So, yeah, I again am told to stand in the middle of the stage. Let me get my timing, my location precisely. I go to precision because I believe the next topic is going to be very precise around decentralized storage. And if I'm not mistaken, the title is something about decentralized storage in 2 minutes or something like that. Now, I'm wearing a Swiss watch today. I may be actually timing this, this entire presentation. If it goes over by 10, 15 seconds, well, we'll see what happens. Anyway, Gerrit, it's over to you.
Yeah, thanks so much. Hey, everybody. Yeah, my name's Gerrit. I work on a fund called Permanent Ventures, and we're just super motivated to invest in a lot of decentralized infrastructure projects, which are set up to exist for a very long time, with proper token incentives and so on. But yeah, today I just wanted to show a really quick demo of one of our portfolio companies, which makes it super easy to archive data permanently on a network called Arweave. And the project in particular is called Bundler, and they act as like a decentralized API where you can upload data super easily, pay in a variety of currencies, and there. So yeah, it's you can show my screen. And I don't use Windows. Yeah, I'll do that. Thanks. Let's make it mirror. All right, and yeah, one of the big problems just wanted to address is, there's like, in the last NFT bull market, there was about $50 million worth of NFT metadata that was stored on centralized hosting providers that eventually resulted in dead links. And majority of the links on the internet that have ever been posted so far are now dead. So this is actually like a big problem in the internet in general, but when you're trying to sell something which is supposed to exist forever, for instance, like an NFT, or there's a bunch of other use cases where it's very worthwhile to have your data stored permanently, yeah, you really want some good assurances of that. So the Arweave network does a good job of providing those. We can dive a little bit into the economics after just like a quick demo. But like, for example, either in simple JS or just through a CLI, you can upload something. So for instance, this is just uploading like a picture of the Rosetta Stone. You just send the command, it's done. And now you can access it through any like Arweave gateway, which you can self-host or use a public one. And then there it is. So that's proven decentralized storage in a few seconds. A bit more background on the economics. Basically, Arweave is assuming that the cost of storage will go down by, on average, like 0.5% per year, which it has done like much more than that since the beginning of modern storage, digital storage. Yeah, and basically, when you send a transaction to the network, most of the data ends up going into an endowment. And this endowment is used to pay out to miners whenever a piece of data on the network is detected to have become rare. It puts out an extra bounty, which incentivizes miners to prove access to that piece of data such that it's not rare anymore. Yeah, so if you want more info about this page in particular, yeah, you can just scan that QR code, go there, and yeah, learn all about it. But yeah, that's my quick little demo. Thanks very much.
Wow. Good job. That was pretty close. That was pretty close. I would take one question from the audience, if anybody has one. If not, I have a question for you. No? Yes, sir?
Yeah.
Thank you. So, I'm wondering your opinion about it's more like a philosophical question, more meta question. I believe, yeah, storage is essential, of course, in the decentralized world, but it seems that the Degens don't agree with that.
Sorry, I didn't hear.
The Degens, like the crypto crowd that's just chasing the multiple of profits.
Yes, yes.
And how do you navigate these waters?
Yeah, definitely. So this project in particular, like the founding team is super missionary. Like they don't really care about making a lot of money. They just really care about the world having a permanent data archive. So it's kind of like on the side of where all of the, you said like degens play. It's not really something that will attract those or like be some like super, amazingly lucrative, Ponzi-esque, pump-fundamentals driven scheme. But it's just a protocol which I really believe, and we really believe at our fund, that it's just going to continue to provide value to all of their networks, and just slowly, surely rise in popularity. And yeah, most NFT marketplaces now publish data through the Arweave network, most of them using Bundler as well. Yeah, so it's just, yeah.
Yeah, thank you. Yeah. By the way, I wasn't so much meaning also about profits in general, but in terms of exactly when you mention NFTs,
yeah,
we know so many stories where the NFTs are still stored on Amazon servers.
Exactly.
And it's like this, it feels like within the community, there's not yet the awareness about the importance of decentralized storage, and that this kind of slows down the adoption.
Exactly, exactly. So that's why I'm like here saying this stuff right now.
All right, thank you.
All right, thank you very much. Quick question to the audience out here. If you're quick, very quick, shout it out.
There's a lot of projects creating self-sovereign infrastructure like Swarm, Stars, Arweave. How can these projects work together? They all have different tokens.
How can you work together?
Yeah, absolutely.
Quick answer?
I mean, Arweave really specializes in decentralized storage. Of course, there's also like a smart contract execution layer, and Filecoin also recently published their Filecoin virtual machine. So theoretically, in the future, you'll be able to make smart contracts there, which also provides some degree of permanence, which will be very interesting. But until now, this is the only protocol which supports like permanent or like promises permanent data storage and provides strong guarantees of that. But yeah, the way that projects can collaborate, and a lot of them do already, is like, for instance, through another project called Kive Network. The chain state of many other networks are archived onto Arweave in a way that's verifiable through their own network. Yeah, so it's mainly just like using it as a backbone for storage is like the best way that they can collaborate at the moment. I think.
Lots of more work to do.
Yeah.
Thank you very much.
Definitely.
Garrett, super.
Yeah. Thanks.
You were quick, very Swiss, very precise. That's good. A round of applause for Garrett.
Thanks.
And from there we move on directly to extractability from ZK Snarks.
Good, how are you?
With Ignacio. You're up right now, Ignacio. Step right up. Over to you. Get your questions ready. There you go. You need a clicker?
Yeah. You need to activate this as well?
That's up to you.
Yeah, sorry.
Mm-hmm.
Thanks. Right here. All right, cool. All right, can everyone hear me? Good. All right, so I'm Ignacio. I'm with the Nethermind cryptography research team. And today we're going to talk about an important property of certain proof systems, in particular zero-knowledge proof systems. Just so we make sure that we all understand what we're talking about, so what are ZK snarks? So ZK snarks are special proof systems for relations. And we recall very quickly that very formally a relation is a subset of strings, binary strings. And when you have a relation, you have an associated language, which is essentially the set of strings such that there exists another string such that the pair is in the relation. You should really think about these as being instances and witnesses for that instance. And we are concerned with proof systems, snarks, that are for NP relations. So these are the languages such that if I give you the instance and the witness, you can actually decide whether the pair is in the relation in polynomial time very efficiently. However, finding such a witness for a given instance might be extremely difficult. And the point of the prover is to show to a verifier that it has the knowledge of that witness. This is very important. So what does this acronym stand for? So ZK is zero knowledge. Essentially what that says is that, very informally, when the prover gives its proof to the verifier, that it knows this witness, the verifier learns nothing except for the fact that the prover knows that witness. The S stands for succinct, which very simply says that the proof is short. Formally, the proof should be sublinear in the size of the witness. Non-interactive, this is the N. It means that the prover only sends one message to the verifier, and the verifier then decides to accept or not. This unique message that the prover sends usually is called a transcript. And AR stands for arguments, meaning that this proof system should be sound, which means that whenever you have an instance that is not in the language, the prover should absolutely not be able to convince the verifier that it is. And what we ask here is that this property only holds against, again, computationally bounded provers, essentially. So if you're very observant, you notice that we're missing the K. So what is the K for? And that stands for knowledge. Okay, so what does that mean? So here we have an adversary. It has some public parameters for this proof system. It has some reference strings, so we're in the trusted setup case. And it has access to some hash function or an oracle. And it outputs an instance and a proof transcript. Okay, So let's just assume that this proof transcript causes verifier to accept with like some non-negligible probability. Then what we ask is that essentially there exists an efficient algorithm which is going to output a witness for that particular instance. In some sense, the adversary had to know the witness because it could just run this efficient algorithm itself. So this is a property that we usually call knowledge soundness. It's a very strong property. It usually implies soundness, and we only require that there's this efficient algorithm extracting witnesses for when the adversary can convince the verifier with non-negligible probability. Okay. So what they do not tell you in this definition is what the adversary really knows. So somehow this definition assumes that the adversary is isolated. It has only access to the proof system's parameters. Is that the case in the real world? Absolutely not. In the real world, what the adversary has, like if your proof system is running, for example, on a public blockchain, the adversary not only has access to the proof system's public parameters, it also has access to a lot of instances of people proving their own statements and the actual proofs of these statements. So what if the adversary sees all of these proofs and then says, well, here is a way to kind of modify them or combine them to prove a statement for which I don't know the witness? This is absolutely not covered by the knowledge soundness definition. So we need, essentially, when we deploy proof systems publicly, some stronger security guarantees. So why does that matter, for example? So let's just take this example right here, where this dog, account A, wants to create a coin and send it to account B. What it does, it sends it to a mixer, and then the account B should claim that coin by essentially showing that it knows a secret. And usually we do this with a proof system, with a ZK snark. But now, here's this very sneaky cat, and it sees the proof instance by account B. If your ZK snark doesn't satisfy this stronger security guarantee, what can happen is that this cat sees the proof, it modifies it into a proof for the statement that the coin should go to its account itself, and it doesn't have to know a witness necessarily for this to happen. So this is quite a serious problem. So how do we prevent this? So we need to show that the adversary cannot turn the proof it sees into proofs for statements without knowing a witness. Even if it sees proofs, even if it has access to some proofs, it cannot turn them into proofs for its own statements without knowing a witness. So there are many ways to do this. You could design your proof systems to be like application-specific design, where you add, for example, an encryption of the witness or a one-time signature, and this comes at some loss of efficiency, or you could use actually a snark that is already simulation extractable. And what that means is that even if you give the adversary access to simulated proofs for any statement, true and false statements, it cannot come up with a proof for a false statement or for a statement without knowing a witness, because we can still extract it. So simulation extractability is this stronger extractability guarantee in which even if we give the adversary access to a simulator for false and true statements, it still cannot come up with its own proof without knowing a witness. So how do we show this? So this is actually work by Ganesh, Koshakhlak, Kollweiss, Niculescu, and Zions in 2021, and very recent work by Dao and Grubbs, which essentially reduces the simulation extractability property to proving three main properties. The first one is K-unique response, which is essentially a measure of how much freedom you have in answering the verifier's challenges. The second one is, in the trusted setup, K-prime rewind knowledge soundness, which, as you will see, is some sort of special soundness, if you're familiar with this term, for non-interactive protocols. In the transparent setup, you only need knowledge soundness of the non-interactive protocol. And the last property is something called programmable zero knowledge, which in the trusted setup case should also be trapdoorless. And some mild conditions on when these properties occur, especially in your proof system. what these people show is that this implies simulation extractability and this stronger knowledge extractability guarantee. And this is somehow easy. You show essentially that if you have an adversary that breaks simulation extractability, then it can break essentially one of these three properties, like especially knowledge soundness and unique response. So what I propose is that we go through what these properties mean exactly, and then we look at two simple examples to show how this is applied and how we can essentially prove simulation extractability of many, many deployed snarks, which is good news. So I have some positive results, which is kind of rare, both in computer science and in mathematics. So let's just go with k-unique response. So we consider 2 mu plus 1 move protocol. So the prover always sends the first and the last message, and then the verifier sends challenges for each of these messages except the last one. So here's an interaction between a prover and a verifier, and here, let's just say the verifier accepts. So usually the zero-knowledge snarks, they are constructed in a way that you take this interactive protocol and you make it non-interactive by using something which is called the Fiat-Shamir transformation, or the Fiat-Shamir heuristic, in which instead of the verifier sampling, for example, uniformly the challenges, what you do is that you hash the prover messages. And to get the second challenge, you hash the first 3 messages, and so on and so forth. So when we use the Fiat-Shamir transform, usually what we say is that the transcript consisting of the prover messages is accepting. Why don't we include the verifier messages? It's because we can always recompute them by hashing. Okay, so here's another prover, P prime, could be the same, and it produces another transcript. The k first messages are exactly the same as the previous transcript, but the last ones can potentially be different. So what the k-unique response tells you is that if the last messages are different, then this new transcript cannot also be accepting. It has to be rejected. And what you can summarize this by saying that the probability of having 2 accepting transcripts, which are different, because some of the last messages are different, but the k first messages are the same, is negligible. You cannot have that. And here you say, okay, but how can the prover messages be different if the challenges are obtained by hashing, so the challenges should be the same? But what I'm not telling you is that you can program the kth challenge. The adversary has the possibility of programming the kth challenge. Even in that case, having 2 transcripts that are different but agree on the first k messages is impossible. All right? What about this rewind knowledge soundness that we need in a transparent case? So here's a running instance of the protocol where the dots represent prover messages and the edges represent verifier messages. In particular, this one is accepting. The verifier accepts this instance. So what I can do is I can rewind to the point where shown in the screen, and I can actually choose other challenges to see what the prover does, essentially. And here, when I chose this other challenge, C1 tilde, the transcript was actually accepted at the end. But when I chose C2 tilde, then the transcript was rejected. And in fact, I ignore those branches where the verifier rejects the proof. So in this way, I can build this tree of transcripts where I rewind to the point which is of interest to me, and I choose different challenges. So what we ask is that when we've built this tree, there also exists an efficient algorithm which looks at this tree and says, here's a witness for that instance. And in fact, here I've represented a tree where the rewind happens only at one point, but the property gives you freedom of choosing different rewind points and many, many different rewind instances. It's just that in the protocols, when you try to prove it, many times you end up with trees that have this form. Okay, and the programmable zero knowledge is actually just a flavor of zero knowledge. If you remember, like, zero knowledge property is essentially saying you have a simulator that can simulate proof transcripts, and they are identically distributed to the ones an honest prover would generate when proving a statement. And the programmable zero knowledge property says exactly the same thing, except that the simulator is allowed to program the k prime prime challenge. Okay? In the trusted case, it also has to do so without a trapdoor. But let's just go over that. So here is an example in the trusted setup. So this is the Plonk proving system. So essentially, what happens in Plonk is you have an arithmetic circuit, and you try to encode this circuit with polynomials where you interpolate they have fan-in 2 and fan-out 1, so you interpolate the left and right wires of inputs with 2 polynomials, and you interpolate the output wires with another polynomial. And the prover is supposed to send that to the verifier, and then the verifier and the prover should essentially interact with some challenges, and in the end, the prover should send this quotient polynomial t, at which point the verifier sends an evaluation challenge, which is called z, and the prover should respond with the evaluations of all the polynomials together with opening proofs. So you should think about these commitments as KZG commitments. And these openings are the openings in the KZG commitment scheme. So why is that unique response? So the point is that once you've chosen the reference string, once you've chosen a polynomial and an evaluation point, the KZG opening scheme is completely deterministic. You cannot do anything else. So once you've chosen all the messages up until the point where the evaluation point is chosen, you cannot have 2 different accepting transcripts. They will be the same after that. So this is essentially given for free by the property of evaluation binding of the KZG commitment scheme. So why is it rewind knowledge soundness? It's a simple little trick where essentially we're going to rewind to the evaluation point, and we're going to choose a different evaluation point. And the prover is going to respond with the evaluations of the polynomials at different points. And so, because these polynomials have essentially finite degree, when we get enough points, we are going to be able to interpolate and recover them. So interpolation is essentially an algorithm that allows you, given enough evaluation points of a polynomial, essentially 1 more than its degree, it allows you to reconstruct the entire polynomial. Okay? And finally, why is it programmable zero knowledge? So the point is here, the simulator is going to do something kind of counterproductive. It's going to choose the polynomials it should commit at first completely at random. So this is rubbish. It should give something that is, it should encode nothing about the arithmetic circuit. So it should, in particular, it shouldn't verify any constraint of the Plonk arithmetization. So what happens is, as the prover and the verifier interact, the quotient polynomial, which should be a low-degree polynomial, is going to be some very high-degree polynomial. It's not going to satisfy anything. So how do we kind of trick the verifier into still thinking that it's a low-degree polynomial? Well, we choose the evaluation point in advance, because the simulator can program that point. And what we do when we know what the point is going to be is, instead of committing to the quotient polynomial, which is not a polynomial at all, or not a low-degree polynomial, we commit to another low-degree polynomial, which agrees on the evaluation of the particular point we've chosen. And when we do that, essentially the verifier is going to accept this proof just because the opening of the KZG opening is going to be valid. And we can do that precisely because we can choose the evaluation point before choosing what the commitment to T is going to be. So here, very high level, we've shown that Plonk satisfies the 3 properties that it needs to be simulation extractable, which means that if you want to use Plonk as a public proof system, you at least have the guarantee that people cannot take proofs they see on your public blockchain, for example, and turn them into proofs for their own statements without knowing a witness. All right? So let's look at the transparent example. So let's look at the ETH Start protocol, for example. And here it's very similar. So the prover is supposed to send commitments to some polynomials, some witness polynomials. And the verifier at some point sends this Q point, which is also supposed to be an evaluation point. And the decision process is such that supposedly the the evaluations of the witness polynomials that the verifier sent are supposed to satisfy some constraint equation, which is given by this equation star. It's not important what it encodes, it's supposed to satisfy this equation. And how do we check that the evaluations of these polynomials are correct with the commitments? Here the commitments are not KZG, they're actually Merkle commitments. So you put the evaluations of the polynomials on the leaves of a Merkle tree, and you hash that and you get a root, and that's your commitment to your polynomial. So the way that ETH-Stark enforces that the evaluations are correct is actually applying the FRI low degree testing to this function g, which essentially is a low degree polynomial if and only if the witness polynomials are low degree, and furthermore they evaluate to the alphas and the betas at the points at the denominator. So why is this protocol k-unique response? And here the point is that we're going to wait until very, very late in the protocol when we open the points in Fry. This is done by essentially showing a path to the Merkle root of the Merkle tree you've committed your polynomial with. And this is if your hash function satisfies some obvious properties like, let's say, collision resistance or preimage resistance. This is going to be deterministic in some sense. Like it's going to be extremely hard for a prover to kind of cheat you into thinking that it's opened correctly because it has to find essentially collisions in the hash or like preimages in the hash. And why is it programmable zero knowledge? So here the technique is essentially similar to what we had for Planck, is that the simulator is going to choose the polynomials completely at random. So again, this is bad. Usually it won't satisfy the equation star at all. So what you do is forget about the polynomials. Let's just choose alphas and betas such that the equation holds, the constraint equation. So why can we do that? For example, we can choose everything at random except one beta. And then the equation becomes linear in this last variable, and so we just solve for the last variable. So once we've done that, we claim that the polynomials we've committed to evaluate to the alphas and the betas. That's absolutely not true. So in general, this function g that we apply the low degree testing to is neither a polynomial, it's not of low degree. But what we can do is that we can, again, program the points where the Fry protocol is going to kind of ask to see evaluations of that function g. And we're going to interpolate g with a low degree polynomial over these points and engage in the low degree testing with that function instead. So that's a complicated way of saying that we know which points are going to be queried because we can program them. So with this additional knowledge, which we don't usually have, we can trick the verifier again into thinking that we have a correct function and that we satisfy all the necessary constraints, but we don't, essentially. So that's how the simulator is going to be able to produce transcripts for the proof. And so this shows that the ETH-Stark protocol is also simulation extractable and satisfy all the nice extractability properties that we talked about. And now, if you're very observant, you notice that, for example, in the Planck case, the way the protocol was set up mattered for how these properties were found. So KZG gave us like unique response. Then we had like to interpolate by choosing different evaluation points and so on. So the Planck protocol it mattered how it was set up for us to be able to prove these properties. But here in the ETH-Stark example, you kind of see that these properties were only dependent on the fact that we used the Fry protocol to test the low degreeness of this function. Like, it didn't really matter what happened before that point or after that point. Like, the only thing that mattered is that the low degree test or the evaluation test was the Fry protocol. So essentially what you can show or try to figure out is that you can generalize this for all Fry-based snarks. And when you have a Fry-based snark in which the decision process of the verifier is such that it accepts if and only if you have polynomials verifying a certain constraint equation, and the evaluations are checked using Fry. Again, you can use the same exact tricks and show that essentially this will also satisfy simulation extractability and this stronger simulation extractability guarantees. So what's been really positive, I think, is that essentially all your favorite snarks are simulation extractable, like Blanc, Marlin, Sonic, Bulletproof, Spartan, ETH Stark, Plonky 2, they've all been shown to be simulation extractable. So even Gross 16, in some weaker sense, it was also shown to be simulation extractable. So yeah, there it is. Thank you very much for your attention, and I hope you enjoyed this talk.
Fantastic. That's been very detailed, very in-depth. I'm sure we have some questions from the audience. The gentleman right here in the center is going to wait for a microphone before he asks his question, because there are thousands and millions of people watching online and they want to hear your question. Go ahead.
That's a lot of pressure.
No pressure, yeah.
Thank you for the presentation. Loved the way you explained it. It's quite a complex topic. I, as a developer myself, faced this problem quite recently, and like seeing this breakdown like that is awesome. My question is, do you see that actually as a developer building on top of ZK Starks, like should I actually care about that, or should the protocols itself always integrate simulation extractability or non-malleability inside of the, like when they design the protocol, so that I can just relax? Because right now we're building our own solution, we have to work around to potentially prevent simulation extractability, like malleability problems by hashing and doing some extra work. So what do you feel like about that?
Well, I mean, it depends, I guess, which proof system you're using. I mean, if you were lucky and it was in the list I said of the ones that were simulation extractable, hopefully you don't need to care that much about it. If it hasn't been shown, I think it is a potential risk that someone figures out a way to, as you said, modify this proof, like if you don't satisfy non-malleability, in which case I think it should be important to add, for example, a one-time signature or an encryption of the witness, as you said, to make sure that your protocol is non-malleable. Which proof system are you using in particular?
I mean, that's the problem for us. So we are generally quite flexible. So we're planning to use Noir and their underlying system, but it's the problem is we need to figure out if they actually are simulation extractable or not. And that's the problem. So I was wondering if it should be an industry standard where all the proof systems that are used should be by default simulation extractable, so that we can just have peace of mind.
I think that's true, especially if your proof system is a condition for you claiming, for example, your coins or some. If the non-malleability kind of the security of the funds in your protocol is dependent on the non-malleability of the proof system you're using, then I think absolutely yes.
And one more question, a quick one. Are all interactive Oracle proofs non-malleable or not? There was a result for that, or you don't know?
I think the simulation extractability definition applies to protocols that are non-interactive in some sense.
Okay, fair enough.
Yeah.
Thank you.
Thank you.
Super in-depth. You got more than one question into the block there. Someone else have a question? Yes? No? Maybe one question from my side. How long have you been working on the topic?
On this
yourself?
particular
Yes.
project, on this particular topic? It's been maybe 4 months.
Okay.
Yeah.
And where is it going from here?
So essentially, like when we started, we wanted to. So the simulation extractability of the Fry-based protocols wasn't very well understood and hadn't been kind of. So what we're planning on doing now is essentially publishing the write-up we have on this topic, and yeah, hopefully also work on some other deployed snarks, which maybe haven't been analyzed yet.
And are you cooperating with some other projects, teams on the topic?
I should mention that this work was supported in part by a grant from the 0xSpark Foundation, But at the moment, it's been only the Nethermind cryptography research team on this project.
Okay, super cool. If there's no other questions from the audience, going once, going twice. Zara, also no questions? No, okay. Very good. Thank you, Ignazio. Yeah. Super.
Thank you for
a round of applause. Okay. We have our next talk coming up in 5 minutes. If anybody wants to stand up, jump around, do calisthenics, so on and so forth, you're welcome to do so. Otherwise, I will stand here for a couple minutes and keep your attention. Our next talk is coming up in just 1 or 2 seconds. You're all set?
I'm just going to set out some swag. I have a minute, so yeah, I'll just put it.
Very cool.
Thank you.
Maybe if nobody else takes one, I'll take one.
Yeah. Are we putting these out or not? Yeah.
Is there anything special about you?
No, it's fine. I can also intro myself. I'm happy to. Let's have a look. Yes, I'm just gonna put out some DarkFi. Yeah.
Just like general.
More. So it's gonna be a little bit on like the kind of philosophy side, and then it will talk about the Lunarpunk. It will talk about DarkFi's smart contract architecture. So how we achieve generalizable programmability on DarkFi. Okay, nice. I will put just like a few of these. They're like an ask. Oh no! I don't want to eat them now. Hey, where do you get them? Okay. Yeah. Okay, and then.
Rachel Rose O'Leary has come to us from Lunarpunk and brought some very, very cool swag for all of those watching from home. I'm very sorry. You unfortunately don't have the chance to take something home with you today, but you can listen carefully. She's going to be talking about the why and the how of Lunarpunk, the Lunarpunk takeover, and I give it over to you. Thank you very much.
Thank you. So thanks very much for coming. We have some stickers here. I'll ask that after the talk.
Lots of
Please
stickers.
Come. Yeah, lots of stickers. Please come get some stickers. I have a quick question before I start, which is, how many people here have heard the term Lunarpunk used? Okay, and how many have heard of DarkFi? Okay, so there seems to be some kind of overlap, which is good, because I'm going to talk about both things. I'm going to start off speaking about our macro thesis, basically identifying what we see as some feedback loops that are driving value and users into anonymous systems and away from transparent systems. So this is a bit like our bull thesis for anonymity, but it's also fundamental to the kind of Lunarpunk meme space as being the means by which the Lunarpunk future kind of emerges. Then I will briefly speak about some more kind of deep philosophical questions, such as, you know, where are we going with this? Why are we exiting from the surveillance apparatus? What do we hope to gain from this this process of exit? And then in the latter half of the talk, I will give a presentation on DarkFi specifically. I will discuss our alpha testnet and explain how we achieve generalizable programmability on DarkFi. So it's 3 parts, and there's kind of a bit on more economics, then it will go into philosophy briefly, and finally, I hope to spend the second half talking about tech. There will be a more technical presentation tomorrow at 10:30 from Amir Taki, which will be on the math aspect. I will explain slightly more as we go on, but I highly recommend his talk for a more technical overview of what we're building. So this is a feedback loop between surveillance and anonymity. Anyone who has worked in cryptography is familiar with this dynamic. So effectively, the progress of cryptography is a kind of cat and mouse game in which cryptography continuously has to update its mechanisms in order to adapt to the increasing all-pervasiveness and increasing sophistication of surveillance techniques. So there is a feedback loop whereby the more sophisticated surveillance becomes, the more anonymous techniques must advance in order to bypass it. So this feedback implies that both surveillance techniques and anonymous techniques are going to escalate. We're going to see a mutual co-development of these 2 distinct worlds. How does this dynamic apply to a crypto context? I think these 2 worlds function as kind of attractors that warp the development of crypto, that bend it in certain directions. So in the surveillance space, we have the development of RegFi. RegFi is our term for crypto that has adapted toward the increasingly stringent requirements of the surveillance state. So it's kind of like the anti-crypto. It's the death of crypto. It's crypto as it merges with surveillance. On the other side then, we have the side of crypto which is anonymous, anti-fragile, parallel infrastructure that we call DarkFi. So this is anonymous crypto that will be vindicated as the true spirit of crypto. And, you know, in terms of the underlying forces, surveillance is based on a mechanism of control, whereas anonymity is about freedom and emancipation. So many of you might be familiar with the anti-fragility thesis presented by Nicola Tayeb. So this is a diagram of a fragile and an anti-fragile system. So you see they've got this nice positive and negative convexity. The graph says concave, but you can call it positive and negative convexity. So what that means is a fragile system is something that breaks when under pressure. An anti-fragile system is something that absorbs shocks and becomes stronger. And we can see here it's not this effect is not linear. It's actually closer to some kind of exponential function. So this is a linear relation. We can imagine, say in the case of something like a crypto wars, which is like the era that we're in at the moment, especially in the wake of Tornado Cash, but really it's been going on for decades. And it's not even the first crypto war. So we've seen this situation of crypto wars spiraling, unfolding in time. And as the crypto wars unfold in time, we can imagine that anonymous systems accrue more users. So this imagines there's a linear relationship. As the crypto wars unfold in time, the amount of users that anonymous systems attract also grows in step with that. However, as we saw from the anti-fragility illustration from before, it's not a linear relationship. There's something else that's happening that gives that convexity. So we're looking for some other dynamic that is really fueling the capturing of value and users into anonymous systems. So this quote is something a little bit closer to that dynamic that we're really looking for. This is Jay Stark. Who here has heard of Jay Stark? Wow. Okay, so more people have heard of LunarPunk than heard of Jay Stark. Jay Stark, totally. Okay, so Jay Stark, he's a German Kurdish man who created the FGC9, which was like a fully DIY gun that you could build using simple materials that are readily available. So he really took the concept of 3D printed guns and completed it by making it something that was like, highly simple and with consumer materials. So Jay Stark, he was murdered by the state about 2 years ago now. But this is a quote from him. He says, "If something unfortunate happens to one individual, another individual will take his place. It's a hydra you cannot completely kill. You cut off one head, another pops up. We are impossible to stop." Woo! So that's a beautiful quote. Well done, Jay Stark. Which gets a little bit closer to this dynamic that we're looking for. So, the dynamic could be thought about in the context of an insurrection, where insurrection happens, a revolutionary is killed in action, 20 more revolutionaries come to take her place. So this is the kind of anti-fragility and the convexity that we're looking for. You may be, or you probably are familiar with Metcalfe's law. Was proposed as a way of valuing networks. It says that the value of a network is proportional to the number of users. It's actually equal to the number of users squared. So we propose a version of this. We call it Jay Stark's law, which is inspired by the ethics of free software. So free software puts into positive feedback the notion of user empowerment and developer empowerment. So user empowerment and developer empowerment are positively correlated to each other in the free software paradigm. So we adapt this value judgment made by free software into this Jay Stark's law, which says user empowerment is positively correlated with system anti-fragility. So the more empowered your user base, the more anti-fragile your network becomes. So it's using this conjecture, this proposed mechanism, that we're able to achieve that nice positive convexity that we're looking for. So let's apply this reasoning to a real-life scenario. Let's imagine that there's some moment of escalation in the war against crypto. Say, for example, that self-custody is banned, which could happen, kind of is happening in some places. So self-custody is banned. We have, it's not this linear situation. We have a rapid, sudden descent into fragility. So we have users fleeing the networks en masse. As they're on a transparent system, users are potentially liable for their activity on that system. The crypto wars escalation leads to this mass flight, this descent into fragility, and this rapidly descending user empowerment and system anti-fragility feedback. On the other hand, in an anonymous system, this dynamic is reversed. So we see that as hostile powers try to restrict anonymous systems, they fall into something that we call the regulation trap, which is the harder they try to prohibit access to these systems and to prohibit people from using them, the more the utility of those systems is justified. So actually, the whole effort of trying to restrict access to these systems is, in a strange paradoxical way, affording more power over to those systems. So as we can see, in the case of a crackdown on an anonymous system, we actually see a rising political consciousness within the community. We see a rallying of individuals around that project, which leads to growth in users and eventually accumulates in this final stage in the convexity curve, which is, actually suddenly there's economic advantages to moving over to those anonymous systems. And an example of this was, I'm sure many of you were following what happened with Tornado Cash. What was very interesting was, instead of Tornado Cash being deleted by the OFAC sanction, it actually was more like a point of radicalization, where you had many people in the crypto community speaking out against surveillance and draconian regulation for the first time, and the Telegram group of Tornado Cash suddenly becoming more active. People were redeploying the contracts on IPFS, etc. So it had the opposite effect. Okay, so that's that explains a little bit the kind of economic theory behind Lunarpunk and why anonymous networks are going to grow in value in users. I'm now going to go into a brief section on the philosophical aspect. Okay, so as we can see, I'll just go back briefly. There are feedback loops intrinsic to this process. We mentioned some of them. But really this positive convexity, this anti-fragility, is more like an open spiral. So we're spiraling outward, we're engineering a kind of agarist exit from the surveillance state. The question becomes, where are we exiting to? And why are we exiting? What is this new world, this dark forest that we've emerged to? Dark forest is a term that's used by Lunarpunks. Generally means an anonymous world protected by encryption that has decoupled from the surveillance state. So we found ourselves here inside the dark forest. Why have we come here? So we know, for example, that the dark forest is protective. The example that I always like to give is a historical one, which relates to the conflict between Ireland and England, where the first time England tried to invade Ireland, that was failed. It was ultimately failed because at the time Ireland was covered in forests, and those forests were the basis for widespread, decentralized, invisible guerrilla resistance. So while the invasion was initially effective, traces of the invasion were entirely erased as the years unfolded. So the efforts were absorbed into the forest by virtue of that amazing decentralized, invisible resistance made possible by the forests. So in order to actually gain a foothold in Ireland, the British forces first had to destroy the forests, and it was only through clearing of the forests that they were actually able to fully colonize Ireland. So we know that forests can protect divergent groups, you know, that they can incubate and protect communities, but what kind of communities do we want to build in there, and what are we trying to protect? So Nietzsche has a really nice a discussion on morality, where he says that what he calls the morality of the master, he also aligns it to the state, basically imposes a morality on people and says, you know, this is good and evil, that's what you have to accept. The problem is when people try to resist against something like the state or some other monopoly, they do a simple inversion, where they say, okay, that's what the master says, I'm going to say the opposite thing, and that's my values. So you have this inversion, this negative copy. But the problem is that if you're in this simple inverted state, you haven't properly escaped the morality imposed on you by the master. You're still within the dialectic. So you have to transcend that morality. And the way that Nietzsche says that we have to transcend it, he says we must become what he calls philosophers of the future. Philosophers of the future create new values beyond the state. So they're in the creation of new values, and he proposes something which he calls genealogy, which is about being very aware and analysing what are the different forces and what are the different morals, where do they come from, what are their origins, and from there constructing something genuinely new and outside of this morality that's imposed by the state, and also outside the inverted morality which comes from the people, which is simply a copy, but an inverted copy of the state. So Öcalan, he says something similar. He says that the society has been enslaved by the state, and it's lost its own morals and politics. It just has a false morality which is imposed by the state. So he says society needs to regenerate this moral and political fabric. And he offers some practical ways of doing that. We list a few of them here. We have Hway Nazin, self-knowledge, but also know thyself, which is like this process of reflecting on your own origins, on the myths that have formed you, and that kind of inward reflection at the society level. Hway Parastin, which is self-defense. That's a big part of escaping the kind of seizure of morality and politics by the state. And finally, the notion of Hway Bun, which means autonomy or self-being or self-becoming, which this is how we achieve something which is not simply like an anti-state, which anti-state is still in this negative inversion of being an inverted copy of what the state is. So this is something closer. This is why we talk about lunar punk as a non-state. It's something that's genuinely exterior to the statist paradigm that has been imposed. Okay, so we have this beautiful image. This brings me to one of my favorite patterns in science fiction. So one of my favorite patterns that happens across science fiction books and novels, etc., is the moment in which a society discovers some kind of alien life or a new kind of technology. An example would be like in The Expanse when they discover the ring. And what's interesting about these moments is that it's a transformative contact. So it's a moment of contact with something so radically exterior and so alien that it completely reconfigures the horizons of the possible. So it's a contact and a transformation that changes the space of potentiality forever. So I'm coming now to the technical part of the speech. I believe we're at a similar moment in relation to anonymous engineering. So I call it here xenotechnics, that means alien techniques, because it's something so radically exterior and so novel that it will permanently change the horizons of the possible. And it's really a contact with this kind of alien force. And if you're interested in this concept, which I will briefly touch on but not go deep into, I can encourage you to attend Amir's talk tomorrow at 10:30, which will give the actual math examples of what I'm about to talk about. So DarkFi, here's a definition, is an L1 for anonymous engineering. Anonymous engineering, I touched on it briefly. Effectively, what we mean is a new kind of engineering which is based off of engineering anonymous schemas. And we will give some examples. And so DarkFi is an L1 to enable this kind of anonymous engineering, which means we expose an interface by which developers can integrate cryptographic techniques into their programs that allow them to construct these anonymous schemas. So we can give the example of ZK, but it's not just ZK. There's many other techniques that can be integrated as part of an anonymous schema, including multi-party computation, homomorphic encryption, and many other exotic crypto techniques that have emerged in the past few years. So DarkFi is really trying to provide a way, a simple way for developers to integrate all these tools and to make applications that dramatically extend the design space that we currently have in projects like, or in ecosystems such as Ethereum. And that's very much our vision is, we're very inspired by the frictionlessness and the level of creative innovation that's been made possible by places like Ethereum and, spaces like DeFi and the other kinds of innovations that have come out of that. So we want to extend that design space. We want to push it to its limits by integrating anonymity as part of that. Overview of where we're at currently. We have our first testnet, which is live and operational. You can download the software and run it and join the testnet, play around. We're using an anonymous proof of stake called Ouroboros Crypsinus, which is very interesting. It's important to note that it's quite different to proof of stake as we have it on Ethereum, where, in Ethereum there's a concept of slashing. In DarkFi there is no slashing. It's kind of conceptually like a fusion between proof of work and proof of stake, in that nodes participate in this anonymous leader selection by creating a local proof, and they do that by running a lottery local on their computers, and they have stake as like a variable in that lottery process, which increases the probability of them winning the lottery. So if they win this lottery and they go through these steps, this algorithm, then they can produce a proof that allows them to create a block. So this is an anonymous leader selection protocol, which is MIV resistant and censorship proof. So alongside this blockchain, we have a general purpose smart contract infrastructure. I'm going to, in the next slides, discuss a little bit what that is and how that works and how we achieve general programmability on DarkFi. We also have an app-driven approach. So there are other kind of ZK L1s that exist at the moment, they have a kind of backwards approach to engineering where they are starting by engineering abstractions and then they're trying to engineer apps from there, but we can see that they're creating complexity traps for themselves. So we've taken the opposite approach where we're actually building apps and we're letting those apps dictate decisions on like our smart contract architecture and also to inform the design choices we make in terms of abstraction. So the apps that we have currently working are, we have an anonymous DAO that's working on the testnet. You can create a DAO on the testnet now if you download the testnet. We also have swaps. It's called here Anon OTC. That's atomic swaps. We have anonymous transactions, anonymous staking with the Ouroboros Cryptonos, and we also have anonymous coordination tooling, such as an IRC, which is highly anonymous. I will discuss that a little bit later. So I will briefly explain DarkFi's general programmability. So we have on the network, all nodes are provers and verifiers, all full nodes. Provers create the anonymous transaction, which is like they load locally, they interact with these ZK proofs, and they put their secret values into them, but those secret values are never revealed on the network. So the prover does that locally. They then broadcast that transaction, which is like, with these anonymized or anonymous inputs, to the network, where they are picked up by these verifiers who verify according to the particular contract. They verify the various crypto and the signatures, and then they transition the blockchain to the next state. So transactions on DarkFi contain multiple function call data. So we see here t is equal to C1 to n. We can have an arbitrary number of function calls data in a transaction. Transactions are also atomic, so we can have chains of logic where if one function call fails, the rest of the transaction will fail. And this is how we achieve advanced anonymous apps, such as protocol-owned liquidity, which we will look at in the next couple slides. So this call data is arbitrary data, which is defined by whatever contract is being used. Depends on the contract. So if that's like for money or for the DAO, etc., that will determine what the call data is, and it can contain proofs and signatures, commitments, etc. So to achieve this, we have like different layers. We have a ZK assembly language and virtual machine, which is using Halo 2. So that is how we achieve the zero-knowledge proofs. And there's a pipeline where we use this very, very simple assembly language, and that's compiled down to bytecode, which is run on the VM. The assembly language, I highly recommend you check it out. It's very beautiful and very simple. I have a newfound appreciation for it since today attending a workshop of other ZK languages and being very disturbed by the complexity of the languages. ZKAS, we've kept it intentionally simple, intentionally like low level for now, such that when you read it, you can actually understand what it's doing. Which I think is really important when it comes to ZK proofs. Anyway, that's a tangent. So we combine this, these ZK proofs with, we also have a WASM runtime. So when we talk about smart contracts on DarkFi, they are using WASM. And we write them in Rust, but WASM is such that you could write them in other languages. Those WASM contracts have access to an SDK, which includes all these different primitives that allow you to engineer anonymous applications. So, signatures, elliptic curves commitments. We will extend this gradually. We're on alpha testnet now, and we've kept things intentionally simple, intentionally manageable, but the idea is to gradually extend so that developers can build increasingly sophisticated applications. So currently on DarkFi, we have 2 main contracts on the WASM. So we have the money and the DAO. Inside money, we have these function calls, which allow us to do the swaps and also the staking. So you can see money transfer. That is, if you guys are familiar with the sapling payment scheme, we will talk about in the next slide how that works in the context of DarkFi. But sapling, it's an anonymous schema that was invented by Zcash, and we use that as well in DarkFi to do anonymous transactions. And actually, in other apps, we use this money transfer as well in this chaining of function calls that we do in the application design. Then we have this OTC swap, which is, we create an atomic swap between 2 parties. And then we have this stake and unstaked functionality, which is used for the Ouroboros Crypsinus anonymous staking. So yeah, this is our, one of our big achievements as well, that we created this anonymous DAO, which is the first anonymous DAO. And it's working on our testnet, so that's pretty cool. So you have DAO Mint. You basically create a new DAO with various constraints that you set. So you decide on things like what is the quorum, what is the proposer limit, like how many tokens do you need to make a proposal. And so there's we will actually look more deeply, but there's several constraints. You create a DAO. You make a proposal to the DAO, and you vote on a proposal, and finally, DAO exec is an operation which transfers money from the DAO treasury to an address specified in a proposal. And so it's essentially a form of protocol-owned liquidity that is conditional, and that can allow for advanced on-chain applications. So this is a simple kind of diagram to explain sapling as it works in the DarkFi context. So on the right, we have the proofs. This is like a simplified version. So we have a mint and a burn proof. Mint is whenever we make a transaction, we output a mint proof, and we burn. We input a burn and we output a mint. So we can see that here it says, Alice wants to send tokens. So the way she does that is she first produces this burn proof. She burns those tokens and then mints these other tokens to Bob. So that's unlinkable and anonymous. Here we have the schema. This is like a kind of simplified version, just to get an intuition for how that works. So in a mint proof, we create a random serial number. Then we create C, which is a hash of a serial number, and any number of attributes. So C is actually our coin, where we can put inside different information, like the token ID, the value of the token. And then we broadcast C, we make it public, and we transition the state. Then from the burn side, we reveal something called a nullifier, which is our double spend protection. And the way that the protocol is designed, as soon as you reveal that, the coin is spent, and you cannot. It protects against double spend. That's because it's deterministically generated from the private key and a serial number that is created in the mint step. So then we do something called a Merkle inclusion proof, which basically just proves that that this is the correct coin and it exists in the state. So that's the burn proof. This then, so we use those mint and burn proofs also within a DAO application, but we have the other proofs as well. So like we've got vote, propose, etc. And here's the diagram, which it doesn't show the mint step. This is showing voting, which is number 1, and 2 is the DAO exec. So on number 1, we can see that someone has created a proposal. That proposal, you know, checks various constraints that are set by the DAO, the proposer limit, which basically says, do you have enough tokens to make this proposal? The quorum, which says how much tokens need to be like committed to this in order for it to be considered valid. And then the approval ratio. What is the ratio of yes to no votes in order for this proposal to pass? So this is all set when you create the DAO. So the participants vote on this anonymously, and if those votes satisfy the constraints of the DAO, then the operation can be executed. Similarly, I didn't mention in the previous slide, or I didn't mention here, that we are also hiding the amounts in a transaction using Pedersen commitments, and the same is true here, that that all the amounts are hidden and everything is anonymous. Aside from, you can tell when a, if I recall correctly, when a vote happens, you can tell that voting is happening on a proposal, but you cannot tell what the vote is or what the proposal is. You can just tell that a vote is happening on a proposal in terms of the blockchain, because we reveal the function calls. Okay, so to back up a bit, DarkFi also has its own peer-to-peer network. This is designed to be highly modular, so it can run over Tor, it can run over NIM. This means we're the only project that is working at, that is like seriously considering network level anonymity. We have these Tor and NIM integrations already working, so that's important. On this peer-to-peer network, we have a fully anonymous IRC. I mentioned that the peer-to-peer network is highly modular. It's very easy to deploy apps on it. So this is one such app. It's IRC, but that we've like integrated onto the peer-to-peer network. We've also added some really nice anonymity features. So we have encrypted channels, we have encrypted DMs, and we also have a really nice ability to change your nick as many times as you want. So the IRC has no concept of identity. You can appear as anyone, it's completely invisible on the network and on the client, like it's completely unlinkable, the IDs. So there's no identity. And we will, as a next step, also release a spam protection, which will include rate limit. We will use rate limit nullifiers for that. So highly encourage you to join our IRC if you're interested in DarkFi. We have dev meetings every Monday at 4 o'clock Central European time. So spin up an IRC daemon and join our chat with WeChat. It's very chill. Okay, so in terms of the timeline, I mentioned that we have kept DarkFi intentionally simple. So with the current architecture that we have, which includes this zero knowledge component and this WASM component, which also integrates the SDK, we can design many interesting applications. So we have already the DAO and the money. We will soon also have stuff like NFTs, and there are many other projects or apps that can be quite simply deployed using this. But we will slowly add more and more features to extend the design space. Like, for example, multi-party computation is an important one. But we're intentionally postponing that because we're simplicity oriented, so we're going step by step. And the current status is we've released this alpha testnet. We're stabilizing it, smoothing it out, and we have to finalize the token. Right now, the proof of stake, it just has a token, but it's like a dummy token. We haven't done any actual token engineering. So the next release will contain the fully fledged dark token. That will be the testnet beta. Then we will go into an audit phase where we need to audit every aspect of the code base. Depending on how long that takes, we will then deploy mainnet. So the current version of DarkFi is pretty much where we want to be when we release the mainnet, minus the token engineering and minus the audit. And depending on how long the audit takes, we can target mainnet for optimistically end of this year. But maybe the audit will create new work for us that will drag on for longer. So it could be a year from now. But basically, we're very focused on shipping mainnet as quickly as possible. And yes, so if you want more information, check out our website. On there, we have a link to the docs, which will give you instructions on how to install and run the testnet and the IRC, where we have the developer meetings every Monday at 4 o'clock. You can also follow us on Twitter, although it's not that active. You're better off following us on IRC. Similarly, there's our GitHub. Check it out, and happy to answer any questions that you have.
Thank you very much, Rachel. Big round of applause. Now, the deal is we have 10 minutes until the next speaker. The next speaker is very interesting. There is some very interesting stuff down here for people who need a little exercise, walking up and down the steps. You have a question, sir? Okay, if you keep it short, keep it to the point, and Rachel doesn't go into a long answer. Shoot.
Okay, I'll try.
Okay.
Are you concerned at all with the emergence of dark DAOs, like lowering the barrier for kind of committing attacks, right? So when I think of like a dark DAO, I think of the ability for people to anonymously coordinate to launch an attack, right, without revealing, right, that they would like to launch an attack. So you could imagine a governance system being compromised by a minority of token holders, right? Because people just kind of keep committing tokens to do the attack, committing tokens until some threshold is reached, right? Such that you can achieve quorum, right? You could also think of it, in more traditional terms, right? In terms of validators, right? Coordinating to compromise some network, validators of oracles, right? So are there things we can do to mitigate the impact of this, or is this just kind of like the new reality that we live in?
Tough question. You go ahead.
Oh, I have a mic, sorry. Yeah, I agree that, anonymity and privacy, they come with these negative externalities, such as you can imagine, like you said, like interesting anonymous DAOs coordinating to do stuff without this issue on ETH where they couldn't do that because they would be caught by police and stuff. So yeah, I definitely think that the privacy comes with negative externalities, but I think that the gains for freedom outweigh the cost, the potential cost in terms of risk that comes from things like dark DAOs. So I'm much more concerned about the potential dystopic impact of us like totalizing surveillance state that we're heading into than I am concerned about like the ability for people to coordinate anonymously to do illegal actions. Sorry, I don't know if that answers.
All right, maybe there's a chance to follow up on the question afterwards. We'd give everybody else a chance to jump down here, grab a very cool sticker if they want. Thank you very much, Rachel.
Thank you.
We have about 5 minutes before the next talk. Thanks a lot.
Nice.
So I think They'll take care of it.
I will review a little bit of the topics that we have been researching over the years with respect to the Ethereum ecosystem. And the reason is the following. In my team, we are performing research on 3 main areas of knowledge in the area of blockchain. On the one side, we are very interested in consensus, scaling of consensus, but specifically on which are the limits that consensus has. For example, when you have networks that are growing and you need to diffuse data in terms of blocks, and you need that this data is reaching all the nodes that are present in the system, that all the nodes receive the blocks that are being broadcasted, you have finite time and you have the diffusion is taking longer, the more data these nodes are, the more data the blockchain is storing. This introduces some physical constraints to the quality of consensus in blockchain-based systems, but also it enables the possibility for different kinds of strategic behavior by the participants in the system. And we are very interested on how this abnormal behavior away from the implicit rules that the protocols have, affect the quality of consensus or affect the way in which rewards are distributed. Reward distribution is also something that is very interesting to us. We are very interested in understanding how the way in which rewards are distributed eventually affect large-scale properties of the economy of these systems. For example, the level of concentration, the level of economic concentration of wealth and inequality that is present in these different systems. I will talk a little bit about this in a second. Cryptoeconomics is very interesting. You can lead not only at the layer 1, but also looking at what happens at the level of token economies. So cryptoeconomics is and tokenomics is something that we are very interested into as well. And we do not do this in a traditional approach that economists do. It's not that we are just doing formal modeling of this, mathematical modeling, but we are also very interested and we perform a lot of large-scale blockchain analytics. It's exactly in contrast to what was explained before. Most of the blockchain-based systems still allow us to analyze the transactional data at all the possible levels, and what we use this data for is to understand economic mechanisms that drive emergent properties. And as you see in this first slide, what is very important for you to remember is that when you look at the global properties of the system, you see that there are some properties that naturally emerge. You see that economic inequality is just something that emerges because of the economic interactions between the participants. And this inequality or this concentration that happens, for example, at the level of consensus power in participation in the consensus, is something that is not enforced top-down. It is something that just naturally appears because of the economic incentives that are placed in the system, and because of the bilateral interactions of people that is transacting value. So all these properties naturally emerge and are not imposed top-down by system designers. And what is important as well to remember is that once you have properties that emerge, these properties are robust against changes. Okay, so you need to think carefully on how the systems are designed at the microeconomic level in order to get properties that are more akin to those that you may want to see inside of the systems. And I will talk a little bit about some of the missteps that different layer 1 systems, Ethereum as well in a way, have taken when designing the incentives as a blockchain-based economy. Okay? One of the main reasons that to me has been always fascinating and that eventually determines at a very large scale what happens with respect to power accumulation in blockchain-based systems is thinking that there are decisions in which the allocation for example, the supply of new assets of Ether for most of the time in which Ethereum was running was a deterministic issuing of new Ether. And this is not something that is allocated by the market. It is not that the new Ethers were created historically for most of the time based on how much demand exists for the assets or how much people is using them. There was just a design choice done at the beginning of the creation of Ether and of Ethereum. And you see here you have the total supply as a percentage of the total supply that was already generated in completely different blockchains. You have a lot of UTXO-based one, all of them forks of Bitcoin. And you have there in yellow the total supply of Ether. You know that most of the Ethers were created at day one when they were together with the Genesis block. They were reallocated to the Ethereum Foundation. But you see that here, in contrast to what happens in real-world economies, always the growth of the supply is just a deterministic function. And it is, most strikingly, is a linear function. Okay? And when you look at, for example, how many accounts are created in most of the successful blockchain-based systems, some of those are not so successful in this plot. One thing that is interesting, once again you have Ethereum in yellow, is that you see that the y-axis is in logarithmic scale. The total number of participants in the system, the total number of accounts created in the system grows exponentially. So here you have a huge failure when thinking of the design of the system, because you have an exponential growth in the demand in principle, and you have just a linear growth in the total number of assets that are taking part of this. And this created, not only in Ethereum, but in most of the blockchain-based systems, an increase in centralization at the level of the incentives that you have in order to participate in the consensus. When you look into how unequal is the distribution of wealth in all these systems, once again you have that it saturates. The Gini index actually is not very good at measuring wealth inequality in blockchain-based systems because it very rapidly saturates to 1 when you have a lot of inequality in the wealth distribution. And while there has been a transition, one thing that we were analyzing as well, is what happens at the level of the fairness and the reward distribution in different delegated proof-of-stake-based systems. And interestingly, you can measure it in different ways, but interestingly what you see is that you have different choices, and Ethereum took one, which is that the total number of validators that are active in one of the eras is fixed. You have different degrees of freedoms of when you have delegated proof of stake. You may decide just to allow for an open-ended amount of validators that may be active in an era, or you may limit, like it happens, for example, in Polkadot, in this case Casper, and as well in Ethereum. Other systems like Cardano and Tezos, for example, allow for an unlimited number of participants to be active inside of each one of the cycles. And what we identify, however, is that with respect to the concentration, actually the design choice that Ethereum took, Polkadot took, and Casper took, that is limiting the amount of active validators, in a way is much more beneficial to the wealth redistribution, to the reward distribution, to make it more egalitarian in the long run. And it is very interesting because you may think that the way in which a proof-of-stake-based system may only affect locally or instantaneously the level of the rewards. However, it has a very long-term impact in the distribution of economic importance of the actors that are participating of the validation process. Another thing that we did research on for the past years was, okay, we have been looking at this level of centralization that happens in different blockchain-based systems. It happens at the level of economic concentration. It happens as well at the level of the validators that are participating of the a verification process inside of these blockchains. And actually what happens is that, I will not talk a lot about this, but we have been analyzing as well for the past years different token economies. And on the one side you have a positive correlation on the pricing of tokens and the amount of activity that they have inside of the blockchains. The more tokens are transacted, the more is the value that they end up having in the system. Actually, it is a law that allows us to recall a little bit what happens with the Metcalfe law, that you know that the larger a network is in terms of number of participants, the more the participants assign value to the token. And this is exactly what we observe as well in the evaluation of tokens with respect to market capitalization. However, what you see in the left panel in these two plots is that actually the level of centralization that happens in Ethereum tokens is incredibly large. There are very few accounts, in general smart contracts, DEXs, or centralized exchanges, that if you remove them from the system, the network of transactions completely collapses. So most of the tokens still means a level of concentration that is that of the speculative assets, okay? Because they are just traded in the market and not circulating organically inside of the economy. We have been analyzing layer 1, we have analyzing token economies, and there is a very interesting project that we have been looking into, that is what happens with some DEXs, with decentralized exchanges. Because you know that in a centralized exchange, all the transactions take place off-chain, actually. They only happen logically off-chain, and the actual exchange of value of one token for the other is never realized inside of the blockchain. It only appears when one of the users wants to deposit or withdraw tokens from the specific exchange. And so I will talk a little bit about a platform that all of us know. It is Uniswap. And when we are thinking of Uniswap, there is something that happens, that is the creation of a liquidity pool is once again not something that a system designer, like in a centralized exchange, is creating. Liquidity pools are something that any user can do if they can provide liquidity for the trading pair. So the first thing that you may say is, okay, all the amounts that people is putting in each one of the liquidity pools, the amount of values that they are putting, all of them are completely independent. So perhaps we will see just some noisy pattern when we think of analyzing the whole structure of Uniswap. So we analyzed the structure of Uniswap version 2. And the question that we asked is, are there general laws that emerge out of this in principle and coordinated action of all the participants inside of this decentralized exchange? And what we identify here, what we analyzed is, by the time in which we analyzed it, at the beginning of this year, there were something like 40,000 different liquidity pairs in Uniswap. And in the y-axis, here, once again, in logarithmic scale, you have the total value locked in US dollars in each one of these trading pairs. And in the x-axis, what you have is the decrease, in a decreasing order, the largest liquidity pools, starting from the largest liquidity pool to the smallest one. And what you see here is, once again, the x-axis is in logarithmic scale. And you see that this is a line. It is a line because in statistics this is called the power law distribution. Actually, this is a SIP law, actually also signaled by the exponent, which is -1. And this is a typical trait that self-organized systems have. So even if people is independently pulling and adding and removing liquidity, buying and selling tokens inside of each one of these liquidity pools, all of them evince a very clear pattern of self-organization. You can build a network representation that is very important to understand how systemic are specific tokens in the following way. In this network that you see there, each one of the nodes is a token, and there is a link between two tokens if there is a liquidity pool between them. And what you see, it is very apparent from this representation, is that there are a few tokens that are completely systemic, and if they fail, all the system of Uniswap may collapse. And this is very important because this is the original version of Uniswap liquidity pool network, and this is how it evolved over time until mid last year. But you see that they are still heavily centralized. Okay, it grew a lot. They have many tokens traded inside of Uniswap. However, you have many of them are transacted against the same tokens. And what you see is that there are communities, from a network point of view, there are communities centered around the specific tokens in which there is a creation of a lot of trading pairs with respect to other ones. And what you see is that there are very few tokens that are completely systemic for the functioning of Uniswap. Obviously, the first one is wrapped Ether, then DAI, USDT, etc. This is in the last snapshot. You have a USDT and USDC as the most important ones in the system. Actually, if there is this plot there of Dogilon, it's because this is actually one top 10, and it is systemic inside of Uniswap. It is traded, it has a lot of value locked, and it has a lot of trading pairs with others. Okay. There is a very large level of inequality in the size of the tokens, etc. But the most important thing that I wanted to mention with respect to this plot is that actually the distribution of the sizes of all the liquidity pools of all this network, the importance of all the liquidity pools in this network has stabilized for almost 2 years. So actually there is remember what I said in my first slide. There is an emergent property in the structure of this network of liquidity pools that is stable. Even if it grows, it preserves still the same shape. And what we are investigating now, I will not go into much detail with respect to this, but what we are identifying is actually that if you look into rug pulls that have happened inside of this system, you see that also they have been affecting completely different sections of the network at all the possible scales, resembling very much the distribution of liquidity pools. And provided that we have had rug pools of all the possible sizes, it is a very important point with respect to analyzing how there can be a cascade of failures induced by this activity. The final thing that I would like to talk in the last 5 minutes that we have been investigating, doing research on, is we have gone all the way from layer 1 to tokens, later to what happens in the centralized exchanges. And one thing that is very important to have a functioning economy is endogenous circulation of cryptocurrencies, such that even if you have a limited supply, it is enough to satisfy all the transactions. Then you do not have speculation in rising prices, etc. And really, what happens in Ethereum if you want to see its economic activity? So there is a concept that macroeconomists have been using for more than a century, is that of the velocity of money. And in general, macroeconomists resort in order to use it in a so-called Fisher equation that provides it's tautological, actually, if you are thinking of this. Because in a real-world economy, you cannot measure the way in which the money circulates. The only thing that you can do is estimate the velocity based on other parameters, assuming that the Fisher equation is correct. Okay, this is what you traditionally do people that is analyzing real-world economies do. What we have been doing for a couple of years already, we started analyzing UTXO-based blockchains, and now we also are finishing a paper in which we analyze this concept for Ethereum, is actually measuring the velocity of money inside of the Ethereum economy. But not only that, and what I like the most about this methodology is that we are not just looking at the macroscopic level of the velocity of money, but we were able to derive how much each one of the users of Ethereum is contributing to the global velocity, and understanding who is actually contributing and how unequal is the contribution to the global velocity. And in a nutshell, what we are doing is, if you have that Alice received 2 times Ether, one in the block number 10 and another time in the block number 20, she received 15 Ether in the block 10, 5 Ether and 10 Ether in the block 20. What we do is basically, and in the block 30, she sends to Bob the 15 Ether. What has happened so far is that there were 10 Ether that stood still for 10 blocks, and 5 Ether that were stood there in the wallet of Alice for 20 blocks. So if you take the weighted average of these two things, basically you know which is the velocity at which Alice's funds were moving in this period of time. Okay? And exactly because it is the approach that is taking usually in economics, what we assume is that the last money that you received is the first one that you are spending, okay? Because all the others are saving. You save money, and then when you earn new money, what you are doing is spending the last part that you received. So this is why we adopted this LIFO approach. So what we did is actually measuring first of all, the global velocity, and what you see is that there was a spike in the total velocity in Ethereum, triggered exactly by the point in time of 2817, which was the ICO craze. Okay? And interestingly, on the other axis you see in green and labeled in the right part of this plot, you see in green the total number of active users. And you see that it is only until 2018 that the total number of active users in Ethereum has been growing exponentially. Once again, you see that the scale is logarithmic. So after that, the total number of users has basically plateaued. And there is a lot of reasons for that. Gas prices have grown a lot. It's one of the reasons on why this thing has happened. But there was no so much economic activity anymore within the Ethereum blockchain as if it was happening inside of 2017, 2018, in that period. What is interesting is that here we have the 5 first most important nodes, users contributing to the total velocity in Ethereum. This is now the individual contributions before we looked into the global scale. And what we see here is that roughly 30% of all the total velocity is only originated in 5 different accounts. Okay? When you look at them, first looking at it from the global point of view, understanding which is the level of wealth that they have times the velocity of what they contribute, what you see is that a family of exchanges contributes is the most one, is the largest one. Then, after you pass all this is the whole set of unidentified addresses, all the addresses belonging to Binance, Bitfinex, Kraken, etc., are the top 5 of the users. This is if you consider the wealth. If you do not consider the wealth, what you see is that the main activity that triggers the circulation of money inside of Ethereum are still exchanges plus the process of verification. Here it is written as mining, but it is all the process of reward distributions. And then you have Celsius Networks, Nest Protocol, Oracle, etc. Another thing that you see is actually that there is a very mild correlation, almost zero, between the monetary, the wealth of the users and the velocity of that they produce. It's basically flat, the process. And what is most interesting to me, and perhaps this is the time in which I can finish, is we can look at the distribution of how much is the microvelocity that each one of the nodes users is contributing to Ethereum. And once again, here you have a log-log plot. And once again, here you have a straight line, so it is a power law distribution in the velocities. And strikingly, and we can concentrate first on the right part of this plot, what you see is that there is a stable distribution that we are trying to understand why this is happening. There is a stable distribution in the contribution to money velocity of all the users that is stable with the power law of -2. But remember what I said before, because it is an account-based system, we are not sure exactly which are the assets that each one of the users is spending when they are spending money. In UTXO-based systems, you can certainly do that. But here we have to make the assumption of the LIFO, last input, first output. If you consider first input, first output, or if you consider just a randomized version of any of the prior transactions, you still see that the distribution of velocity is still the same. So this is an emergent property that is stable and that characterizes the contribution of all the users. Power law distributions are important because it means that you have a handful of very active users and you have a very large amount of users who do not contribute at all to the velocity of money. Okay? In a way, I would like to conclude this presentation that was very long, trying to say that we have to remember that all the systems, when we are thinking of this as an economic problem, we have to remember that all these systems are very far from equilibrium. As we have seen, number of users changes exponentially in number. So you cannot make models in which you are trying to come up with pricing, etc., need to take into account not only the fact that the system is out of equilibrium, that its parameters are constantly changing, but also that the complexity of human behavior is an additional layer of, as an additional factor that must be taken into account to better understand them. Thank you very much for the patience, people.
Very, very interesting, very in-depth. I know you're going to be around later on, so anybody who has an in-depth question will be able to ask you those questions then. This report that you just mentioned will be available soon?
We have the paper on Ethereum velocity out in a couple of weeks, yes.
Okay, okay. So very good timing.
Thank
you. Very, very good. Thank you very much.
Thank you.
Good. We're going to move very shortly into our next presentation about the Portal network from Piper Merriam. Just 1 or 2 minutes. Feel free to jump up and down, get some exercise, relax. I would ask you to ask your question personally, maybe, if that's okay. Yeah? Good. You're getting yourself set up? You're all right?
Assuming you guys have my slides.
I assume so. So that's very good. So Piper, over to you.
All right, let's see if this clicker works. All right, it looks like it does. Cool. Well, hello, everybody. I'm here to talk to you today about a project I've been working on for a bit, me and a couple of other people, called the Portal Network. I'm Piper Merriam. I work for the Ethereum Foundation. I guess researcher might be the right title here. I've done a lot of things. I've been doing Ethereum stuff since the network launched, and well, it's been quite a ride. Goal is, at the end of this, you guys have a sense for the answer to this question, both kind of conceptually and the, like, what problems are we trying to solve, what problems are out there, as well as just pragmatically, what specifically, technology-wise, are we building. This is kind of my white whale. I've been at this problem for like 5 or 6 years now, and it's got some more to go. Turns out lightweight protocol access is not easy. Which 2016 me had no idea about. I thought, yay, I'm going to build a light client. Around 2016, Parity is shitting the bed, and Geth is pretty much the only show in town, and client diversity is a problem, and I thought, maybe I can fix that. It went great. Not really. We spent 5 years building a Ethereum client called Trinity. It was written in Python. We knew almost nothing about the protocol when we started, and we learned a lot along the way. We built, and we ended up with something that looked kind of like Geth, but was really slow. And then we spent another like 2 years iterating on different things that we could do with LES, which is the established light client protocol at the time. Ways that we could use the existing peer-to-peer protocol that all Ethereum clients use, and ultimately we ended up letting the boulder roll back down the hill. The conclusion was you can't get there, from here, wherever you want to put that. This is a concept from a science fiction book that I read recently that I like a lot, and it's just this phrase to try to capture when you are essentially trying to do something the wrong way, trying to transform a system into something that it doesn't want to turn into, that sort of thing. So we learned some stuff during this time. And one of the big ones is that the dev P2P protocols that Ethereum runs on are far too demanding. Dev P2P is a peer-to-peer networking protocol. All Ethereum execution layer Ethereum clients use it to communicate. And Dev P2P, the way that execution clients use it for, is basically a dumb transport layer between full nodes. And full nodes are hardware-intensive pieces of software. This is like rough stats of what a full node looks like today. You need something generally like a full terabyte of fast disk to run these things. You need large amounts of RAM, many cores of CPUs to run. The transaction pool itself is an expensive thing to be part of. And if you want to be part of the network that execution clients are part of, you have to be this tall to ride. And if you aren't, then well, you're this sad little girl at the fair. Dev P2P demands a ton from the clients that are part of its network. And the end result is that all of those clients end up looking about the same. And they're all really heavy pieces of software to run. On the other side of that, we have this protocol called LES, the Light Ethereum Subprotocol. And the end result, after many years of development, is that it doesn't scale well. This is what LES is like. LES is a client-server model. Again, we have this dependence on full nodes, this sort of fundamental assumption of full nodes. And all of the light participants in this network just get their data from full nodes. And being a full node in this network looks something like this. You just get hammered with requests from all of the light nodes. And the amount of capacity in the network is a function of how many full nodes there are. So every new light node that comes online is eating up some amount of fixed capacity. And being a full node in this network has no benefit to you. It is purely a cost to you. And the light nodes have no ability to contribute to this protocol. They are purely takers. So after spending a bunch of time building what was effectively a copy of Geth, and realizing we weren't going to do better than being Geth, And then spending a bunch of time trying to build options around in different directions of how can we make this client shape differently, we came to this conclusion: you can't get there from here. And so we came up with a certain set of like, well, if we can't build it from this, what do we need to build? One of the things that we centered on was kind of well, first of all, we weren't going to build a centralized solution. Centralized solutions are boring to me. Go have fun building one of those if that's what you want to do. LES fits this decentralized model, but the client-server model, we already kind of looked at that and thought, this isn't working well. We don't want to depend on full nodes. And so we aimed for something that fit this distributed model. It's sticks with the core of our ecosystem's values, right? We care a lot about decentralization. But we wanted something that didn't have this kind of like full node, light node distinction. We wanted something where all the nodes to the network contributed capacity. A lot like BitTorrent. We aimed to build something, and we have built something, that instead of each new light client coming on taking up some amount of fixed capacity, we wanted something where as we added new nodes to the network, it got more powerful. And then this is a graph that's been in a bunch of my slides because it's really what we're aiming at. Today, you only get the decentralized heavy option or the lightweight centralized option. And there really should be something in the upper, yep, not mirrored, cool, left corner of this graph. And that's what we're aiming to build. That's what we are building. So what is it? So the Portal network is a completely new set of peer-to-peer networking protocols for Ethereum. It's built on the Discovery v5 protocol for anybody who cares about those kind of specifics. There's some really nice things about that protocol that we like. One of them is that it's connectionless. It's another thing in the dev P2P world that we didn't like. In the lib P2P world as well, that they are lib P2P and dev P2P are connection-based protocols. You establish a connection with somebody and then you hold on to it. And that itself is a little bit discriminatory towards light nodes who want to pop into the network and do something. In a network where they have to establish long-lived connections, they're already at a disadvantage. So we were looking for a protocol that was well-suited for light nodes, and the Discovery v5 protocol did that for us. This is a distributed storage protocol. We looked at what data you need to do lightweight protocol access, and then started looking at how we map that data onto a distributed storage network. And the whole thing is designed from the ground up, aimed at being resource friendly towards low resource devices. So aiming for building protocols that don't have kind of these implicit height requirements, these you must be this tall to ride. Aiming for a protocol where the base level of participation is accessible to consumer level hardware, consumer level internet connections, that sort of thing. And then I came up with this mouthful: a globally available, highly accessible, massively cooperative archive node. That's what we're building, a mouthful of that. Globally available, it's a peer-to-peer network. You can get on it from anywhere in the world that you have an internet connection and that you can connect to another peer. Highly accessible, targeting low resource devices. Ideally, you can flash a Raspberry Pi and run it on our network. You can run it on your laptop. You can run it as a daemon process that doesn't eat up your CPU. Massively cooperative. We're looking for something where we bring hundreds of thousands of nodes online around the world, and that capacity gives us what we need to not only serve all of Ethereum's historical data, but even archive node level state data. We've been at this for a little bit. We're on track to deliver a fully functional history network. So that's a network that serves all of the historical headers, block bodies, and receipts. Probably in the next couple of months, but betting on software delivery is risky business. So by the end of this year, we should have a fully functioning chain history network. We're hoping to see experimentation on top of this for EIP 4.4s. one of the things that's blocking most of the Ethereum clients from dropping all of the deep history is there isn't an alternative place for them to get it. We're working on state. We're just getting started on that. That's going to be a harder, nastier problem, but we're looking at delivery sometime towards the end of this year or Q4. Or 2024. This is like a long, ongoing research project. We're delivering pieces as we go. And we're really just hitting our first kind of like live networks with live data where these things are really working. I encourage you guys to join our Discord or anything like that if you're interested in getting involved. We are right close to the point where we start talking to the community about turning nodes online. But we're not quite there yet, so I'm not going to tell you to do it. But if you think that this is a project that you're interested in, that you'd like to learn more about, I'd love to get you hooked up, talk to you, whatever. But I want to zoom out a little bit. If you remember, I kind of started this way back in 2016 with this idea that I was going to fix client diversity. This project, I never know what to call it, because it is a project. It's a multi-team project. We have 3 different client implementations. This spans beyond just the EF. This is something that is, infrastructure for kind of like our entire ecosystem. And lightweight protocol access is a huge thing. It is one of the primary things we're focused on. But I want to talk a little bit about execution layer client diversity, because that's kind of the piece that's hidden under the surface level here. This is roughly what client diversity looks like today. It's the Geth show. It's been the Geth show for as long as it's been. It shows no sign of not being the Geth show anytime soon. And so the answer, so I asked the question, like, why is it this way? And what is it that we need to do to fix this? Because this is a graph that we should want to fix. And the answer, if you can come up with an answer to this question, that's my thesis here, is that if you want to fix client diversity, you have to figure out how to beat Go Ethereum. And I'm using intentionally adversarial language here. Nobody wants to actually ruin Go Ethereum in any way. We're talking about Go Ethereum does a really good job, so you have to do a better job than Go Ethereum, but it's more fun if I say beat them. So how do you beat Go Ethereum? Well, we tried this, be better at being Geth than Geth is. And I think that there's some other clients that are doing similar things. And I don't really blame them for this. If you remember what I said earlier, the Dev P2P protocol dictates a lot of functionality about what your client must do in order to be part of that network. If you make a list of what that functionality is, you basically get a list of what Geth does. And it turns out if you go to build a client, you end up building roughly the same functionality of what Geth does. You build a client that walks its way through the header chain to figure out what the front of the chain is, that walks its way back, downloading the whole history, and then uses some process to grab a snapshot of the state, and then execute blocks to keep it up to date. That's what an Ethereum client looks like, because that's what the network basically makes you do. These guys have been slowly gaining some market share, but this graph has not changed a lot for a while. It's my thesis that if you want to beat Go Ethereum, you need to play a different game than they're playing. Go Ethereum has had, what, 5, 6, 7 years to get good at being who they are. Like, you got a lot of catch up to do if you're going to beat them at their own game. Aragon has come along and said, we're going to play a slightly different game. It's not a fundamentally different game, but it is different. And they have differentiated themselves. But they're still not quite winning, right? Nobody is beating that 70% that Geth has on this graph. It's my thesis that if you want to beat Go Ethereum, you've got to play a fundamentally different game than they're playing. And we'll see if I'm right. But the thesis goes something like this. If you want client diversity, then you need diverse clients. As in, you need clients with a diverse feature set. If all of your clients look the same, then you're just playing a zero-sum game against each other. To get diverse clients, you need flexible client design. You need the ability to actually make your client different than the other ones. Turns out our networking protocols don't really allow that, and so if you want flexible client design in the Ethereum ecosystem, you're going to have to actually change some of the networking protocols that all of these clients live on. And it turns out that in order to get buy-in for changing the network protocols, you got to get Geth's buy-in. And I worked on trying to get them to do some of this stuff for a while, repeatedly for a while. It turns out they don't care that much. And I don't mean that as any negative thing towards them. Their job is holding up the core of the protocol. And the networking protocols that we have, they serve that just fine for them. Geth's doing just fine with the network protocols that we have. And so this is where coming in and trying to play a fundamentally different game comes in. And so somewhere a couple years ago, I had the bright idea of, well, let's build a whole new set of networking protocols. So that's what we're doing. The Portal network is a fundamentally different game. Hence this, you can't get there from here concept. I tried to evolve the networking protocols that Ethereum clients use into something new. It wasn't a viable path to get to where we needed to go. And thus, building this whole new set of protocols that come at the problem from a completely different direction. Yes, we're going towards lightweight protocol access and light clients and functional things like that. The other thing that I hope to unlock from, up on top of this fanciful, beautiful mountain with gold on top, that none of the other clients are on top of. No, the thing that I'm hoping to unlock here is the option for other Ethereum clients to change what their client looks like, to develop different functionality that doesn't look like the other clients, to allow them to branch out in different directions. Because right now, the protocols that they're all stuck on and they all use, they dictate a lot about what their clients look like. I'd like a world where that's not the case, and I'd also like a world where we have light clients. This is supposed to be the view from the top of that mountain. Somewhere towards the end of this year, I expect to do that community call, because one of the things, if you remember, we're building a network where not only do the people with big pieces of hardware, like full nodes, get to contribute to this, but if you want to turn one of these on your laptop, you will actually be contributing to something tangible and valuable to Ethereum's ecosystem. And we're going to hit that point somewhere towards the end of this year, hence the little star in this graph. That's what I got to talk to you about today. Anybody got any questions?
Very, very interesting. Piper? I think we have one question right here in the back. Shoot.
Yes, very easy. You talk about Raspberry Pi. Could you precise on which version of Raspberry Pi?
We don't have hardware numbers right now, so I'm just going to be really upfront that these are targets and not things that we've measured. But you should be able to make a meaningful contribution to this network with half of a core of a CPU and a gig of RAM and 500 megs of disk.
Okay, so I could run it on a Raspberry Pi 3 without, at least to benchmark it or to see how it works.
Yeah, I mean, the goal for each of these networks is no height requirements. That if you want to show up with a core of CPU and a slow DSL connection and 100 megs of disk to give us, great.
Okay, thank you.
That's a pretty good answer. Who's got another question? Right here in the front? Or, yeah, maybe, well.
So is it incentivized BitTorrent style in that in order to get some service from the network, you have to provide some service back, or is there some other incentivization in the
There
background?
is no quality. Our clients are dumb at the moment because we're kind of just getting off the ground. So at present, There are no incentive systems. There is no there's nothing in there built for that. The idea is to make the barrier to entry low enough that contributing to the network is disappears into the kind of gap space in your machine where it's not really a big deal to leave one of these on in the background. It's not saturating your bandwidth. It's not running your CPU at full tilt, right? It's intended to be something that is lightweight. And the networks themselves are designed to allow you to tune your participation. So if it is eating too much of your machine's resources and you want to turn it down, the networks are designed to have knobs so that you can turn that participation knob down. It's a thing that we're going to have to iterate on over time. This is we're in kind of this tight iteration cycle loop, and the first goal is get something up and functional, and then figure out where the slow parts are and attack those.
Thank you.
Cool. And over here.
Thank you. So you mentioned DiskV5 as one of the protocols that you are building on. Is it part of the protocol stack, or you are building on DiskV5?
We have built our protocol on DiskV5. It's a UDP-based protocol, connectionless. It does exclude browsers, but we do really like the connectionless aspect of it, and not having to build a whole base protocol along with this was a nice starting point.
Thanks.
All right. Any other questions up here around? No, can I ask you one question myself?
Go for it.
The team, group, community working on this, how's it going? Are you looking for more contributors, help, or you have a lot of help already?
I think that the kind of help that we're looking for is less the harder development help and more of the community building, soft skills, that sort of thing, as well as people who are interested in building more hackathon project type things on top of this. I think that's an answer.
Okay. So, and as you move towards the end of the year with launch and all this kind of stuff, you're going to look for the hype, the spread the word.
I imagine that we start looking for more help around that time.
Yeah. Okay. Very cool. If there's no other questions, thanks a lot, Piper. Very interesting.
You're welcome.
Good. All right. All right. We'll have our next presentation from Daniel Nagy and Swarm in just a few minutes. Stay put, stay with us. That'll be coming up in just a minute. Here we are again. Thanks for joining us this afternoon, Saturday afternoon. Our next presentation is from another Daniel. I'm feeling a little bit overwhelmed. We had two Daniels on the panel discussion before. Now we welcome Daniel Nagy from Swarm. We also heard about decentralized storage earlier, and he's going to be talking about Swarm and decentralized storage now. Please welcome Daniel.
And where's the clicker? Oh, there. Thank you. So, hello everyone. Just doesn't work. Oh. So I'm going to talk about the storage incentives in the Swarm network. That's not the only incentive system. There's also a bandwidth sharing incentive system, but I'm not going to talk about that one. So now I'm only going to discuss how the Swarm network incentivizes nodes to store what they're supposed to store, and how it incentivizes users to only upload what they really want to be stored. So what is Swarm? So there are three things that are called Swarm, which is a decentralized storage solution, which kind of encompasses everything. It's a network, a peer-to-peer network, and it's also a content address namespace. So it's in that way, it's similar to IPFS, but it's dissimilar in that it also is a storage network. So it actually stores data, not only indexes where everything is stored. So here's a quick overview of how Swarm works. Very, very superficial introduction. So all data is broken up into small 4-kilobyte chunks. They are redundantly distributed among the nodes. It's all stored in a DHT, meaning that node addresses and chunk addresses come from the same namespace, and nodes actually store what is closest to them. So the content is divided up based upon the first few bits of their content address, and those bits determine which set of nodes is going to store it redundantly. And these groups of nodes that are supposed to store the same content, we call them neighborhoods. So when I'm talking about neighborhoods of nodes, this is what I mean. Why do we need incentives? Well, first and foremost is to protect against spam. So before the times of the blockchain, there were several attempts at creating distributed content addressed storage networks, and basically all of them were swamped with frivolous content that nobody really cared about, but they were just overwhelmed by uploads. So, and they did not reward the participation in any meaningful way. So basically what happened was that the amount of data that needed to be stored in them just grew, and participation became more and more expensive, and then basically participants gave up on them. So we need an incentive system in order to motivate participation of storers. And also we need an incentive system in order to make the allocation of storage resources efficient. So basically to store as much relevant content as possible. And here the emphasis is on relevant, because we actually want those who upload to prioritize what they actually really want to upload and for how long they want everybody to store it. And we also want to provide adequate redundancy, meaning that we expect some churn in the network, so nodes come and go, and we want to make sure that content is not lost because some nodes go offline. So how do we implement it? it's implemented as a set of smart contracts on an EVM-compatible blockchain. Currently, we're using Gnosis. Originally, we wanted to do it on the Ethereum main chain, but unfortunately, it has become too expensive. And we're not married to Gnosis, so basically, any layer 2 solution that fits the bill is a good candidate for running this incentive system. And we have an ERC20 token that is issued and redeemed on the mainnet, on Ethereum mainnet, and we chose Gnosis because it has good ERC20 bridges that are sufficiently trustless and reliable. And the way the whole thing is implemented is a shelling game. So this is how you make these smart contracts aware of what is happening off-chain, namely in the storage itself. So shelling games are a standard way of making smart contracts aware of some state of the world which is outside of the blockchain. So basically, in 2 sentences, what happens is that uploaders pay and storers get paid. So there's a way of redistributing these payments to the storers. And this presentation is basically about how uploaders pay and then about how storers get to receive this payment. So uploaders pay by affixing so-called postage stamps to each of these 4 kilobyte chunks. Postage stamps are purchased in batches by on-chain transactions by registering a public key and the batch size with a smart contract. And once that public key is registered, you can attach a little bit of metadata to each of these chunks and seal it with a digital signature that can be verified with this public key. And this way, each uploaded chunk is marked in a reliable way that it has been paid for. So once the network receives a chunk, it knows whether this chunk has been paid for or not. And it only needs to look into the state of this contract to see whether the payment of this chunk is sufficient, because all these postage stamp batches have a balance associated with them, which gets regularly debited. So there's a rent that uploaders need to pay in order to keep data on the blockchain, in Swarm. And so this rent is paid in this token, BZZ, per chunk per day, let's say. So basically, it's proportional to the amount of data that you store and the duration of storage. The rent is going to be continually adjusted according to supply and demand. If there's time, I'm going to talk about it. If not, then please ask me and I will answer questions about it. But the short story is that the more saturated the network is, the higher the rent becomes. And if the network gets, if there's less data to store, then the rent goes down. And batches with zero balance are, of course, invalidated and the corresponding content is garbage collected. So now we have a mechanism of collecting payment from uploaders and marking data that needs to be stored in an unambiguous fashion. And we need to redistribute these funds among the storer nodes. So how do we do it? So it's a randomized game where participation is tied to storing stamped content. So if a node is storing what they're supposed to store, then they are going to be rewarded from time to time. And because we have these neighborhoods, of course, they're not going to be storing exactly the same data because there are some latencies involved in how data is propagated, so there's no exact consensus on what needs to be stored, but there's a rough consensus. So all the postage stamp chunks whose content address begins with the same bits with which the overlay address of the storer node begins must be stored by all the storer nodes that have this property. So essentially, all the nodes in a neighborhood agree on what needs to be stored, although it's not an exact match, so we cannot verify exact equivalence of what they're storing, but they still can verify each other whether they're storing the same thing. And in order to be Sybil resistance, so in order to prevent like fake nodes that use the same storage but just pretend to be more nodes than they are, nodes need to put down a stake in order to participate. And then we have this redistribution game that happens regularly in rounds. So first we have an on-chain oracle that picks a winning neighborhood. This is done with uniform probability, independently of how much stake is in each neighborhood. So basically each neighborhood has an equal chance of being selected. Then nodes in that neighborhood commit to and then reveal the Merkle hash of a deterministically chosen random sample. So the reason we're doing this random sampling instead of building a Merkle hash of everything is precisely in order to have a little bit of tolerance to not storing exactly the same. So if the random sample has a large chance of being the same, even if there's a few chunks of difference between what they're storing, because the chunks haven't arrived to some of the nodes in the neighborhoods yet. But they are expected to agree on that random sample. And then the correct sample is chosen with a probability that is proportional to stakes. So an alternative could have been that the majority stake vote is taken as the source of truth, but we decided against this because it would have meant that with a large enough stake, you can reliably take over a neighborhood and without any risk, basically censor. And with this choice that the source of truth is chosen in proportion to with a probability proportional to stakes, we have the property that usually most of the time the majority stake will get its way, but even the majority stake is not safe from having a different opinion from what the truth is if they play dishonestly. So this is an additional incentive to play honestly, because otherwise, even if you're in a majority, you risk to have your stake frozen. So currently, if you're not revealing the same Merkle hash that the source of truth revealed, then you get your stakes frozen. Maybe in the future we're going to introduce slashing. Currently we're only freezing because we don't want to punish too harshly the participants, because our software can have bugs in it, so there can be reasons for losing the game even if there's no bad intent on your part. So currently we're just freezing stakes, but that might change in the future. And then from those who did reveal the correct Merkle root, again with a probability which is proportional to the stake, the winner is chosen and the winner gets the reward. The smart contract is structured in such a way that the winner is the one who executes most of the housekeeping and therefore pays the gas price for it. So of these three kinds of transactions that are submitted by participants, the claim payout transaction is by far the most expensive, and the commit and reveal transactions are actually cheap. And there's also some technicalities, like when can you top up your stakes. We're also thinking about stakes to be withdrawable after some grace period. So, but these are really technicalities. So this is the basic mechanics of redistribution. And just to reiterate, the only safe strategy is the Schelling point, which is to play honestly. And since every reward is proportional to stakes, it's never worth operating sock puppets, because you can achieve the same by just pooling the stakes and operating one node honestly. So basically, this is the incentive system. And I would also like to discuss how Swarm, given this incentive system, can possibly be used for roll-ups data availability, because superficially it seems like a perfect fit, that here's a network where you can cheaply store data for a potentially short period of time, so you don't have to store it indefinitely, you don't have to pay for it to be stored forever. You can actually store data for a given period of time. There are some nodes that are incentivized to store it. So it looks like it looks like a good match. The problem is that Swarm cannot provide data availability guarantees of the kind that, for example, Danksharding can, that given certain assumptions and this regular sampling, you can give some number really close to 1, which is the probability that you're going to get your data back. And also, there are these more philosophical questions that data availability can be subjective. So something that is available for me may not be available for you. So what we came up with is that we can assume that layer 1 data, so what's on the blockchain, is available to all, but it's very expensive. So basically you want to use that only as a last resort. And in order to provide some kind of guarantee of availability, instead of the statistical availability, you can statistical guarantee, you can provide an economic guarantee that there's some state guarantor, which can be the sequencer of the rollup themselves. So they have a stake, and they have an on-chain commitment to the Merkle root of the data, of the transaction data in this case, and the duration for which they are making it available. And what they do is they upload the data to Swarm, and they monitor the smart contract, because the rent might go up and down, and if it goes up, then they might need to top the batch price up. So basically, they need to keep the data available and pay for it. And there's this smart contract to which they committed, and one particular transaction type with which you can communicate with this smart contract is an unavailability challenge, that you can claim as a user that, hey, this specific transaction, which is the number whatever in this Merkle root, in this Merkle tree, is not available. I claim that this is not available. I could not download it from Swarm. And at this point, if challenged, the guarantor has basically two options.
Either they respond to this challenge and they upload the whole transaction to layer 1. And in this case, it was very expensive for both of them. So both the challenger and the guarantor had made a layer 1 transaction, and they paid the gas cost of it, but the data ended up on layer 1, where we assume it to be available to all. Or, if it's really not available, then the challenger is reimbursed and the guarantor loses their stake. Which means, so it's an economic guarantee that if the data becomes unavailable, then the guarantor will lose this amount of money. And maybe this model is actually workable for rollups to store transaction data in Swarm, because most of the time these challenge responses will not happen, because if the data is really available, you're not going to do the challenge because it costs you and you gain nothing. So it's basically just a griefing attack, but it's costly, so it's not free. And it's relatively cheap for the responder, so it's a griefing attack, but not a devastating one. So if the data is really available, there's no reason to do that. So it's not going to happen. So it's only there as a deterrent. And the storage incentives that I have introduced in the first half of my presentation actually incentivize the participants of the network to store them. And there's a separate set of incentives built into Swarm, which are the bandwidth incentives, which incentivize the nodes to actually make data that they do store also available. So there's an incentivized network that is incentivized to store and make the data available on one hand, and on the other hand, we have the state guarantor that is going to lose funds if he doesn't keep this data on this network. But if something happens, like something extraordinary happens, then of course we still have the fallback to resolve the dispute on layer 1, and in the worst case the sequencer will have to upload part of the transaction data to layer 1. So thank you, that was my presentation. I see that I still have more than 5 minutes for questions, so please go ahead and ask me.
Thank you very much, Daniel. Well done. Very informative. And yes, we would have time for 1 or 2 questions from the audience, if there are some.
Thank you, Daniel. So my question is that the 4 kilobytes looks like a small choice to me, because just a digital signature has some size. I'm sure there is a lot of metadata potentially for every chunk. So how was that chosen, that the chunk size is 4 kilobytes?
So the 4 kilobytes seems to be kind of a popular choice in chunking up data. So it used to be the basic unit in which SSDs operate. That's not the case anymore. But when this choice was made, it was still the case. And also there are other systems. So one example is a SQL database called SQLite, very popular. All of you have an SQLite database in your pocket, because probably that's how your mobile phone stores the address book and many other things. And one of the things that you can do with SQLite is to, so SQLite transforms SQL queries into file operations on one single file, which you can also transform into range queries, HTTP range queries, which are compatible with the Swarm API. So what you can do is you can store a huge SQLite database on Swarm and have a client-side SQLite. So there's a SQLite implementation in JavaScript on the client side. And then you have the full power of SQL queries, and you can very efficiently access Swarm. So this 4 kilobytes comes from the fact that many other systems have this kind of chunk size, but it's not dictated by anything in particular.
Okay, cool. I have one more question, but maybe...
Go ahead while you're there.
Okay, cool. So my other question is, so this is basically kind of similar to Ethereum staking. I just also need a hard disk, right? So in some sense, your competition is Ethereum mainnet staking, right? If they are paying, let's say, 5%, or I don't know, 3%, what's the current percentage, then to use my money and make my money work on Swarm, I also have to buy a hard disk and do a little bit more than Ethereum staking, simple mainline Ethereum staking. So my question is that how much free space do you have in the calculation, that how much the interest on the mainnet can increase before it's totally not possible anymore to use Swarm because everybody will just go to stake Ethereum on mainnet?
So as I said, we have a mechanism that adjusts the rent. And if nodes leave the Swarm network because it's not worth staking, by the way, I disagree that operating Swarm involves more work than validating Ethereum. Validating Ethereum is also hard work. It requires different resources. But anyway, if nodes are leaving the Swarm network, it creates a shortage of supply when we still have a lot of demand, meaning that this price adjustment mechanism will increase the rent and will keep increasing the rent until this situation persists, which will increase the kind of interest that you earn on your stake in Swarm. So there's going to be a market mechanism that adjusts the rent if nodes are leaving the network.
Yeah, but only until it's reasonable, right? So
yeah,
when AWS is cheaper, so how much leeway do you have compared to AWS or something like that?
So I would say that AWS is not a direct competitor. So unlike some other decentralized solutions, and here, for example, StorageJ being a prime example, so they want to compete head-on with AWS. I think Swarm is not a competition to AWS in that there are many use cases when AWS is the preferable choice. Swarm is a decentralized censorship-resistant network, which means that it serves the needs of those who need this kind of decentralization and censorship resistance, which AWS obviously doesn't provide, and it might have a very different price from AWS.
Okay, we have 1 minute and 20 seconds. Was there one more question? The lady here on the side.
Yes, can you elaborate a bit more about the rent is adjusted to the available storage? Do you mean also the available storage in a certain neighborhood? And if this rent is adjusted, how does it work when you have a disrupted application that is taking a lot of space? And what happened with the previous stored data?
Right. So the incentives are laid out in such a way that we can kind of count on nodes being uniformly distributed across neighborhoods. So all the neighborhoods have roughly the same redundancy. I'm saying roughly because it's never equal, never exact. And this rate adjustment mechanism works as part of this iterated redistribution game. And indeed, each round only looks at one neighborhood. So if in one neighborhood we have a shortage, then the rent is nudged up a little bit. And if we have an abundance, then the rent is nudged down a little bit, and it only looks at one neighborhood. But in each round, we're looking at a different neighborhood, meaning that if this is just a statistical fluke that due to random chance there's one neighborhood that is underserved, it will not have a dramatic effect on the rent, and everything that happens in the rest of the neighborhoods will kind of equalize it out. But if there's a systemic shortage, like there's a lot of data uploaded to Swarm, it means that because of the uniform distribution of the hash function and the uniform distribution of nodes, we can expect that we're going to have a shortage in the majority of the neighborhoods, meaning that in each round of the redistribution, the signal will be the same to, hey, increase the rent, increase the rent, increase the rent.
Okay, thank you very much. We've come to the conclusion of this presentation. Daniel, thank you very much. Very interesting. I assume you'll be available afterwards for some more questions. Thank you. A round of applause for Daniel.
Thank you.
We heard a little bit about data availability, and now Csaba is going to talk about the same topic. Over to you, sir.
Thank you. Okay, yeah, we're all set. So, yep, things settle. Okay, so my talk will be about the networking aspects of data availability sampling, specific to the Ethereum context. This is a work that we jointly done by Leonardo and Dimitri, who are my colleagues at Status. Status you might know from the Status Hub, from KeyCard, from the Nimbus client. And we are all in the Codex team, which is working on decentralized storage technologies. And this work is funded by an Ethereum Foundation grant. So thanks to the Ethereum Foundation, we can work on this. So what is data availability sampling and why we need it? As I said, we are focusing on the Ethereum context. So data availability sampling is a generic technique. But in the Ethereum context, it's really the key, the new key to scale Ethereum. So the goal, what we have here is really increase the block size beyond what a single node can handle without really making the nodes heavy, so without changing the requirements on the nodes themselves. So the question we should pose ourselves is how can we go and increase the block size so that put ourselves in a situation where nodes cannot download the block and yet have the system working. And thinking of this, double sharding, proto-dank sharding, dank sharding, there are some underlying realizations. I was listing here 3. One is that there is data, which is sitting in data blobs, which nodes do not have to interpret. So if nodes do not have to interpret it, they actually don't need to download it to interpret it. They're really downloading it for something else. Currently, they're downloading it. And what they're downloading for is really to know that the data is available, that the data was released, that it's not withheld. So that's the only reason they are downloading. So you can do something else. And the something else that you can do is sampling. It's probabilistic sampling. So the other realization is you don't have to go deterministic and download all the block. You can do a probabilistic sampling, a statistical test. And based on that, you can hope to be lucky enough to figure out if data was not actually released, and thus you know that the data is not available, and you can disregard that block. So we arrive to sampling, and as I said, we have a statistical test. The data, the block is segmented, and there's a sampling process going on, picking a piece, or maybe more pieces of the many pieces, and based on that, deciding whether we believe the data is available or we don't believe the data is available. So the first thing we do is segment and sample. So the data is in some state. It's either available or not. And it's segmented, and you're asking for one of these pieces. And if there were k segments and you are asking for one of these k segments, you have 1/k probability that you figure out that it was not available if you're on the right side. If you're on the left side and it's available, you're fine. You will always find it available. And you can ask for more samples. You can ask for S samples of the many k pieces, And you have this linearly growing probability of figuring out that it's not available if it's not available. The problem is that this is linearly growing, so you're not really gaining anything with the sampling. Statistically, this is quite wrong. So what you do is you are extending the code. You are using read-sum encoding, erasure coding, and you are extending the data. You are adding read-sum encoding, which has the base property that if any k, in this example 4, of the pieces are available, of the extended 8 pieces, then you can reconstruct the data. So when it's all available, it's fine. But what you see below is also repairable, right? So you have 4 pieces missing, the red ones. 4 pieces are there, 2 which were generated parity data, 2 of the original pieces. So you can reconstruct the data. So you can look at it as the data being still available. This interesting part is when 5 pieces are missing, and then the data is not available. And in that case, you have kind of 1/2, in this example a bit more probability, but if there are many segments, it's 1/2 probability that you figure out that the data is not there with one little single sample. And the nice thing is that if you have 2 samples, you have 0 or 4, and if you have S samples, you have 1 minus 1/2 to the k probability of figuring out. So it's kind of vanishing probability with the number of samples, if you have many segments, that you figure out with a statistical test that the data is not available. And we are happy with this. No, we are not. Because there is a problem. There was a read-sum encoding, we think, but actually we don't know that those pieces which were there can be used to regenerate the original data. They can be just random data. We will sample it. We will find out that the piece is there, a piece is there, something is there, and we believe that the data is there because our test is showing that. But they cannot actually be used to reconstruct the data. So in the example you see there, actually there are 5 pieces missing. We just don't know. We sample, we get something, we believe it, and that's wrong. So that's why we have to segment, we have to extend the data, then we have to prove each single piece, and then we will sample. So what's happening is that we are proving the read-sum code, and this is going with a KZG commitment. So there is a commitment to the data. Each single sample proof has, each single segment has a proof attached. So if you have the commitment, a single segment, and the proof, these together enable you to verify that the sample is actually coming from the correct read-sum encoding. So your math is working again. If you sample and you get something, you know it can be used to reconstruct. So once you segment, extend, prove, and sample, you are having something which can be used to guess whether the data is available or not. Now, this would be very nice, but this is not what is being planned in Ethereum. That's a slightly bit more convoluted. It's just a nice little step. So this is what it is. So this is how block encoding is planned in the next evolution. Where the K that you see there, the 64K, is not the K that you've seen before. This is kilo. So this is 64,000 segments. So the data block, which is 32 megabytes, is divided into 64,000 segments, which is half a kilobyte per segment. And then over this, there is a read-sum encoding, but it's not a normal read-sum encoding. It's a 2-dimensional read-sum encoding, which has a nice property that if you have K pieces, so it's in this case 256 pieces of an individual row, then you can reconstruct the row. Or if you have 256 pieces of an individual column, then you can reconstruct the column. So it is extended to 256,000 segments, each one being half a kilobyte, and we have 128 megabytes of data. And this is kind of our new block that we are going to sample on. And of course, there are KZG commitments. So you see the numbers there. For the 128 megabytes of data, you have something like, I don't find it now. 12 megabytes of KZG commitments added. So you have this extended set of data, of which the top left corner is the original data. And sampling is going over this. Now, let's have a little quiz. So, is data available if these segments are there, the blue ones, and the white segments are not there? And you would say, yes, this is the original data. This is data from which the extra data was generated. So obviously, this is repairable, and this is available. And with rows and columns, you can easily repair it. You can see I repair the row, you can repair all the rows. From those, you can repair all the columns. And yes, it's repairable. Let's take another example. Is this repairable or not? And this doesn't seem that obvious, right? But if you see that you can repair that column, for example, you see that you can repair all those, that row, you see that you can repair all those rows, and you can repair the columns, and at the end, yes, that was repairable. What about this one? Maybe notice that in these, going back a little bit, only 25% of the data was available. So what about this one, where we have almost 75% of the extended block available? Sounds like repairable, right? But actually it is not. It is not because you cannot repair anything. There is no row or column where you can start repairing. In every row or column, you either have a row or column already there, so you cannot repair it because it's already repaired, or you have only 3 pieces, so you cannot start repairing. So this is a no, right? What about this one? So there are different reasonings here. One is we just simply don't have enough data to have it repairable. It's less data than the original data. It can't be repairable. You can extend it, and you get back to the previous one, and you see this is not repairable. So we have this nice data structure, and we understand how repairing works on this, and we understand how sampling into this could work. But actually, this is not done locally. This is done over the network. So let's see the networking perspective. Let's see what happens on the network, actually, when we are sampling. So how we check data availability over the network in the context of Ethereum. So notice that in the context of Ethereum, there are different nodes, and they have different goals. So validators and full nodes have different goals that they want to achieve from this extended set of data. Validators, their goal is they should either generate many attestations if the data was available, or they should generate very few attestations if the data was not available. And that's the system level goal. We don't like things in between. For nodes, it's a bit different. They want to find out, with a very high probability, during the statistical sampling, if the data is not available. Because if it's not available, then it can be a block, which maybe it was even validated, but maybe there is some supermajority malicious among the validators, or maybe for other reasons. It should not be accepted. So if it figures out that it is not available, then there might be data withhold, and depending on the use of this data, whether it's used for an optimistic rollup or whether it's used for a ZK rollup, there are different use cases, but for each one of these, if the data is withhold, it can be a huge problem. So we have to get the data from the block builder to the validators and to the nodes in a way that they can satisfy this. So it's actually a process which goes through many steps. There are individual pieces here. So there is the block is being created, extended, as I was showing. then the block proposer or the builder is disseminating the rows and the columns to the validators, and the validators do the job of validating or not. And then there is another thing, which is the data is pushed into a neutral structure, a DHT, from which then the nodes can sample. And then this structure might also need repairing because nodes are leaving, there is churn. So there are all these processes going on behind the scene. Now today I will focus on the dissemination of samples to the validators. So I will not go into the DHT part, and I will not go into the actual sampling over the DHT. But let's see what happens between the block producer and the validators. So from builders to validators. Each validator is checking a number of rows and columns, and by default we are speaking of 2 because it's an easy example. It's a variable parameter at the moment. So each validator is selecting randomly 2 rows and 2 columns, and they are checking that. And that's the check. Is it there or not there? And just to give you a bit of dimensions of the problem, so we have 500,000 plus validators, around 8,000 plus beacon nodes behind which these validators are sitting. You have those 260K segments, which are sitting in 1,024 rows and columns. And we have something like 4 seconds to do this. So how do we do it? There are different proposals out there. The base proposal that I'm speaking of now is to use a gossip sub, or a gossip sub-like protocol, I would say, because I don't think it will be the gossip sub as of now, whichever version. So we use a gossip sub-like protocol, and we knew a number of topics in gossip sub. So if you know gossip sub, you know what it means. If you don't know, gossip sub is building a mesh network, like you see there. Those are beacon nodes behind which you have validators which are interested in the 243rd column, and they form a small mesh network with a given degree in which they are sending the column so that everyone has it. And you have 1,024 of these networks built. And we like gossip sub, and we like gossip sub-like protocols, because they are robust. They have different reliability mechanisms. So one is that they are building this mesh to push. They are sending gossip messages so that nodes can pull information. And they have also, using reliable transport, they are using TCP. Gossip sub also has downsides. They send lots of duplicates, and they are not yet ready for large messages. But you see, we are not just using the gossip sub here. We have 2 more technologies here. Like you have the Azure coding, and we have this 2D structure. So we are adding 2 more layers of reliability. We have the Reed-Solomon code, which we can use as a forward error correction code from communications, if you know that. So basically, if you have half the row, if you received it, your node, you received a half, whichever half number of segments, you can repair it. And the topics are cross-connected. So if you receive something on a row, you have it on a column. So we can use these 2 techniques as well. So we have 5 reliability mechanisms there with which we can play to have a system which works well. So what we did is a simulator for this. It's in Python, which is nicely accessible, we hope, for others. It's very much work in progress, and everything I show here is preliminary. So don't take the exact numbers. And we do many simplifying assumptions from the networking perspective. We don't care about TCP slow start. We have 100 millisecond round trip time at the moment. And this is what you see on the right side is one single dissemination with a builder which has 1,000 megabits per second link. This is a conservative estimate, but we are not counting with some factors. We have 5,400 nodes, which are kind of solo takers, one validator with a smaller bandwidth. And we have 1,600 nodes, which are having their beacon nodes handling a bunch of validators and having a better network connectivity. And what you see on the right side is kind of the progress, the evolution. So on the top, Below there's the time, so we are arriving to 1 second. And in 1 second, nodes are receiving samples, and validators start to validate. Validators validate when they have all the rows and columns. And then you also see a bunch of network statistics. What is the transmission bandwidth, the reception bandwidth, and how many duplicates you have. Now how we use this. Let's see one example. This is about message size. So I said we are sending rows and columns, but you can do it in many ways. So on the left side, what you have is sending, using Gossip Sub with messages being rows and messages being columns. So the message is 280 kilobytes. This is the big message case. And what you see there is that to validate, so that for the green curve to go up, we need something like 1.6, 1.7 seconds. On the right side, we are using small segments. So small messages. So every segment of those 260,000 is a message. And then we are much faster. Another example of the simulator is checking boundary conditions. So what you see on the top is something which we know is repairable and available. What you see at the bottom is something which we know is not repairable and thus should be not available, should not be validated. What you see on the right side is validators, basically all of them, validating what's on the left, what's on the top in a second and something. Below, what you see is that validation progress is stuck at a low percentage. Obviously, no one has more than 75% of the chunks of these segments, and this is what we wanted to achieve. So we have the simulator now. As I said, it's quite work in progress. We are using it to kind of figure out the right combinations, figure out what Gossip Sub like means. So we are experimenting with different variations. We will improve the simulation fidelity. We will do parameter space exploration. The curves I've shown you were single runs, so they are definitely not statistically relevant. Exploring attacks, and then dealing with the other parts of the dissemination to DDHT and of the sampling. So, thank you. If there are any questions.
Thank you, Csaba. Super interesting. Again, very in-depth. Any in-depth questions from the audience? Over here.
So I wonder if all the blocks that are meant to be available for the period that this is under consensus are constantly sampled by the validators.
Why they are constantly sampled?
No, I'm asking is like if block availability should be like, I don't know, 2 weeks, then all the 2 weeks worth of blocks are constantly, each of them are sampled from the DHT by nodes.
Why nodes are constantly sampling it? So the validators are doing the verification because they don't validate if they don't see it available. The nodes are doing it because they also want to be protected against the case when the validators themselves have a supermajority of malicious misbehaving nodes. So it's kind of a case where they just don't believe everything to the validators.
Okay. Another question from the audience? No. Going once. Going twice. 2.5, 2.75, 2.8. Okay. Very good. Thanks again, Csaba.
Thank you.
We have just 5 minutes before our final panel discussion of the day. It's one I think you won't want to miss on staking after the Shapella upgrade. Please stick around in 5 more minutes for the final panel discussion. All right, ladies and gentlemen, the final panel discussion of the day. Please take your seats. It's going to be full on, in-depth, super, super interesting. And the person who's going to lead the entire discussion about staking after the Shapella upgrade on Ethereum is Aliyah. So take it away, Aliyah.
Thank you very much. Thank you all so much for being here. It's 5:20 on the end of day 2, and you're all still here. So first, a round of applause to yourselves for the stamina. Good job, team. And this is a really topical panel, because when we looked at the description of it, they said, there's a scheduled upgrade in Ethereum. And here we are actually 2 days after the upgrade. So it's a really good time to, I think, be talking about this, especially with this distinguished lot of people that I have here. So before we really dive in, I'm going to ask you guys to kind of go down the line and introduce yourselves, who you are, what you do, and how you got here. Really quick, though. Sorry.
Okay. So, hey guys, pleasure to be here. I'm Lior, Israeli by origin, and I'm the legal counsel of Stake Capital, mainly Stake DAO, so deep down in the DeFi space. I'm in the blockchain space since 2010, doing many stuff since then, building stuff, not always as a lawyer, so entrepreneur also. In the last years, I'm mainly dealing with law.
Amazing. Next in line.
Cool. I'm Nicholas Kunkel. I was a founding member of MakerDAO. Currently, I am the Oracle Core Unit Facilitator at MakerDAO, and more recently became the founder of Chronicle Labs, who is building a decentralized Oracle protocol.
Awesome. And Mara doesn't really need an introduction, but I'm going to ask her anyway.
My name is Mara Schmid. I'm the CEO at Alluvial. We're an enterprise-grade liquid staking protocol that's focused on enabling mainstream adoption across the market. Prior to starting Alluvial, I actually managed the business and sales team at Coinbase Cloud and Bison Trails before that, so I've spent a lot of time in the staking space over the last couple of years, and very excited about our discussion.
Awesome. And Michael.
Hi, I'm Michael Messler. I'm CEO of Pillar Project and also Ethersport. And with Ethersport, we bring an account abstraction solution. What I mean by that jargon is we try to give Web3 a Web2-like UX. So we talk about mass adaptation. If it ain't usable, it's not going to be adapted. So I'll talk more about that tomorrow. I'm just plugging in, so thank you.
And Mario.
Hey, everyone. Thank you so much for coming. Mario, I work with Ethereum Foundation in protocol support team. So protocol support is generally helping with like coordination. I'm doing some research, and I've been actually helping a little bit with Shapella testing and so on. And I've been running the protocol fellowship, created toys for creating entropy using cats and stuff like that. Yeah.
Perfect, perfect. And maybe just sticking with Shapella, since it's basically the top of everyone's mind right now. And to you, Mario, how do you think the upgrade went?
Well, I mean, the Ethereum is still running, right? Yeah, let me check it's making blocks, right? Yeah, I mean, it went pretty smooth. So technically speaking, like, I don't know what else to say. We get few very minor bugs. The participation rate with the attestation dropped like 5% maybe. So normally Ethereum is operating with like 99.5 and more percent validators attesting and working, and we need like 2/3, which means 66 or like, I don't know, let's say 70% would be like the bottom. So, yeah, very good when the lowest we saw like was 94 point something, so around 5% less. And this was just minor bugs. There was bugs with Prism and MEV boost. There was a minor bug in Lighthouse, which caused a lot of CPU usage because during the fork we saw a lot of the updates of the keys which you need to do to withdraw the funds. So that just clients are going to handle, but generally it was smooth, it's there. And of course, the biggest upgrade of the Ethereum now is finished thanks to the push zero, which was like the most important thing in Chapella. Do you know about push zero actually?
Tell us about it.
Yeah, push zero pushes zero on the stack. You can do it with the opcode push and zero, like pushing zero, but now it's in one code and you can save 1 byte. It's like the best change in the, no, okay. I'm trying to troll a little, sorry. So like the withdrawals were the main thing, but there was other small changes on the EVM, so it's all running all smooth.
Perfect. Would any of you guys want to add to that? Feelings about Chapella and the upgrade? Yeah.
Should I say something?
I heard you take a deep breath. I was expecting something.
No. It's a deeper of thinking. You see the Ether value going up. Everything is okay. Everything, really. It's part of this evolution that we see in the economy. The merge went okay. People were afraid from the merge. Nowadays, everything is smooth. You even less hear about it, by the way. Some of us were surprised from it, maybe. And to see it, happening so smoothly, and also it's a major change. And also, by the way, all these stakers that were waiting so much time for something to happen, it's not obvious at all. And I think you can see it's an expression of trust in the community, in the ideas, in the major project in the space, and this is my perspective.
Well, if I take it further, I'm excited by the opportunity and the challenges that it brings. Things we don't really talk about when we talk about the liquidity side is the APY rate being taken as potentially as the risk-free rate for the Ethereum space and beyond, and the kinds of products that can be built on top of that. And I find that fascinating and potential. And obviously, liquidity staking, it could be disrupted, and that is again up for a debate. So you guys have more expertise than I do on that.
Yeah. Piggybacking off that, it's been honestly one of the really, fundamental milestones, I think, that not just the community that's already invested in participating in this ecosystem, but also players that have been sitting on the sidelines have been looking towards. When you think about participation from, the traditional market, from institutions, a lot have felt that, the enablement for withdrawals and the period, the duration that this hasn't been enabled has been one of the remaining unknowns, I think, in Ethereum, core participation and market sentiment. So to echo your feedback, I'm very excited to see how we, see renewed interest and general market sentiment, attract not just innovation, but also new participation in the space.
Sure. Nick? No? All right. I mean, everyone said everything that was possible to say about Chapella, right? No, but a lot of you guys obviously work quite deep in the staking universe. And of course, now that withdrawals are possible, that's kind of been the highlight that everyone's taken away from the upgrade. But maybe looking into the sort of institutionalization of the staking universe, right? How does this impact your sort of business case and your approach to the market? And I give this back to Mara.
Yeah, I can continue where I just left off. I've been focusing on different kind of staking ecosystems for a long time. Long time as long as it's been around. Focusing on kind of enablement for the early adopters, so crypto native participants in the really early days, thinking about how to support at-home stakers through things like the Ethereum Launchpad, which was launched back in December 2020 when the Beacon Chain went live first. All the way to, how do we move along the adoption curve? Who is the next set of adopters that we're going to be able to enable, and what kind of tools, products, and capabilities do they need in order to participate in the market, but also contribute to Ethereum's, core security through staking participation? I think one of the really interesting sort of observations through the last 18 months is that institutional participation and demand is starting to, come into the market, not just through traditional staking, but also if you think about the various strategies that, hedge funds might deploy or structured product providers, the opportunity space that enables is massive. Concurrently, you've almost seen development and innovation that is developed around, what happens not just in the staking space and who participates in it. We've almost moved from a very, monolithic technology stack where node operators are sort of the end-all, be-all to a very modularized technology stack where, now we're seeing key middleware solutions around DVT and MEV relays, right? We're starting to see staking pool forms that provide different users, different value adds or, capabilities that people can build on top of. So I'm tremendously excited for that. I think we're seeing a lot of that on our side, of course, as a partner that focuses on, enabling leading custodians and other partners who service the institutional market and really catering to that on-ramp.
Sure. Maybe on your side, Leo.
Yeah, I'm thinking, first of all, institutions is a big word. I've been asked this, I've been asked this question in various, occasions on what is institutions. I think when we speak about institutions, people tend to think about traditional institutions, and that's actually something that you see quite nice in Ethereum. So staking, the ability to stake in Ethereum, and now the Shapella upgrade is even open this to more institutions and give them the certainty to invest in, because Ethereum, from a legal standpoint, is pretty much clear that this is a commodity, maybe staking. So the risk is but the risk could be mitigated for those kind of institutions. So it could be like the traditional institutions that may have this ability to invest in. Also, of course, the exchanges and the regulated exchanges like Coinbase, etc., they can invest easily. When you think about institutional investment in the more in the DeFi space, so this is for institutions that may take the risk, and this is for maybe different kind of institutions that are more like crypto oriented in that regard. So my take is that the change in Ethereum will give much more certainty for institutions from all kinds to participate in the staking activity.
If I add, what do you think of counterparty risk? Say, for instance, if I am an old institution, now I don't need to go to a third party that gives me another token. I can just take X amount of I can buy a portfolio directly into Ethereum, knowing full well I can take it back out.
Yeah, sure.
So how do you think that can then engage older family houses, old-fashioned family houses, etc., that want to dip their toes into this space and experiment with this asset class?
Yeah, I totally agree with you. And this will inject another, treasury to the industry, and then all the DeFi layer 2 LSDs, etc., will gain from it, of course.
And when we talk about institutions, like you said, it's actually a really interesting sort of difference, and it's important to identify that difference, right? When we talk about institutions as in old Swiss houses like a Nestle or a UBS versus Stake Capital, which is in fact also a form of institution, but maybe more on the DeFi side of things. How would you see sort of the difference in the attitudes towards staking by, let's say, the DeFi side of things?
Of course, if we speak about all family houses or financial institution, etc., they are bound to regulation. They have less ability to take the risks, less ability to do specific things. But when you have this more oriented crypto institutions, they are institutions at the end. There are the new generation of institutions. It works with a lot of partnerships in between those. So those new generation of institutions are actually the gate to DeFi, to some more complex real world assets. etc. So a lot of time you do these deals, complicated deals that gives the ability to some traditional money to participate in the crypto space in a safe way.
So I think more on the DeFi side of things, now that we are kind of in like a post-Shapella landscape, I think there's going to be like a significant redistribution of market share. Nothing against Lido. I love those guys, right? They clearly have a very dominant position right now. But I think when you look at why they've been able to achieve that dominance is because they've had, one, a lot of liquidity, right, for the LSD, right? But two, right, that people could also, right, that it had been integrated into, DeFi credit platforms, right? So people could leverage up on the yield, right, or, tap into the equity of that yield-bearing kind of asset. Now, post-Shapella, liquidity isn't really a constraint as much anymore, right? As soon as you can redeem, right, the liquidity buffers start mattering a lot less. And what that also means is that you're going to see a lot of the DeFi protocols start onboarding other LSDs extremely quickly. Because I can tell you from the MakerDAO perspective, and I'm sure this applies to Aave and Compound as well, is that part of the reason why we wouldn't onboard alternative LSDs, or at least not with the amount of like debt exposure that users might like, is because of the liquidity constraints. So if you unlock the liquidity constraints, you unlock the credit restraints, and all of a sudden now you have a much more competitive landscape.
So following on from that, right? So you're saying there's going to be a lot of new competitors to Lido, but what is actually the use case for a Lido staked ETH token today compared to, let's say, 5 days ago?
I wouldn't say that Lido got worse. They did not, right? People can unlock now, right? It's safer, but everything else just got better, right? And so there's more of like a leveling off type of effect.
Sure.
But would they still have a little tiny niche, because you can't just withdraw, you have to wait 27 hours, and if we were slashed even 36 days, would they have that little say, oh yeah, but you can take it out straight away kind of thing?
And for a complete, like to withdraw everything, you need to wait even 100 days. So it's a lot of time for financial activities to happen.
But generally, it was a big constraint that just the LSDs had basically lower market value, or like you were losing, I don't know, 1% or something when you are exchanging them. So now this arbitrage basically won't be necessary. And yeah, mentioning the alternative project, like I don't know, Rocket Pool had a problem exactly with this. They had little liquidity to offer, and now I hope, I'm bullish on these decentralized pools. Hopefully they will get more traction thanks to this, yeah.
For sure. And it's, I actually don't think it's a winner-take-all market at all.
That's a good thing, right?
Yeah. I think post-Shapella, if anything, as Nick mentioned, we'll probably see a lot more of a competitive market landscape and probably specialization around certain capabilities, value propositions, and other things that, will attract stakers that come from very different customer segments. I think, go for it.
No, just to dive into that. So you're saying different sorts of, I guess, value propositions around different LSDs available in the market. Maybe you can elaborate on that a bit more.
Yeah.
Without necessarily shit-talking anyone.
No. I mean, look, we have like a very particular approach. Like, I've kind of seen the market evolve. I've done research on this market since like 2020. I love the different implementations that exist. They all serve a very particular need, have different architectural, considerations. The one, thing that I found missing, when I was working at Coinbase, but also found missing across the other, partners that we were working with at the time is how do we get people to be able to contribute to Ethereum security using Robinhood. You know, knowing fully that Robinhood is not going to be able to integrate Lido because, you know, it's a company that has a compliance unit and a risk management arm and, you know, certain counterparty risk considerations and other things that, you know, will just prohibit from being able to integrate a fully decentralized backend that is just completely permissionless. So we focused on this question in the market, which is how do we get the next realm of participants on? And where do these participants interact, transact today? And how can we go away from having fully centralized architectures to centralized front ends with decentralized backends? And how can we be the bridge to that, right? To create a compelling offering that has significant advantages to the users, that has significant advantages to the businesses that are integrating it. So that has been our approach. I think one of the really interesting things, and Michael actually said this, is I think the behavioral pattern in crypto that we're going to see is like we've gone from like holding crypto, which was like the first use case, custody, to like trading crypto, and then exchanges kind of had a big moment and sort of proliferating to like what is the utility function in crypto, and staking naturally lends itself to the third sort of pillar in the adoption that we're probably going to be seeing, not just across users that are starting to onboard on the retail side, but also on the institutional side, right? So that's really like our differentiation or focus point. But again, I view different solutions as different capabilities. As someone who, you know, feels comfortable, uses a ledger, wants to use a dApp, love using liquid staking protocols that like offer me an interface that meets me where I'm at. But most people are not there. And they don't have to be, right? It's okay. So yeah, piggybacking off what Nick said, I think we're going to see some really interesting dynamics. And I'm also really excited to make this accessible to the broader public. So,
Nick, you want to add something there? You look like you had something to say.
I'm sure. I think she's kind of said it all.
Okay, then, I mean, of course, none of us have a crystal ball, but there's been a lot of sort of, let's say, speculation about what we're going to see kind of happen over the next couple of weeks as the first withdrawals start processing, and also what this means for the sort of supply demand around ETH. And maybe, Mario, you want to jump in there?
What was the question? The demand?
Supply and demand around ETH, as in, and also, I guess, maybe what percentage of ETH we'll start to see being staked now?
I cannot answer that.
No
I really don't know.
Into this.
I mean, honestly, like purely subjective. I met somebody at this conference saying, "Well, now with withdrawals, I feel comfortable to stake." Right. So I can imagine that there will be more people, hopefully home stakers, who feel more comfortable coming in a part of the institutions. And I'm not sure if we can see that yet. Like I saw some charts already. You can see some nice visualization of the withdrawals and deposits. And I think in past few, hours. It's still hours since Shapella, right? We actually saw also a spike in deposits. So maybe they will cancel out, and we will see around the roughly the same or maybe slowly. I'm like generally for the security of the network, we need or we would prefer the deposited ETH, the validators deposits going up, right? We need more security. So I'm hoping it's going to still be inclining. What worries me a bit also the LSDs, which worry me a bit, how the protocol security will handle this, or like big parties. And like just to reiterate, I just hope that if we see now the landscape changing a little with some withdrawals, some new deposits, that it will end up more distributed across different pools, technologies, and yeah.
Michael?
I mean, the stats so far do not show drastic movement. I mean, there is a net withdrawal, but within realms of expectation. And as an individual, for instance, if I'm hodling, say, let's say I have 100 ETH, I didn't feel comfortable to stake my ETH because I don't know when this thing is going to be allow me, just in case there's a run on the bank's type of scenario. Now, at least at the back of my mind, I can say, okay, I can put this portion into the staking, knowing well, within 27 hours, I can take it out. So as an individual, I feel more comfortable. Even if I was a treasurer of a certain company, I might think, because I'm sorry, but I wouldn't touch liquid staking stuff because it is exposing me to another risk. I'm not dealing with some company like like Celsius going down and.
But do you think that's the consensus view of the average person? I agree with you personally, but I think that we're rather odd in that respect. I think if you're going to hold ETH, you may as well get the yield from staking, and so to me, it's just that staking number is just going to go up only. There's just going to it's I don't know if any of you here have tried to stake on your own, right? Like I have a DApp node at home, and DApp node makes it kind of approachable. But if I asked my sister or my dad to set up a validator on a DApp node, I don't think he could, or she could. Yeah. Yet with LSDs, right? When they become a bit more ubiquitous, just presents people with a really accessible way to do staking. And post Shapella, now that you can also unstake, right? They've been de-risked significantly. So I really don't see, I don't know what the scare was about, that we would see, mass people fleeing from staking. No, it's just up only from here. And
but would you see that?
I've yet to hear any compelling argument for why that's not the case.
Then would you see then some sort of innovation where the LSDs probably allow me to stake my ETH without even touching their token, but I just want to go into ETH, get your commission.
Is your problem the token or just the counterparty risk on whatever protocol you're using?
Both. Counterparty risk is always there, but the token as well. And what if I'm so conservative and say, I just want my ETH and I don't want to touch any other ERC token, ERC20?
It's actually really interesting because it takes the presumption that you are already holding Ethereum on your balance sheet. We're talking to institutional customers who aren't even there yet. And they want to get exposure to staking rewards. So the only way they can get exposure to staking rewards is if they look at putting market neutral trading strategies on, leveraging liquid staking tokens that can be cash settled. That'll be their first entry into Ethereum because they're not even at the point where they're holding it on their balance sheet. And I think it's that innovation space that becomes super interesting when you start bringing participants in that haven't even gone through the process of approving custody holding for their entity, right? That's kind of what I'm referring to. Of course, there's going to be people between there and sort of the degens that are on the other end of the spectrum and probably on this panel. But I think there's sort of a middle ground there. I do agree with Nick, just on the dynamics of what we've seen. If you actually look at the statistics, just probably people should be checking out the rated dashboard. I actually love it. But if you look at the dynamics that we've seen, it's withdrawals are there. The withdrawal queue is probably 15 days at this point was what it hit. But when you look at the composition, it's actually mostly partial withdrawals, which means that people are just recycling their rewards. And then there's a small portion, 5-ish%, that are actually full withdrawals, people leaving the chain. And people are oh, we thought this would be so much longer. If you deposited your ETH 2 years ago, knowing you were going to be locked up for 2+ years, you're probably not trying to run for the hills anyways. You were pretty long on it to begin with. So I agree with Nick. It's probably only up from here. The more innovation that continues, the more we're creating robustness in the way that staking infrastructure is operated, the diversification of staking infrastructure between at-home stakers, enterprise stakers, liquid staking pools, and sort of the responsibilities that we all have to ensure that we're optimizing for security in a holistic way. The more participation we're going to see on a risk-free rate participation in Web3.
Also comparing to the other proof of stake protocols, the staking in Ethereum is quite low. So in the others, I guess in Ethereum it's 15%, in the others it's 30, 40.
It's 40 to 80%.
40 to 80.
Yeah. 40 to 80. But this is a sort of interesting question that kind of came from what Michael was saying before. There's going to be people who will just happily, use their Kraken or Coinbase account and just press stake, and then they're kind of done with the deal. There'll be people at home with setting up their DApp nodes. Apparently, Nick is one of those people. And somewhere in between, I think you also have and institutions who would partner directly with counterparties like Alluvial. I guess what is the benefit to me running my own node at home, and what are things that I should consider when doing that? And then on the flip side, what are the benefits to kind of just chucking it in there with Lido? And maybe Mario wants to take first hit.
Thank you for the question. Because what you mentioned to run your node, it's the only way how to use Ethereum. Literally, like that's how you use Ethereum. It's the only way how can you use Ethereum in truly trustless, private manner without it. Like the whole point of this ecosystem here is like, well, we want to avoid third parties, we want to avoid single points of failure, and then you ended up using like a wallet within Infura, which is like just a third party, and you completely trust it. So I would encourage everybody in this room to run their own node. And one thing is that, which we don't have for staking right now, but even for normal users, light clients are already a thing, I believe. But otherwise, for I've been talking to many home stakers who just help to set up the node at home, and it's mostly hobbyists, you know, like it's people who want to dedicate a little bit of time. So that's what you have to sacrifice. That's be excited about it, because you're certainly gaining the security, the privacy, and well, the sovereignty for yourself. But also you are helping the whole network. You are being one of those in the current setup where everything like the LSDs are growing. Like there's a great article on the risks of LSD by Danny Ryan. And that's one of the issues here, right? Like if the LSD grow that much that it's bigger than what we need for finality on the consensus, we might see some potential problems when these big actors can actually abuse their power. And the home stakers, they're only saving us, right? So and it's kind of amazing if you think about it, that like my little computer here at home, or I mean there were guys taking it for a hike or something, and like this here created next Ethereum block. It literally built it, decided it, okay, maybe somebody uses MEV Boost, but you can build the block in your own little computer. You can show your grandchildren, this was the block built by me, I'm part of the Ethereum history forever. So this is what you can get with your own node. And again, like you can use DAppNode. There are, what I'm hoping to see now is actually more solutions like DAppNode. They are doing a great job. There are other alternatives like Avado, there is Steerium, there is NiceNode, and I'm hoping to see more solutions like this. And if somebody's afraid of a terminal, they can use this. Otherwise, they can open up the terminal. But I'm hoping there will be more like home staking solutions which are easy. And also the pools, that's another thing. Like I already mentioned, the distributed pools, which enable you to stake some lower amount than 32 ETH, but at the same time, keep the sovereignty of your own hardware, of your running the open software on your own computer, right? And I mean, that's Rocket Pool, which is going to have the 8 ETH. There are other protocols popping up, I think Device doing same thing. And I don't want to name specifically, but we see that that's growing as well. So for many people, it will become, even with a lower capital, it will become easier to actually do this. And yeah, so that's what you are gaining, and you just you need time. What you need to dedicate is the machine, is to have the computer, which the core devs or like the community of Ethereum is working really hard to make it as simple as possible, as save as many resources as possible. That's why the gas fees are so high, by the way, right? So yeah, use the opportunity to use some, I mean, low-end hardware. I recommend using old laptop. It even has a battery. It can run on your shelf. You already have it lying around. Yeah, compared to this, just to click on some Lido thing or something, I mean, yeah, it will be always easier, but you will not help yourself, you will not help network. And I believe that in the case of the capture, in case of the, well, probably government or whatever alien invasion, you won't see that ever again, right? So you need the keys. It's not your keys, not your coin. And there is still big trust in the third parties, whether you're using the LSDs or some custodial services. Yeah.
Sure. Maybe on the other side, more positives on custodial or pooled staking solutions or alternatives to running your own node at home.
Sure. I mean, look, it's like you said, right? If you're
everyone, there's space for everyone here. Yep.
If you're staking at home, yes, you're contributing to the network, right? I think Michael, you would probably say, right, I don't have to take the counterparty risk of, you know, this LSD protocol, right? So it's risk mitigating. So we can say those are the benefits of staking at home, right? Versus the benefits of LSDs, right? You're going to have DeFi integrations, right? And so you're going to be able to basically lever up on staking yield, right? Or you're going to be able to tap into the equity of your, you know, staked ETH, right? That's while taking maybe a little bit more risk, right? So for someone who is more financially motivated, right? That's probably the best approach, right? For someone who is, you know, believes in crypto but maybe doesn't feel technically comfortable to run their own node, right? It is getting easier, but let's not kid ourselves here. It's you have to, like, you know, maintain. You have to, like, watch it every day. Make sure you're, like, hitting the attestations. Maybe your node goes down. Maybe you didn't upgrade the node in time for the hard fork, right? It's a thing you really have to babysit, right? And so from an accessibility point of view, right? I can totally understand that someone feels much more comfortable, right, going to, you know, a Rocket Pool or going to a Lido or you know, right, or some other LSD, right?
It's a great summary. I would just like, I think I also saw the visualization like that somewhere. It's basically like risk versus how comfortable you are, right? Or maybe, the leveraging the positions and stuff like this. It's also another benefit with maybe more risk.
Now, if we can stake at home and somehow find a way to plug that into DeFi, then I mean, all bets are off. Then we have the best of both worlds.
That would be awesome, to be honest, because I follow you. It just reminded me of 2017 when I was running my own node, and to just basically see the wallet interactions, etc. And it is painful.
And I'm kind of foreshadowing here because I do know some teams that are working on this, but they're still in stealth, so I'm going to keep their names private for now.
Easter eggs dropping around here, guys. Keep your ears open. Alpha. Yeah.
Yeah, but it's true. Like, I think it's not just about the question of, like, how do we make it easier or more accessible for at-home stakers, but also maybe how do we, like, take the burden of risk and self-responsibility. Like Nick said, it's work to run your own node, right? I think there's innovations that are happening in loads of different parts of the tech stack. I think DVT is a really exciting solution that can let at-home stakers sort of share and spread the risk of participation. And there's some amazing, you know, teams in the audience today that are making that possible. So I think we are seeing a lot of that. I think it's really, really healthy that we're continuing to innovate in that direction and support, you know, Ethereum core direct staking models alongside all the other capabilities that we want to see in the market to really bring crypto mainstream.
But outside of, like, the sort of ease of, you know, setting up your own node, is there any other benefit to kind of working with someone who's actually specialized in it? So with a larger pool provider or so, maybe in the distribution of rewards, or I'm asking as a person who is considering the two options in front of me.
Yeah, it depends who you are. Right? I saw sort of the evolution of, like, staking as a service companies in, like, 2018-ish, 19-ish. Like, it was a very proliferating market because it's actually really expensive if you're a company to, like, build an entire team out that, like, runs core infrastructure. And actually, you might not want to just run your own nodes because that creates a lot of risk, especially on a network that has, you know, correlated risk considerations, right? So we're seeing a lot of people move away from those architectures as is, which is actually good for the network to have that diversification and see that also across these, you know, dominant players and centralized players in the market. But it really depends what your objectives are. And I think it goes back to what Nick is saying, right? It's like, what things are you optimizing for? There will always be a breadth and spectrum of solutions that will cater to those needs, and that's healthy. That's called, like, having a healthy, mature market, and different solutions that cater to that.
Awesome. We're at about a minute or so, and I want to also leave time for questions. I'm going to go ahead and assume everybody in the audience owns some amount of ETH. You know, shoot me if I'm wrong. But let's do like a show of hands. How many of you already have staked your ETH?
Hey.
All right. And how many of you have staked your ETH at home?
Woo! My man.
There are dozens of us.
Swag t-shirts for you guys.
I wish I had cookies to offer, but I don't. I want to quickly check the audience. Is there already somebody who has a question that's better than what's on my list? And you don't know what's on my list, they're all crap, so. Anyone got questions? Otherwise, I can keep going.
Cookies for stakers is like home stakers is like a really good idea. Yeah.
They need those, eh? Okay, so maybe just going down the line, starting with Lior. What are you most bullish for in the staking landscape in the months ahead?
Ooh. Let me think. I don't think I'm bullish on something. I think I'm bullish on everything. It's really, that's why I'm here.
Up only, up only.
That's why I'm here. It's like I see it as I see always like great steps. So, like if you ask me if in 2017 people told me DeFi. Back then I said DeFi. Well, we're already doing DeFi. Bitcoin is DeFi. And so for me, it's like everything is amazing innovation. As a lawyer, I'm trying to support this always. So bullish on everything.
Nick?
Okay, I think with the proliferation of like LSDs, you're going to start seeing people use a significantly larger amount of leverage than they felt comfortable using before you could unstake. And I think you're going to have a similar kind of situation that you had when Curve launched, right? Right, you could lock up your Curve tokens and unlock, a boost, right, to boost your yield from LPing and Curve. The only problem is when everyone, the amount of yield that was possible, right, was, as an absolute amount, right, the amount of tokens were the same, right, and so when everyone is boosting, no one is boosting. But I think it's going to be a similar situation where you're going to have people lever up on LSD yield and DeFi so much that it's actually going to bring non-LSD yield down like significantly, right? And I think that's going to have like interesting effects of like where kind of people land on the spectrum of like what they're looking for, right? Because the trade-offs are going to become much more distinct.
Sure. That's already a whole different panel discussion.
And it's bullish or bearish depending on which side of the divide you sit on. I'm a little bit biased.
Tiny bit, yeah.
Yeah. Honestly, I think we're just getting started, to be honest. Like, I think the amount of innovation that's yet to take place is just like, it's just kicking off. We're like literally seeing the evolution of like this modular stack, continue to grow so quickly. Every, couple of months, there's a very new sort of, idea or like utilization play in the market. People are very excited about restaking. I think most people are like optimistically cautious about how that plays out and sort of the dynamics it introduces in Ethereum and its like core security model. But I think we're just literally seeing the beginning of this. And just to call it out, like staking today has been pure play staking, right? There's been nothing going on other than that, right? Whether you're an individual or a company or an institution, it's been like a one-way road and that's it, the journey ends there. I think what we're starting to see is like a real economy or like real industry form around this where loads of different players play loads of different roles and there's going to be a ton of different monetization opportunities within that.
Amazing.
The ability to withdraw and the potential emergence of a risk-free rate, activating more traditional companies to join the space. I think that's what excites me.
Cool.
We didn't talk about risk-taking, about the eigenlayer stuff. What I'm bullish on, what was said here, like we are early. There is still a lot of development to do on the protocol level, on the side of the UX for home stakers, for distributed staking pools. So what I'm hoping for is more of this kind of stuff, like better tools for handling Ethereum trustlessly in general, but especially in the staking experience, having more or like improving the experience for distributed staking pools, and also empowering the home stakers. Yeah.
Awesome.
And all of this, not to be the bad guy, but regulation or the really, because it's like technical developments that this is one thing that allows a lot of financial activity that is connected to the real world, and this is like maybe a big clash that will come or evolution. Yeah, and this is important also.
I think you need the same hoodie that he's wearing, the Institute of Crypto Anarchy.
Yeah.
By the way, yeah, I wanted to mention, guys, anybody here, if you want to run your own node and you are scared of the terminal, just ask me or write to me. I'm always glad to help with this kind of stuff if you want to help the network. Yeah.
There you go, call to action. And then can I get a big round of applause for this great panel?
Thank you very much, Elia. That is already it for today, the second day of Ethereum Zurich. Thank you very much, everyone, for joining. Things will take up again tomorrow. I won't be with you, but enjoy.